Hey, good morning. So thank you for being here so early in the morning on the first day. Apologies for that, not our decision. And welcome to the first joint Egocentric Vision workshop, which is held in conjunction with CPPR 2024, as you know, and it will be a full day event today. And so thank you on behalf of all the workshop organizers that you see here in the slides. And thanks to them for the organization of this event. So I'm just gonna say a few words, and then we can start with the program. So this is the first joint Egocentric Vision workshop. We called it EgoVis, but I think an issue we need to address is have we met before? So this is the first Egocentric Vision workshop, but I mean many familiar faces, and we probably already know each other. Some of us know each other very well. So I think we need to spend just a few words on what's the history behind this first edition of the workshop, because there are some past events that are very related to this workshop, and these are the most related ones. There are maybe others older than this, which are not in this slide, but for sure, some workshop series that are very related to this workshop are like the Epic workshop series and Ego4D, but also the human body, hands, and activities from Egocentric and multi-view cameras, and ARIA tutorials and past workshops. And everything starts with the EgoVis board, which was established last year. And this is a diverse set of people, volunteers that contributed to the field. And the idea is that this board tries to bring together different people and different communities, sub-communities, who have been working on egocentric vision in the past. And the result is these new series of workshops. And the idea is to unify previous efforts so that people can get together in the same room and talk about the same things more easily. And so the EgoVis workshop brings together a diverse set of challenges. So as previous workshop, we based a lot the whole program on challenges, because it is a good way to get together people who are actually working on the specific problems that we have. And so specifically, the HoloAssist community, Ego4D and EgoX4D, the ARIA community, and the Epic Kitchens community. And these are the main communities which are in this initiative. This is a very brief summary of the program. So we have keynotes, and we have challenges. We have then we have a poster session, and we have a distinguished paper awards. You can find our program also online. So very briefly, we have 4 different keynotes at the times that you see there. So the first one is going to be in a couple of minutes by Jim Ray, and these are briefly the times, but I mean you can find all the information online. And then we have 4 different slots for the challenges, where the results of the challenges in the different data sets will be announced. And these are the times that you see here in the program. And then we have a poster session. This is during the coffee break. A couple of information about that is this is going to be in another building, in the Arch building. So you have to reach that building. It's in 4E. It should be the same place where you can get your posters if you print it through their service. And we're going to have 18 extended abstracts. So this is ongoing or already published work of people who submitted their work to the workshop, and they were selected to present. There are poster numbers which have been assigned. So if you're going to present, please stick to your poster number and use the appropriate poster boards. And also, we have been instructed that we should be able to use those boards only at those times. So please remove the posters after the poster session. And we also have 17 papers who have been invited from the main conference from CPPR. So these are CPPR works. And the idea is that this will be, we hope, helpful for you to get a preview of what cool works are going to be presented later in the conference. And you'll also see online the presentation details for CPPR, so you can make a list of things that any way you want to attend during the main CPPR conference. And this is same time, 10:20 to 11:20. All right, we also have a lunch break, of course, and a coffee break in the afternoon. And right after the lunch break, we're going to have the EgoVis 2022 and 2023 Distinguished Paper Awards, where we will give awards to some papers that have been selected by the EgoVis board and which have been found to be particularly impactful despite being published in the last couple of years. So I invite you to attend and to see the list, which is anyway already online on our website if you want to have a look at it. And finally, we're going to conclude the workshop at about 5:30 p.m. when we finish everything. All right, so we're now ready for the first keynote talk, and Siddhant is going to chair the session. But give us a moment for.
You need this adapter?
Oh, I think I
just use USB.
I'm Siddhant. I'm one
Oh,
of the
okay.
organizers
Yeah.
for the EgoVis workshop. So today we are very fortunate to have Jim Ray, who is the founder professor of computer science and industrial and enterprise systems engineering at University of Illinois, Urbana-Champaign. Previously, he was a professor in the School of Interactive Computing at the Georgia Tech Institute of Technology, where he then co-directed the Health for Center Analytics and Informatics. In this keynote, Jim will be speaking on egocentric view of social AI. Please join me in welcoming Jim Ray.
It's a rather large file, so. Is this on, by the way? Testing?
Should be on.
Doesn't seem to be. Testing? Or should I just be loud? When I touch this, it doesn't make a sound, so.
Yes, that's true. Or is there anything? No.
Oh, now it's on, okay. And let me just check whether the audio on these slides play,
Yes.
just in case there's a problem.
Yeah, that's why I was thinking so hard. I was like,
Just click here. Oh.
Well, that's way maybe you don't,
I could try.
because I'm not trying to find out who you do something. Yeah, if you feel confident in.
Is this working? Yeah, this is working.
that's why I was thinking so hard. I was like,
Is there mic picking it up?
Music one.
Enough?
Well, that's way maybe you don't,
I'm not sure.
because I'm not trying to find.
Can you
out
guys
who
hear it in the
do
room?
something.
Yeah.
Yeah, if you feel
I can just
confident.
I can just mic the laptop. It's not a big deal.
Okay, but is it coming? I think it's feasible. If you can.
Yeah, let's try one more time.
Into the wrong screen.
that's why I was thinking so hard. I was like,
Where does the sound exactly come from? I'm not sure.
It's coming from.
Music.
Okay, let's just do that. I'll mic it with the mic on
I'm
the.
not trying to find.
The wrong screen.
Let me just leave it
Yeah,
there.
if you
Get it.
feel confident.
The wrong screen. Oh, yes, and the presenters be on the
Ah, right. That's the typical Zoom problem.
Is this fine or do you need?
I don't need those presenter notes.
Okay.
Does that work for
Then it's
Zoom?
fine.
Okay,
Yeah,
great.
it's fine.
Awesome. And I'm back to this again, I think. On Zoom, is it still a problem? Can you do your magic again? I think every time I go back into the thing, it resets it.
Should be this.
It's just in Italian.
No.
Understand.
Yeah, that's why.
All right. Well, thank you very much for the invitation to be here. And delighted to share with you some of the work we're doing at Georgia Tech and now at Illinois on understanding social interactions. Actually, I guess I'm 5 minutes early. Is it okay to start, or should I hang out awkwardly for 5 more minutes up here? Okay, better for me. All right. So I wanted to just set the stage for a second by giving you something to take a look at.
You know Jack Edrich over in the county? He committed suicide. Yeah, hi, Ken Crane. Listen, I gotta get those photos from the retoucher by tomorrow morning, okay?
I'm leaving you.
Honey, please, I can't hear. What? Okay, you too. Thanks a lot. See you tomorrow. You guys eat?
Ted, I'm leaving you. Ted. Keys. Here are my keys. Here's my American Express card. Here's my Bloomingdale's credit card. Here's my checkbook. I've taken $2,000 out of our savings account because that's what I had in the bank when we first got married.
What's this, some kind of joke?
Here's the cleaning. Here's the laundry ticket. You can pick them both up on Saturday. You have to
Joe,
pick
you
them up
wanna
on
tell me
Saturday.
what's the matter?
I paid the rent, I paid the
No.
Con Ed bill, and I paid the phone bill, so.
Or you really pick your times to. Well, I'm sorry that I was late, but I was busy making a living, all right? Come on, okay? Can we stop now?
So that's everything.
All right, so even if you didn't watch this classic 70s movie from the US, as a human familiar with social interactions, you can already make a lot of deductions about this very short clip. You can think about what is the relationship between the two actors in this case, Ted and Joanna. You can understand how they view each other, get some clues about that. You can understand what's happening with their relationship. You can make predictions about the future. What are their goals? What are they likely to do next? So the building blocks for these kind of inferences, of course, are the kind of the meat and potatoes of multimodal analysis that we've seen over the past few decades in our community. So understanding the visual component of that interaction, gestures, facial expressions, and so on, understanding the dialogue, who said what to whom. But for humans, those low-level details are just the building blocks, and all the important stuff actually lives in the interactions between the individuals and their relationships over time. And understanding those interactions and relationships is really the core of what we're considering to be social AI. And this is essentially kind of the grand challenge for our field for the next several decades, is to build AI models that can really kind of get to the core of those most basic human interactions and understand them in fine-grained detail on the basis of data like you just saw. And, you know, I don't have to tell you the different examples and applications that this might enable in virtual reality, in social agents, and so on. Okay, so my goal today is to sort of give you a snapshot of where we are as a field with respect to this challenge, and along the way, just showcase some work that we've been doing. So in order to understand social interaction, the first thing you need is some kind of conceptual model. How do we describe this process of interacting computationally? And the starting point in this case is just two individuals, and then the basic communication channels. They're the words that they say, the sounds they make, and then all their nonverbal cues combined. And in order to communicate, the most important thing is that you have some set of shared beliefs, things that you have in common that are the substrate for the interaction. And these can exist at many levels. So at the lowest level, there's the interaction itself. How do you take turns? How do you coordinate so that you're speaking appropriately at the right times? All this is done unconsciously by humans all the time throughout our day. Then there's higher level things like our social relationships. How do we relate to others? What's the nature of those relationships? And then the interaction takes place in a specific situated context, like in this case, in an apartment, in an example that you saw, or at a ball game or what have you. And that context informs as well the interaction. And lastly, there's some set of beliefs about the world, some set of facts we have in common, and then we use that in part to communicate. Now, one of the most important things that happens during communication is actually establishing these shared beliefs. You figure out, does the person you're talking to understand you? Do they get what you're saying? You rephrase, you kind of figure out what's going on if there's a problem. And that is in turn driven by your ability to make inferences about what your social partner believes. So your social partner has private beliefs that are in their brain. You can't access them directly, but you can make inferences about them. Okay, and so this process of inferring what your social partner believes about the world is a critical part of communication and something which is just beginning to be studied computationally. So if you then think about going back to that clip, what it would mean to analyze that clip, there's a bunch of things that we need to make progress on. So obviously we need to make progress on the low-level modalities, particularly the visual ones. I think speech is in relatively good shape, but the nonverbal communication still remains, I think, is a challenge for our field. Going beyond that, we have to talk about how people are attending to social cues in their environment, and then ultimately build this theory of mind, which is your ability to make these inferences about your social partner that I was referring to earlier. So these are some key challenges that I'll touch on today. Now, in the process of looking at this, I just want to emphasize, due to our workshop here, the importance of doing this from an egocentric perspective. Okay, so this is the perspective that humans actually have when they're interacting. And one of our basic tenets that got us into this area a long time ago is the importance of capturing that interaction from the perspective of those that are participating directly. And you can see a lot of reasons for doing this scientifically and also just pragmatically. And we still believe this is the best way to sort of build agents that can understand interactions, that have this perspective. So I just want to walk you through a couple of basic problems just to kind of set the stage. What are the challenges that arise in solving these various tasks? And the first problem, the one that we looked at first, is this basic idea of eye contact. So this basic interaction of looking at someone's eyes. It's a visual perception task. It's a building block for social interaction. It's extremely important in communication. And so early on, we built a data set that let us tackle this problem. And in this data set, there's a child. In this case, I'll talk about why it's a child in a little bit, sitting across the table from an examiner, an adult who's wearing a pair of glasses with a camera right here on the bridge of the nose. And you can see from the setup that whenever the child looks at the examiner, they're looking right into the camera that's in between the examiner's eyes. So then you can frame eye contact detection as just a binary classification task. And in that setup, it's actually quite easy to solve. And here you can see the performance. This is a child that we collected data from in Atlanta at Georgia Tech in a lab that we had there. You can see green whenever the child makes eye contact with the examiner. The examiner is wearing the camera here, of course. And then you'll see in a second, this is a boy with autism at our partner site in Weill Cornell Medical Center. And again, he doesn't make as much eye contact, but when he does, we're able to detect it with this method. All right. And so one of the key properties of this method is the accuracy. And this is a really important aspect, particularly when we want to think about using these types of computational models to support developmental psychologists, behavioral psychologists that want to use these tools to treat humans, to deal with people and their various challenges and conditions that may arise in terms of social interaction, with autism being kind of a canonical example. For these folks to use these methods as tools, they have to be accurate. And so one of the things we've been really pushing on is understanding how accurate are these models and then having the ability to validate them. And so here you can just see evidence that shows that this eye contact detection model that I just introduced is in fact working as well as humans are at this particular task. So each yellow dot is a human expert rater of eye contact in video being compared to their fellow humans. So the spread of those yellow dots is kind of the uncertainty or the ambiguity that humans have in assessing the social behavior. And humans, of course, are the gold standard for all of this work. And they are also, not perfect in some sense in assessing or agreeing what's going on. And the little green diamond is our algorithm, and it's right in the middle of the humans. So if you took one of the humans away, replaced it with AI, then the accuracy in rating that behavior would not change. And that's our kind of definition of human level performance, okay? So from that perspective, the research program here is actually pretty simple. We've been doing it now for more than 8 years, which is simply, pick out and identify all these important constructs like eye contact, collect appropriate data sets and appropriate populations, build these AI models, and then validate that they're working as well as people are in solving these tasks. And if you complete all those, constructs, you can then really build this foundation for social AI. All right. So, of course, eye contact is just a tiny example of some of the, visual behaviors of interest, and the visual behaviors themselves are only a small part of the overall space. Let's talk about some of the others. So more generally, we're thinking about an individual shown on the right here interacting with their peers in some environment. And then eye contact in that case is just, are any of my social partners looking at me? But there's many other social gaze behaviors that are very important. For example, we'd also like to understand where our partners themselves are looking. Who are they attending to? What parts of the environment are they attending to? That information helps us understand what information they're receiving. It helps us understand this perspective taking, what they might believe about the world. Okay, so this is a basic challenge to understand the attention of others. And that's framed, as you can see in this example. So there's a video clip, and at the top row, we focus on the woman. You put the green box around her head. It means she is the target of analysis. And then we identify where she's looking in every frame. And so the green dot shows where we think she's looking. And that includes the case we can't tell where she's looking because she's looking somewhere off the screen. And in that case, you just see the green box with no dot. And then we can do the same analysis for the man in the row below. Repeat this for all the people in the scene to understand their patterns of visual attention. And so I'll just present some, at the moment, unpublished work that's our latest effort along these lines, and use this to illustrate this sort of task. So here's the definition of the problem. So you've got an image, you've got a bounding box for the head. Your output is some heat map that shows where you think the person is looking, including whether you can see them see it in the frame or not. And the ground truth data for this, of course, is always humans clicking in the image to know where they think the person is looking, okay? And so there's been a long history of work in this area. I won't recap all of it, but this is an early paper with a two-stream architecture. We introduced an architecture a few years ago that was much more complicated and also worked over time. We introduced a data set that's still the kind of the standard data set for video-based analysis of this task. And then recently, things have gotten really complicated. So I'll just highlight for you some of the properties of some recent models. They're fusing all kinds of different channels, depth, body pose, focusing on the eyes, et cetera, all in an attempt to drive the accuracy higher for this task. And these architectures have gotten super complicated, okay? And not only that, but then adding all these separate modules requires them to be fused, and this fusion step is also challenging. And if you don't get it right, then you don't get the benefit of all these additional parameters you've added to your model, which in many cases are a massive number of extra parameters. Now, this is interesting because this is in contrast to the progress we see in other parts of computer vision, where there now exist these very large models with many parameters, but a single model, which is capable of solving multiple tasks at the same time, okay? And so in this case, you can see Dino V2 and some of the standard things that it's able to do. If we go back and look at the cues that are thought to be useful in predicting attention, we can notice an interesting fact that these cues also take the form of dense prediction tasks in the image, predicting at every location something which is happening, which is relevant to the task at hand. So this raises kind of an obvious question. Could we leverage these existing foundation models and actually solve this task of visual attention estimation? Now, you're probably used to, these foundation models doing everything. So when I say that, you may just say, oh, yes, it sounds reasonable. But the thing I want to remind you is that the people that built these models, they didn't care about social attention. Okay, they didn't care about people, in the context of their models. And they really had no idea about this as a task. So it is a question, actually, whether or not these models and their representations contain sufficient information for us to understand visual attention. Okay, having spent this much time on it, you can imagine that the answer to this is yes. Okay, so this is a new architecture. This is the work of my student Fiona, who's, I think, somewhere in the back of the room right there. And the name is entirely hers, as well as everything else. And so the way this thing works is that it allows you to take this model, this Dino V2 model, you just freeze it, you don't touch it in any way, and you utilize the representation that it produces. And then with some additional downstream layers, you modify that representation to extract the information that it contains that is relevant for this visual attention estimation task. Okay, so this is in some ways a new approach to tackling these social cue related problems, not by collecting massive data sets and training complicated architectures, but rather taking the existing massive representations that already exist and then asking the question, how can they be repurposed to solve these tasks? All right, so this is doing really well compared to all the previous work. And I'll just show you some examples. That's a mistake right there. So these are all examples on the testing set for our data set we collected earlier. I'll just show you briefly some out-of-sample examples. These are just some YouTube clips that we downloaded and ran the model on. And it, of course, works less well on these as some of the others, but still works pretty well. Okay. So I think this is an interesting finding, and I think it has a couple of implications, but the one that I want to focus on is this hypothesis, okay, that you can see on the slide. It's possible that these models that we already have our hands on, so to speak, already contain extremely rich generalizable representations of the people and their behavior. They're just buried in the weights somewhere. And the question is, how much information is there? And if it's there across all the modalities of interest, if you think about all the models that are out there currently, this could be a really interesting path to tackling these problems. Now, one of the consequences of this hypothesis is that we have to think really hard about validation. So it's in this setting, we can imagine collecting validation data sets that are completely different from the data sets that are used to train the models. And that's actually super important to be totally different and not covered at all by the training sets the models are using. And how to collect those data sets actually, particularly in ways that would validate the utility of these models for conditions like autism and other types of developmental and mental health conditions. This is actually a non-trivial challenge that we started to work on. So we're collaborating with a variety of psychologists with data sets around human social behavior, and we're going to be building this validation data set to understand the performance of these models in a more kind of comprehensive and detailed way. All right, so now I'm going to accelerate a little bit and just get you through some of the other things that we're working towards. So we've been talking about pretty low-level attention-related behaviors. And in particular, there's a developmental trajectory that's relevant here, which is moving from sort of pairwise interactions, one person looking at another, to understanding interaction in this broader context. And there's this notion of what's called joint attention, which is that you're interacting around some object of interest. In the typical scenario, a child is playing with a toy and there's an adult there that they're interacting with in some social setting. And this is known to be really important developmentally in representing kind of a milestone of a child's social development. This happens at an age when children don't have very much verbal language, they mostly can't speak, but they can already communicate effectively with nonverbal cues. So developmentally, this is a really important window in time. And we've been kind of building tools to analyze these scenarios in our goal of understanding and supporting autism. So you're probably all familiar with autism as a developmental condition. I just want to highlight with this one finding here why doing attention analysis is so important. So this is showing a very famous study from a number of years ago. And what the study shows is that if you take children at intake, so when you first encounter them, and you just assess their nonverbal communication skills, and then you follow them for 4 years. Okay, so it's a long time developmentally with kids that are 18 months. 4 years is a long time. You follow them and you track their language skill, their ability to communicate with language. And these are all children with autism, by the way, whose communication in general is going to be impaired by their condition. But what you can show is that the sample of kids with autism can be divided into 2 groups. And the group that has high nonverbal communication skills when they're really young does much better than the group that has very few. And so nonverbal communication through these types of findings has been shown to be really important for predicting outcomes and understanding outcomes in autism. And so building better tools for analyzing nonverbal communication with computer vision, for example, can be a really useful tool in this field to help understand children's behavior. And this is an example of what that might look like. So this is the same kind of data sets I showed you earlier. These scenarios are designed so children have to interact socially in the context of a toy. So this is a classic joint attention type of task. And you can see the model's ability. This is an older model, by the way, but you still get the idea. This model's ability to infer where the child is looking. And this allows us to build a picture or a portrait of their nonverbal skill at an important window in time. But turning this into an actual measurement and model of joint attention is still an open problem. And there really still are not extremely good methods for doing that. So in general, this idea of joint attention, interacting in the context of an object, is super important developmentally, super important for social communication. And really, there aren't any satisfactory models right now, I would say. A bunch of different work's been done, but nothing that sort of is really exactly what you want. But I think given the progress and tools, this is a good time to really mount an attack on this task of joint attention. All right, so I've been talking a lot about visual attention, and I just want to shift gears briefly and bring in some other aspects of communication. So of course, there's the language itself, what we say with our words, and we'll get into how that might be used in a little bit. But it's also important to understand where people are listening, as well as understanding where they're looking. And of course, understanding where people are listening is much more challenging because there's no eye movements to focus in on to tell where attention is being allocated. It's entirely covert. But it is a crucial task, and humans have the ability in many cases to solve it by leveraging multiple modalities taken together. And so the first piece of work on this that we did, and this is actually, I think, the first piece of work on this task, particularly in this egocentric context, was done, again, by Fiona last year in collaboration with a group at Meta. And you can see our paper from last year at CVPR that shows the results on that. And this year, we're going to be presenting at this conference an update to this work. And this is about enlarging this idea of attending. In this case, we're just looking at where the egocentric user, the camera wearer, or the sensor wearer, in this work, we're understanding where that person is listening. Now we're kind of extending this work to include the entire scene. So the combination of my attention and the attention of my peers to each other and to me. So this is a more comprehensive analysis of these conversational interactions from these different perspectives. And so this is a work that Wenxi, are you in the room? Yeah, right back there in the back. Wenxi's going to be presenting this on Friday, so I encourage you to come see her poster. And I think she's also got a poster in the poster session in this workshop later in the afternoon. So you can get a preview on Friday, and then any unanswered here today, rather. I mean, not here, but in the other building today. Any unanswered questions, you can find Wenxi again on Friday. Okay. All right, so let's just quickly, and I'm not going to get into the details of this in part because I don't want to leave something to cover in the session. So this is the basic idea. I think this tells the key story. So we're going to go from this egocentric perspective of what am I looking at, listening to, understanding exocentric perspective, what are my social partners looking at and listening to, put them all together. And now we have a comprehensive characterization of the pattern of interactions among a set of people. Of course, if all these people are wearing some wearable sensor rig, then we'll be able to get each of their perspectives from different points of view. And that would be an amazing characterization of this pattern of interaction. And this is really pushing heavily into both the egocentric perspective and the combination of these modalities. So it gets beyond the classic speech-based analysis, which misses all the important information that's contained in the visual channels in these cases. And so this is an architecture. It looks very complicated for solving this task, given the video and a multi-channel audio. So this is a microphone array that produces multiple audio channels. And I encourage you to find Wenxi and get her to explain to you what's going on in this architecture. All right. So let me just give you a quick demo of how it works. So in this video, what you'll see is the egocentric perspective from one of the sensor wearers, and then you'll see and hear the interaction, and then we'll show you as this is evolving in time how the graph is being inferred and how it's being compared to the ground truth graph that was produced by analyzing this data set.
Actually, we
Just give you that one more time so you can hear it better.
actually we
Okay, so that's the audio and video, and this is the result of the analysis. All right, so that's a pretty complicated, actually, characterization of interaction, but it's operating at the level that is necessary if you want to truly understand how people are interacting and what information they're receiving from their partners and from their environment. So now I want to just basically give you a little bit more of a preview of some things to come. So we've been building up kind of step by step these different building blocks for understanding these interactions. And we've been building towards this ultimate goal, which is really a kind of multi-party, multimodal analysis, people interacting in a variety of contexts, talking in a variety of complicated patterns, utilizing all the different modalities of communication, visual and auditory, to understand not just who says what to whom, but what their goals are, what they're trying to accomplish, what their relationships are. And there's still no single model that is capable of doing this, but I think we're making steady progress step by step towards such a model. So this is kind of at the heart of the question, is how to get at the dynamics of this interaction using all these modalities. And I just want to now preview a couple of data sets that have become available recently that give us an angle on this. So the first data set is one that you're probably all very familiar with, Ego4D. But Ego4D was actually a very complicated data set with many different constituent components. And so one part of it that I want to highlight here is the social benchmark within Ego4D, which is a subset of the data that was specifically focused on understanding social interactions. And so here are some of the statistics. So again, this is just the subset of Ego4D that contains people interacting with each other in a variety of complicated environments and very naturalistic settings as well. And you can see the different sites where the data was collected. And notably, it was not just sites in the US. This is one issue that we face in general in this area, is kind of a Western bias in a lot of these data sets. And so we're steadily moving towards improving upon that. A variety of complex sensors, head-worn recorders, eye tracking glasses, and so on are present in this data set. And then a variety of different tasks have been framed and worked on. And this is just a sample of what the data looks like. Again, this is the collection at Georgia Tech.
that's why I was thinking so hard. I was like,
So you can see the 4 videos all time locked together, time synced, and then a variety of complicated behaviors and patterns of interaction that are captured on this data set.
Yeah, if you feel confident.
And so we've been working on this steadily in the ensuing years since Ego4D came out. And one of the most basic things we're trying to understand is the behaviors in these games that are being played. And these are social deduction games like Mafia one night werewolf, where you're trying to guess what your partner's roles are and deceive each other essentially to win the game. And so the first piece of work we did was looking at persuasion strategies, understanding how people are trying to fool their peers through what they say and do.
Villager. What are you? This year, and I looked in there, and I forgot what the
So this guy is trying unsuccessfully to lie to his friends who don't believe him. So there you go. So that's a failed attempt to persuade. And so this data set contains a rich set of annotated examples of persuasion strategies. You can see them here. And it provides a benchmark and a series of tasks for understanding persuasion strategies in the context of these egocentric kind of face-to-face interactions, including data from the Ego 40 data set and also data from YouTube as well. So kind of enriched by additional videos. And then this week we'll be presenting a new work along these lines. So this is an oral that Sangmin has. Sangmin, are you in the room? No, I think he's not here yet. So he's going to be presenting on Thursday a talk about this new kind of augmented data set that includes additional tasks. And you can just get a sense of some of them here. So there's a task around understanding who you're speaking to, so identifying the speaking target of the utterance. Pronoun co-reference resolution is a basic task on understanding natural language, but it's one that benefits tremendously from having access to visual information. So a lot of this is about really doing a better job of taking the visual channel and utilizing it to understand the language itself, which for adult interaction is super important, actually. And so there's a number of really challenging tasks here that are all brand new and a very large data set that lets you look at them. One of the key challenges is to align these modalities. So take the utterance, which has been transcribed, so you understand what someone is saying, and then figure out who exactly is the person in the video that was saying that, at what time were they saying it. And so that dense alignment between the visual information and the natural language is really important and quite challenging, actually, in this egocentric perspective. And there's a bunch of novel baseline models that you can compete against. And this is a baseline architecture that I'll skip. And the main point I want to make is that the accuracy is very low. Okay, so please go work on this data set. You can certainly improve these numbers, and then you can publish that in some other meeting. All right. So I'll start wrapping things up a little bit. So just want to thank our sponsors over the years for supporting this work. I want to just acknowledge the amazing team of collaborators, both computer scientists and psychologists we've had the pleasure of working with in many different institutions. And I just want to conclude by saying that there's a grand challenge before us to understand human social interaction from this multimodal perspective. I think we're right at the cusp of being able to make progress on this problem in ways that will surprise everyone. And a key aspect of it is for vision and auditory and NLP modalities to come together, which is a topic this community is very excited about. And progress along these lines would be very helpful, not just in the standard kind of VR and AR settings you're probably thinking about, but also in helping children with developmental conditions to be more effectively treated and hopefully have a more successful lives. So there's many things and many motivations that can be behind this work. With that, I'll conclude. Thank you.
Thank you so much, Jim, for an interesting talk. So we have time for 2 or 3 questions. So does anyone have any questions to us? Anyone? Yes.
So I think all the benchmarks and the model are great for understanding facial term relationship or actually speaking to group. But I also feel like there's some gap between the first example of the drama, because it's more like holistic or like people trying to transmit their intention in more kind of a cooperative manner rather than just talking to you. What's your opinion for?
Yeah, so I mean, the example that I led with, of course, obviously, this is a highly charged emotional scene in a movie where it's kind of the key scene in the movie where this, you watched it for an hour and then it leads up to this, this kind of development. So it's probably much more enriched emotionally than most of your daily life interactions, hopefully, but I think it's still, the pattern is still there, that to really understand something like that, you have to understand how do the people relate to each other, what do they think about each other, and then interpret all the cues, right? So the objects in the scene played a role in communicating the intentions of the actors. So it's not just the words, it's also what they're doing with their faces and their hands. And to me, that's the key challenge. But one way to answer your question is yes, the challenge is before us. It hasn't been solved yet. And there's plenty of work to do to get there. Yeah, it's a good question. So in gaze, we know from example, for example, from eye tracking work, that the temporal information is really important. When you have access to eye movements at really high temporal sampling rates, you can do a lot just in the temporal domain without doing anything else. The temporal dimension in the type of attention we can get from video is also important. And it's not modeled nearly as well as the spatial dimension. So there's a few papers like our earlier paper that does this, but in general, it's pretty open. So I think it's important, and I think it's pretty open right now, how to bring time into that picture effectively.
You had one more question after that? Yes, please. Oh, so I think, yeah, yes.
So for the more complicated scenarios like these multi-person games, at what point does the speech or the language just sort of take over compared to the NDC?
Yeah, it's a good question. So the question is, in these more complex, interactions among adults in the context of the game where there are rules, if you just look at the dialogue alone, the NLP, is that enough? You really need the video. And I think the paper that we'll present this week has significant evidence that you do need the video, but it is, there's a sense in which it plays a supporting role. However, the thing about it is that in real life interactions, the speech can be very complicated. In particular, people say very little, they communicate a lot and say very little. The transcripts, if you've ever seen them of interactions, tend to be really opaque if you just have the transcript alone. So I think it's an open question as to how much information vision is going to provide, but the need for vision, I think, is pretty clearly established. Yeah.
Thank you so much, Jim,
You bet.
for an amazing talk. Let's thank him again. Now we will hear from the Hollow Access challenges, which will be online.
Okay, so we have a couple of minutes where we try to check if everything is working with the audio. So we'll start in a couple of minutes.
Hey, can you hear me?
Yes. Let me check if I can get the audio to stream, because maybe it's just this one.
Can you just
Can you try to speak and we see if
Yeah, I'm speaking now. How about now?
okay. Nothing changed. Just a moment.
Or should I increase my mic volume?
Right. Okay. So how do we get audio from the computer? So I tried to connect this. I don't know if there is any other extra step that I need to take.
You cannot hear me at all, or it's just
No. So we can hear you, but only through my laptop, and we would like this to go so that other people can. Well,
okay, I got it.
oh,
You have your
works.
device manager.
You can,
Oh, maybe
yeah. I think it's this one.
might be this one.
Yeah, try that. Yeah, try that. One that just popped up.
Okay.
Is eMeet.
eMeet, yeah, exactly.
Okay, can you try again?
Okay, how about now?
I don't know if you are.
Yeah.
Okay,
Does it
thank
work?
you so much. Thank you.
Okay.
Okay, so just give me a moment because I still need to get a chance to download the video the message that you
Oh.
sent me.
Yeah, please
Just let
go ahead.
me just disconnect and check it. We should, but I thought it was on charge. Okay, thank you. Good point. I'll try to fix that.
And I just want to make sure the video from my side also, whether you can hear the sound or not. Let me quickly go. Do you hear anything from the video?
No, not from the video. We hear you, but not from the video.
Okay, if you cannot hear me, then it's still fine. I can just explain by verbally. Okay, so I believe you can see my screen.
Yes, just let me check. Is it visible on the, okay, so it works. Okay, so just give me a moment. I download all the videos that you sent, so then we can proceed smoothly.
Perfect.
Do you think you can play those videos back from your end? Because that would make things easier.
Yeah, I can try. Let me try quickly then. For example, but what I'm not sure is like whether we can play sound and the connection is good or not. So let me try. Could you hear any
So
sound?
no, but I think there is an option when you share your screen. There is an
Aha.
option to forward the audio. So you should stop sharing and then share again.
Okay, share again.
And there should be an option saying, I don't
Share
know, I'm not
sound.
sure. Yes, there should be.
Today, I would like to present our work on
Yes,
action.
I can hear it now. So
Okay.
let's try to do it this way.
Okay, this sounds great. That's for me.
So then in that case, we're ready to go. All right, thank you for your patience.
Yeah, thank you so much for setting up this.
You're sharing the presenter view. You should switch the view,
Oh,
seeing the
okay.
notes.
That's very interesting.
Okay, now that's great. Thank you.
Okay, thank you. Okay, so hi, my name is Tae-kwon. I'm currently a PhD student at CVG, ETH Zurich, and today I will present about our hollow assist challenges. So first, I will introduce like our data set first to get more context. After then, we will talk about what challenges we have, and then like the participants, they will present about their own results. So yeah, so like to implement interactive AI assistant in AR and VR, I think there are many challenges. So when you think about the mixed reality applications, one of the most popular application is AR remote assistant. So it's basically egocentric communication. So the user call to the somewhere far away, remote person, and they get help through the egocentric view. And then the person behind the this mixed reality device, they explain what we need to do. And the other popular application in mixed reality, there is a app called AI Guide, and this is basically like designers design, like a warm up step by step for some procedure or task, and then they give some guidance through this like mixed reality. So meaning that there is some 3D arrow that what we need to interact with, or like a or what will be the next step in this like a procedure task. However, these two all require a tons of effort to implement. Like for example, AR remote assistant, we always need like a person behind, and AR guide also designers need to design step by step. So actually, yeah, then what we should do to implement this interactive AI assistant? So the challenge is lack of real world interaction data set with a full spectrum of perceptual sensors. So therefore, that's why we collect this hollow assist data set. This is captured by 350 unique instructor performer pairs, offers 169 hours of data with 8 modalities and 2,243 sessions. So as you can see, we have many other modalities. So we can see modality one by one. Here, for example, we have RGB and head pose. We also have depth image, and then you can also see point cloud in the scene. We also have like a 3D hand pose, and then this is a projected hand pose. We also have eye gaze. You can see orange ray here.
Audio.
We also have audio and conversation between people. And we also have IMU, like for example, accelerometer and a magnetometer. Lastly, we also have After Effects text summary, which is annotated by annotators after they watch the entire video. So what makes our data set be more unique? So we basically always have performer and instructor. So we always require at least two persons to record this data. And whatever does from this performer side, the instructor can watch what they are doing through this laptop, like a screen, and then intervene whenever they need some help. So for example, in this example, the performer trying to assemble the Nintendo Switch grip, and instructor watching that scene in real time through the screen. And then instructor can intervene in real time. So when they make a mistake, then instructor say, oh, okay, so that is not the correct way. You need to assemble your like a right side of the Nintendo Switch from top to down, for example. So here is a more detailed example. So this is manipulating a vehicle example, and then the user, the performer, trying to do some like action to fix this like a state, for example. And then since this is correct action, the instructor just say, okay, now we need to go to the like, next step, which is like a slide the shifter arm onto the mounting peg, etc. And then by following this instruction, the user, the performer do some like a manipulation, but they here like for example they did mistake. So at that time, the instructor intervene to the situation and then just comment what they need to do. Like they said, oh, it's right below your hand. It's that long piece of metal. And then finally, the performer do the correct action, and then it goes like to complete the task. So there are many different object categories. For example, there are small objects that we can easily like manipulate like that, and these objects usually change their object pose quite like frequently. For example, cameras, Nintendo Switch, small copy machine, or RAM graphic card. We also have medium-sized object. We can move it, but once when you manipulate, it usually stay in that locations, like copy machine or like small printers. We also have big object. Usually they are fixed in some location, and then it's like quite like a large, like furnitures or some like a big printer, big copy machine. Also, we have like a rare object, which we frequently we only can see in the like a laboratory or some like a factory. So here's some like a example of our annotations. We have coarse grained action. Usually takes like 30 to 40 seconds. in its very goal-driven actions. And we also have fine-grained action, which is 1 to 2, like, around like a 3 second of each action. And then this is very, like a fine-grained, like we basically annotate very like a very small chunk of the action whenever they move. And then also we annotate a conversation between the like instructor and performer. So we can see some like a data statistics here. We try to collect the different objects like a bit like evenly as much as possible. And then we can see the like a total session length per activity, for example. And this utility card usually takes like the most. It takes a lot of time, like usually like 30 to 40 minutes to assemble. That's why we have the most lengthy here. And then we also have like some like a skill level and like every session level here. What we maybe need to see more like closely is this like a course action, for example, it usually lasts like between 30 to 6 seconds the most. And for the fine-grained action, we have so many fine-grained action between 1 to 2 seconds. We also have like a verb, noun for fine-grained and coarse-grained action here. Let's see some video example. I think it will be makes you understand a bit more clear. So like, basically now the instructor like explain what they need to do. And then now performer try to follow the instruction. And performer load the paper up.
Open the gray flap, and there's a blue tab that closes in the paper.
Yeah, since the performer did like something wrong, so the instructor tried to give more information what they need to actually do.
The one further into the paper.
Oh.
Yeah, that one. And then there's a blue tab on your left-hand side.
Mhm.
And press that closer towards the paper.
Yeah, and then like the instructor provides more tips how to properly load the paper here.
Yeah, that's good. Perfect. And there's an output tray in the front that you have to pull out as well. And there's an extra tab there that you rotate outwards at the closest to you. There's on the left-hand side, you just pull on the tray, and just pull that out.
Like
Closer to you. Yeah, that one.
oh yeah, sorry.
So I'm not sure you can clearly hear the sound or not, but there are like many interaction between the participant and the instructor to complete a task together. So in this EgoVis challenge, we have two challenges. First one is fine-grained action recognition, and the second one is mistake detection. We also have an intervention type prediction, 3D hand pose forecasting, but we didn't cover in this workshop, but we are looking forward to cover these challenges in the future as well. So fine-grained action recognition. So given a short clip, our participants need to classify fine-grained action label, which usually lasts like 1 to 2 seconds. And in this example, you can see there's like a fine-grained action label. They put like copy bin bag for. So it is like basically we annotate this using like a verb and noun, and the participant need to classify them correctly. And there's also mistake detection. So they need to take the features from the start of the beginning of the coarse-grained action until the end of the current action clip. And as you can see here, like there's like input, and then you can see whether it's like a mistake or correction. In this test, they need to change the like a printer like ink. So whenever they, touch the the paper part, it is like annotated as mistake, and then now it's going the correct way. And there's another benchmark in intervention type prediction. We want to know which intervention type, for example, like a conforming action or correct mistake or follow up from the instructors. And given an input of like Windows of 5 seconds before the intervention. And there is another one called the 3D hand pose forecasting. Basically, given 3 seconds of input here, for example, for your information, green hand pose is ground truth and red is forecasting. And then forecasting is like this. So we want to know the continuous 3D hand pose for the next 0.5 and 1 and 1.5 seconds. But this is very challenging. So this is like a failure example, and you can see it's not easy to get like a correct hand pose for the future. But we believe this will be like a possible applications for how we can actually guide in 3D space. So we also wanna, do this like benchmark like promote this benchmark more. In addition to the data set and paper, we also share more resources. For example, we also share this like a capture code called PSI. You can, if you go to this link, this is the effort from the PSI team in Microsoft, and we collaborate to build this application to capture the HoloAssist dataset. And then now these applications are open, so you can more easily capture all the data stream from HoloLens using this app. There's like a HoloLens capture app and HoloLens capture server, and then exporter as well. We also share hand-eye gaze projection code, and with this code you can also get this like 2D projected hand pose and as well as eye gaze through using this code. So yeah, if you see this projected hand pose and eye gaze is quite interesting. How usually the user focus on when they do some manipulative task. So yeah, from now on, let's share our challenging results. So first, like a fine-grained action recognition. So we actually left UniBZ. Congratulations, you got like a first rank in this fine-grained action recognition. Congratulations for like Artem and Oswald. So they basically improved a lot, like for the like top 1 accuracy, like about like 13%, and for top 5 around like 8%. And then like also like for the like verb and noun accuracies as well. And for the mistake detection, also congratulations for the Michelle, Antonino, and Giovanni. You got the first ranked in this mistake detection benchmark, and this team improved around 15% for the like F1 overall score, which is quite a lot of increasement compared to our baseline, which is around 35. So yeah, so each team will present their own result. So let's start from fine-grained action recognition.
Hello, my name is Artem. I am a student at the University of Bolzano, Italy. And today I would like to present our work on action recognition task using HoloAssist dataset. HoloAssist is a novel, large-scale, egocentric dataset where 2 people collaboratively complete physical tasks. It includes more than 100 hours of undated videos and approximately 2,000 fine-grained actions. It also includes 7 modalities, but we used only RGB videos in our model. In this action recognition task, we need to perform multi-class classification of the fine-grained actions across different activities. Here, I would like to introduce our pipeline. First of all, we worked with trimmed fine-grained clips independently. And given that such clips can be very short, the duration can be even less than 1 second, the original frame rate of 30 FPS was preserved during the video decoding process. So our framework is similar to the framework from TSN paper, or Temporal Segment Network, where both temporal and spatial sampling methods are employed. To be more precise, we uniformly sample frames from predefined segments. In the final model, we used 16 such segments. And after this, we stack and crop the sampled frames and then input the data into 2D convolutional neural network. It could be any 2D CNN, such as ResNet or Inception. However, such CNN is augmented with the fusion module that I will discuss in the next slides. Finally, we train our model using cross-entropy loss to predict class logits. Okay, the main difficulty of video understanding lies in how to fuse the temporal and spatial dimensions accurately and efficiently. To address this problem, the gate-shift fuse, or simply GSF network architecture, has been developed. The GSF is efficient spatial temporal feature extractor that can be integrated into any 2D CNN structure with almost no additional parameters. On the right side of the slide, there are 2 examples of Inception and ResNet, where the GSF module is inserted. And the experiments show that these particular locations of GSF give the best result. Actually, the GSF is a generalization of a popular module called TSM, or Temporal Shift Module, which performs temporal modeling by moving the features along temporal dimension. GSF also blends features among the temporal dimension using shift operations. However, in the TSM, the feature flow is fixed by design. It means that features are forwarded from one block to the next block without data-dependent decision. GSF replaces the fixed channel split with learnable blocks that I will show in the next slide here. Here I will explain in the high level how the architecture of GSF works. After the convolutional block, which is blue here, we split channels into 2 groups and apply grouped spatial gating for each of them. The gating block learns a spatial weight maps for each group that determine which regions are shifted in time and which regions are not shifted. And it's done by separating 2D convolution output into group gated features and residual features. Group-gated features then go through time shifts to encode temporal information. And finally, we would like to merge shifted features with residual features. The easiest way would be to make just a summation, but fusion by summation may be not optimal, and instead GSF performs weighted averaging on the two feature groups. To sum up, GSF employs adaptive blocks that can be learned based on the data. Okay, in order to train the network, we used batch size of 32 to best fit our resources. The stochastic gradient descent optimizer with momentum and multi-step learning rate scheduler, where the base learning rate is set to 0.01, which decreases by half at epochs 5, 10, 13, and 15, with a total number of epochs of 15. Also, we tried different backbones, fusion methods, and pre-trained weights. The best result was achieved by using Inception v3 backbone plus GSF fusion module and something pre-trained weights. The validation learning curves on the right show that GSF outperforms other fusion methods. For the inference, we conducted temporal and spatial sampling simultaneously and repeat the process 10 times. So the predicted logits from each of the 10 sampled clips are averaged to obtain the final video clip prediction. As you can see in this table, our approach achieves better accuracy than the timesformer baseline, and notably that it was achieved with fewer parameters. Yes, this is the end of my presentation, and thank you for your attention. Hello.
Yeah, so thank you so much for your recorded presentation. Due to the time manner, we will merge the two Q&A session in the end of the next presentation. So I will go to this mistake detection presentation by Michelle. Yeah, I will play here.
Hello everyone, I am Michele Mazzamuto from the University of Catania. Today I'm pleased to present the solution developed by me and the Unicity team for the mistake detection challenge of HoloAssist. Smart glasses have recently gained significant popularity with various existing products available on the market, capable of providing assistance to the user through augmented reality. In order to provide timely assistance, wearable device should be able to identify moments in which the user makes mistakes or is confused and require help. If such instances are properly detected, the AI system can proactively support user by offering contextual information or suggestion on how to best carry out the task at hand. Our hypothesis is that mistakes manifest themselves through unusual behavior patterns displayed by the person wearing the camera, who may experience disorientation while performing the given task. We aim to develop a gaze behavior model, specifically a gaze prediction model. As we can see in this video from HoloAssist, after closing the paper tray and before making a mistake, the user exhibits some unusual and disoriented gaze behavior. The gaze pattern returns to normal as soon as the mistake ends. In the example we just saw, we can observe approximately 9 seconds of unusual and disoriented gaze behavior occurring before the student mistakenly grabs the incorrect tray from the printer. In our proposed setup, at each time step t, a model takes as input a video observed to a time step t and a relative 2D gaze trajectory, where each element of the trajectory is a 2D gaze fixation. The model then returns a score called S, indicating whether a mistake is occurring at the current time step t. In this context, high S score indicate the occurrence of a mistake, while low S score indicate a correct action. Therefore, we can view the mistake detection problem as a classification task, where each time step t is classified as mistake if S is above a given threshold. This is our proposed architecture. The model input consists of T observed RGB frames and the 2D gaze trajectory. The first half of the trajectory, highlighted in orange, is utilized in one of the two gaze fusion strategies. Following a peak finding operation, the latter part of the trajectory is predicted. The gaze completion model takes as input the video and the first half of the input gaze trajectory, predicting a gaze trajectory aligned with the remaining part of T. The goal of this module is to predict where the user is looking in the video, conditioned on the initial trajectory. Conditioning helps reduce uncertainty in gaze prediction and provide a prior on user behavior. Our gaze completion model builds on the state-of-the-art paper in the area of Transformer, Global Local Correlation for Egocentric Gaze Estimation, incorporating a novel trajectory conditional module. This module integrates the partial input trajectory into model computation and includes an additional trajectory consistency term during training. In our analysis, we used a probabilistic approach to determine how likely is that a given ground-truth A fixation detected by the device matched the predicted heatmap. This involves evaluating the probability that the actual A fixation occur at specific coordinates within the predicted heatmap. The likelihood is calculated based on X and Y coordinates of each fixation point. By examining these coordinates within the context of the predicted heatmap, we can estimate the probability that the ground-truth fixation point match the prediction. To assess the accuracy of the entire predicted trajectory, we sum the likelihood of each point along the trajectory over a certain time frame. This cumulative score gives us an overall measure of how well the predicted heatmap corresponds to the actual trajectory of the A fixation over a specified period. This method allows us to quantitatively evaluate the performance of our predictive model in a detailed and systematic way. Here we present the result obtained for the mistake detection challenge. HoloAssist provides three distinct sets: training, validation, and test. We trained our model using only the training set and selected best model and threshold based on the performance of the validation set. The table displays the result obtained on the test set for the challenge. It's evident that the task is highly challenging, as our proposed approach tends to frequently misclassify some mistake as correct. Therefore, there is ample room for improvement. Here we present some qualitative example. On the left, we have a no-mistake example that was correctly classified. Note how the predicted gaze in blue followed the ground-truth one in green. On the right, we have a mistake that was correctly classified as mistake. Note how the predicted gaze drastically changes when a mistake occurs. Thank you for your attention. If you have any question, please reach us. For more information, please scan the QR code. Hello, everyone.
Yeah, so thank you so much for the presentations. So I believe there are the two participants in this Zoom room. So please ask maybe one or two questions for these presentations.
So any questions? So maybe in the interest of time, since we're running a little bit late, we can go to the. I mean, we can finish here, but maybe since the winners are in the room, we can take a picture of together. I think that'd be nice. And we try to fit you in the screen. Does it work? Does it work?
Sure. Like how to make the picture together like this?
Do you have a screen with all the winners in your slides?
No, not really.
So maybe, yeah, okay. So maybe I'll stay there. I'll zoom in. You cannot see, but it will work. Trust me. I'll zoom you, and maybe all the winners, if they can come to the here in front, and we take a picture.
There's some winners on the Zoom call, so you can just change the so that they can turn the cameras on.
Yeah, I wanted also to get the team, or do you think it's? I think this is gonna work. John. Okay. Okay. So I think the others are online. So let's ask them to turn their cameras on, the other winners. So we try to. Okay. And Michele should be there as well. Okay, not sure if we can get something a bit more. I think.
You can put this outside.
Yeah, I think everyone is here.
Yeah, like this.
I'm not sure we have all that control in the end. I feel like before was better.
So like a ship by sharing screen.
Let's keep this. Let's keep this as it is. And maybe, yeah. Okay, so thank you. Is there anything else, or this concludes the session, I guess?
Yeah, that's all from our side.
Okay, so thank you very much. And now the next part, the next thing that we have in the program is the poster session. So this will be in the other building, so in Arch 4E, which is 1 block away. So we should all head there and be back here for the next talk, which I think is 11:20. Okay, so let's be back here at 11:20 for the next keynote talk. See you later. Okay, hello everybody. Okay, this is like on off, but anyway, we'll start in a couple of minutes. We could not anticipate that going to the poster session would take something like 10 minutes because there's still a poster session is ending now and people are moving here because it's in another building. So we'll start in a couple of minutes. Thank you. Okay, so Diana, if we can check, we want to do an audio check. If you can, hello.
Hey, does the
Okay.
sound work?
Yeah, I think this is loud enough.
Okay, brilliant.
All right, so I think we're ready to start this session. So let's welcome Diane Larlos, who's our next keynote speaker. Unfortunately, she could not make it, so she's not here, but she will deliver a talk remotely. So Diane works at Never Labs, and she's very well known for her work on geometric understanding, and we're very excited to hear her talk. So you can start. Thank you so much.
Thank you very much for the introduction. And thanks again for the invitation. As you said, I couldn't be at CVPR in person this year. Sorry about that. But it's still my pleasure to join today and present remotely and be able to share some of the recent work that I've been involved in where we've looked at the 3D aspect of egocentric vision. So as you're all extremely aware in this room, in standard video sequences, the scene is observed from an external point of view. And for egocentric videos, they offer a first-person view, which means that they're taken from the perspective of the actor. And egocentric vision has many very concrete applications. To illustrate this, I'll refer to the excellent IGCV paper from Chiara Plizzari and many other colleagues from hers who've been working on this topic for 4 years now. And their article provides very concrete and very convincing examples of potential future applications of egocentric vision. For each, they list the relevant computer vision tasks. And what we observe is that many of the scenarios components require to reason in 3D. Additionally, I'd like to argue today that many of the other tasks would also benefit from a 3D understanding of the overall video. So that's what we are going to talk about today. Yet, egocentric videos, they are quite challenging when it comes to understanding what happens in 3D. So most of the experimental results I'll show in this presentation will be obtained on sequences from the EPIC-H1 dataset. And in this presentation, I will cover 3 pieces of work that all relate to the 3D understanding of egocentric videos. The first one will focus on objects that are moving in egocentric videos. And this is joint work with Vadim and Andrea. And we've presented this work at the 3DV conference a few years back. But first, let me clarify the task we would like to tackle here. In this work, we wanted to discover and to visualize all 3D objects that move, at least at some point, in a video sequence. And on the left, you see a short clip from the EPIC-H1 dataset. And on the right, you see the kind of output we would like to obtain. So as you can see, we have removed the background, fixed the viewpoint, and this way, we're able to visualize all the objects that are moved at least once during the sequence. The overall goal is to be able to reason about foreground objects in a way that is also consistent with the geometry of the scene. One way to frame the problem I just described in the previous slide is to say that we would like to perform foreground object segmentation. Yet, if you look at what's been done in literature, typical approaches for background abstraction, they make strong assumptions about the scene. In general, the camera is fixed and objects are well defined. And the method is typically applied to sequences like the one we just seen. Now, our work also relates to the task of motion segmentation. And here the goal is to segment moving objects from the background. Generally, the camera is either fixed or follows the object in a steady way. Now, if we look at this video sequence of an egocentric video of a person cooking, you can easily assess why none of these families of approaches can be applied in our case. Let's dive into challenges posed by egocentric videos. So for this video from EPIC-H1s, we can see that first, the person is constantly moving over the whole kitchen. So this results in a very large variety of viewpoints, and the objects are not always visible. As a second problem, we see that the actor, because it actively interacts with some objects, it occludes part of the scenes in most of the frames. And finally, this kind of videos contain many objects that rarely move. So in the keyframes that are extracted here for this slide, you can see that some of the objects have not moved for 7 minutes. They will move later in the video. So with our definition, they're considered as foreground. So they need to be segmented out. But for the first half of the video, they have not moved at all. So this gives an overview of the challenges we'll have to deal with. Now, let's forget about the task we want to solve for a second. And let's review the popular NERV family of approaches based on neural rendering. NERV has been initially proposed for synthesizing novel views. And departing from traditional approaches for this task, it does not explicitly model the geometry of a scene like voxels or meshes would do, but instead it implicitly models the geometry of a scene by means of a neural network. And for this scene, NERV would, for instance, allow to render the scene from any viewpoint, even unseen viewpoints. This neural network takes as input a 3D location and a 2D viewing direction, and it is trained to predict an emitted color and the volume density. Then, for a given ray from a particular frame, we can sample the volume at different positions along the ray. The neural network provides the color and the density at all those different samples. Then we can apply volume rendering along the ray, and this will predict the color of the corresponding pixel. Now this predicted color should correspond to the ground truth color of that pixel, and this is the information that is used for training. But NeRF has initially been designed for static scenes only. And NeRF-W is a method that came a bit later, and it's an extension of NeRF that handles unconstrained photo collections. It is designed to deal with photometric variation due to time of day or weather conditions, and also it's designed to handle moving objects and occluders. The thing is, it does not fit what we need here because it is designed to ignore transient objects, not to capture and segment them. More recent methods have been proposed since then with the exact same goal, but they are not applicable to the task we want to solve here for the exact same reason, because they are meant to ignore the foreground. So now let's go back to our problem of interest, the scene of an egocentric video. We've said that it's a bit too complex to be captured by NeRF because of all the moving pieces. But what if we start making assumptions about the different components of the scene? First, we could model the background using a fairly standard version of NeRF. Such a model would capture things that stay static during the video, such as the table, the floor, and objects that never move. Then we could try to create a second model indexed with time to capture the objects that move during the sequence. For example, here, the cutting board will move at some point, and the knife moves a lot when it is in use. And then we can model the part of the actor that is visible in the video, such as the hands and the arms. And this can be modeled separately from the objects because they have unique properties that I will discuss later. And this is how we build the proposed neural diff. It's a neural architecture that combines these three different NeRF-like models into a single representation of the scene. But each model needs to be designed carefully. For the two models that are capturing moving components, such as the second model for foreground objects, and the third model, the one for the actor, we use time as an additional input. This allows both models to render views, not only depending on the spatial location, but also the temporal dimension. And this is very important for both models because the two of them combined are supposed to capture anything that changes over the whole video. Then we model uncertainty with a score that enables both models to capture anything that is not well expressed by the static model. One way to properly separate the dynamic part into the foreground object that we are really interested in, this is the goal of the task we're trying to solve, if you remember, and the actor, is by using an inductive bias, because we know that the objects are mostly anchored to the world coordinate system. But the body of the actor is attached to their head, hopefully, and therefore move with the camera. So to capture these two different types of motion, we simply express the actor model in the camera coordinate system. And this detail actually proves crucial if you want to be able to separate the two kinds of motion. Now let's have a look at how this model works in practice. On the top left corner, you see the ground truth. Given only the viewpoint associated to each frame from the video, we see that neural diff successfully reconstructs the full video sequence. And it does this by estimating and combining the reconstruction for each of the three model components that I described just before. This component respectively corresponds to the background, the foreground, and the actor. Now, because NeRF is initially a rendering technique, it means that we can render the exact same scene, but from a fixed viewpoint. And this is the kind of results we get when we do the same rendering, but we choose the viewpoint. This allows to better observe how the different objects come and go in the video. So I've showed you the reconstruction task, but what we're really interested in this work is the task of foreground object segmentation. So let's go back to this task that we're really interested in. Our ground truth annotations for foreground objects are shown in red, on top of the left frame. And then we see the results from nerf W, the baseline introduced before, and we see that it fails to capture the plate and the actor on this example. For a model, but which doesn't have the actor component, just a background and a foreground model, we see that the entire lower body is missing. And we see that the hands are segmented, but with low confidence. Now, if we include the actor model, so all three components, we see that the full body is captured correctly with high confidence. And we see that objects are also segmented better. So this concludes the first part, where we have used a 3-stream neural renderer together with some inductive biases to segment foreground objects in egocentric video sequences. Let's move to the second part. In this second part, we will look at an approach that tries to learn representations that capture both semantic and geometric information. And this is joint work with Vadim, Iro, and Andrea. And we've presented this work at the 3DV conference 2 years ago. If we look at these recent neural rendering methods, such as neural diff that I presented in the first part, we've seen that 3D reconstruction can be cast effectively as an unsupervised learning problem. The problem is that such methods, they're typically optimized per scene. And because of this, they capture information about the appearance and the geometry, but they're not able to capture any semantic. They're not doing any semantic understanding. On the other hand, self-supervised methods, they're great at learning powerful and invariant representations from sets of images. If we take the example of a Dino descriptor, we can look at local attention maps produced by Dino, but this is typical for all these self-supervised descriptors. Typically, they correspond to coherent semantic regions. And in this work, we wanted to combine the best of both worlds. The 3D understanding that is captured by nerve-like models, but also the semantic information that is brought up by strong 2D features. And this is how we proposed neural feature fusion fields, or NEF in short, and we show that 3D reconstruction can be integrated with semantic understanding at the image level. Let's look at how we can do this integration. For this, we start with a collection of images. Then we reconstruct the 3D scene by modeling it with a neural radiance field, right? Then, for each image, we extract semantic features, such as the Dino one. And then we fuse those semantic features into the geometry of the scene using a 3D reconstruction task. But why would we need semantic features when we want to reason at the scene level in egocentric videos? Well, I'm going to give you one example. Given a patch in an input image, for example, this orange patch that you see here, then we can segment the corresponding object, not only on the input image, but also directly in 3D, as shown in this point cloud. Let's go back to the way NERF is built. We use the RGB value of a pixel in an image as ground truth color. Then we sample 3D points along a ray that corresponds to this pixel. These 3D points, they are fed into a neural network, which will produce colors and densities for each of them. Then we apply volume rendering on this ray, and this allows to render a color. The model is trained so the rendered color matches the ground truth. Let's now see how we can extend this NERF-like model. First, we can generalize rendering by also reconstructing features at not only colors. But on top of that, we formulate this task as a distillation task. The student is a neural renderer, and the teacher is the self-supervised model which produces the features. And then we train the neural renderer to also predict the features of the teachers. In our case, Dino. So the model is optimized by jointly minimizing the image and the feature reconstruction loss. Unlike typical features distillation, in this particular case, the student and the teacher work in different domains, respectively 2D and 3D. Let's look at an example application of that model. We'll forget about egocentric videos just for a little while, and we will consider static scenes. The static scene we've modeled with a vanilla nerf, and we show that we can precisely localize semantic objects from just a small input patch. Given a query patch, our model is going to predict and render the features of this patch. The features of this patch are then averaged to obtain a query feature vector. We can then compute the distance between this feature vector, this query vector, and the features of every pixel in an image. We visualize this distance maps for the feature of the baseline 2D teacher, Dino, and for those obtained with our method nerf. And we observe that the student has surpassed the teacher in that example, and features have been enriched by this 3D information that was available. Let's look at those unsupervised segmentation results in motion. The input image on the left is divided into a foreground part and a background part. Note that concurrent paper presented a similar contribution a few months later at NeurIPS, and that this idea of distilling 2D features in a 3D model has been heavily studied since then, considering all kinds of features, Dino, Dino V2, clip features, SAM as well, and different kind of 3D representations such as NERF, like here, but also the more recent Gaussian splatting. We have seen how this works for static scenes, but our formulation is generic because we can combine it with any other nerve variants. So now let's go back to our goal, that is segmenting objects in egocentric videos. Remember, we have a few challenges to deal with. We have objects that move frequently, and we know that the actor heavily occludes the scene. So how do we deal with such challenges? Well, we simply build NEF on top of the neural diff model that I presented in the first part of this talk. Neural diff can deal with all those challenges thanks to the way it models the scene with the 3 separate components that I presented before. One for the background, one for the foreground, and one for the actor. As for neural diff, time is an additional input, so the model can deal with the dynamic nature of the scene. And each component predicts its specific colors, but also features. And all these components are going to be trained jointly. So all the parts of the model are run together. This has many potential applications, and I'll illustrate just the one of scene editing. Given a query, so the query is this object that I cover in green with the mask here on the counter, we would like to localize this object in 3D thanks to the 3D representation using distances in the feature space that we've just learned. And once the object is localized, we can render the video sequence without rendering the object in each frame. As the object originally appeared at different locations for different time steps, we can assume that the background has been observed at some point in the video, which means that the frames are correctly rendered under the object, even after removal. This is because this knowledge is implicitly obtained in the radiance field that separately model the background and the foreground. To summarize, we have proposed NEF, a method for the distillation of 2D features into a 3D representation. And we've combined the approach with neural diff in order to specifically deal with egocentric videos. The last part of this presentation is quite a large effort involving many great people that I mentioned here in this slide from Oxford, Bristol, University of Michigan. And this paper has been presented at NeurIPS last year. As quite often in computer vision, datasets have fueled progress by attracting interest from researchers, but also making new tasks or new models possible. And this last piece of work builds on the large effort of Dima Dam and colleagues who built the EPIC Kitchen dataset that has allowed for this progress. So what I want to present today is the EPIC field dataset, where we have reconstructed the geometry of 671 videos from the EPIC Kitchens dataset. And we provide camera pose for almost all frames in those videos. This means that there's now 3D information for 19 million frames, covering 45 different kitchens. As you can guess, egocentric videos are not the easiest ones to reconstruct in 3D, because structure for motion methods, they often fail on such complex videos. So why exactly was this reconstruction challenging? Well, first, standard reconstruction pipelines, they often assume that the scene is static, and these methods are not robust to dynamic objects. And in these videos, we've seen that there are many dynamic objects, including hands that occlude the scene in almost all the frames. On top of that, videos are several minutes long, so that's a lot of frames to handle. We've seen that the distribution of the viewpoint is heavily uneven. because the video alternates between, on the one hand, small motion, for instance, when washing something in the sink, but also fast motions that happen in between this small portion period. For instance, when somebody is grabbing something in the fridge and then going somewhere else. So we address all these challenges by applying what I'm going to call an intelligent sampling mechanism. More precisely, we've applied this sampling to each video in order to reduce the number of frames and to balance the viewpoint distribution. We then use structure for motion to reconstruct the scene from the filter frames. And finally, we register the remaining frames to this reconstruction. Here, you can see the result of the intelligent sampling algorithm. After this sampling, the video is only composed of a subset of the frames, the ones that are most useful for reconstruction. The goal was to then sample the video while keeping enough overlap between the frames to allow for a proper reconstruction. And for this, we estimated the homography between frames by matching SIFT features. And thanks to this, we removed everything that overlapped too much. This resulted in discarding about 80% of the frames, without discarding the critical frames. By critical, I mean the ones that happen during quick transition between places. What happens if you don't use this sampling? Well, in many cases, the algorithm just fails and no geometry is estimated. When it does work, the reconstructions are not as good. For one of the examples where the reconstruction does not fail without sampling, you see that without this intelligent sampling, let's call it like this, you can reconstruct a lot less of the scene. With this sampling method, you can reconstruct a lot more of the scene. Now that I've described this data set, which is Epic Kitchens extended with this 3D information, this allows to define new tasks in egocentric videos. So among the hundreds of videos we have reconstructed, we have selected 50 videos to build a benchmark. And this benchmark is composed of 3 different tasks. The first task is the one of dynamic new view synthesis. So given a subset of video frames as input, the goal is to predict missing frames. And this benchmark task is composed in a way that it considers 3 levels of difficulty. The second task is the one of unsupervised dynamic object segmentation. The goal here is to identify which regions in each frame correspond to dynamic objects. We can distinguish the dynamic objects that the actor is currently interacting with to a second part of the dynamic part, which are the semi-static objects, which are all the other ones that are composing the foreground. The third task is the one of semi-supervised video object segmentation. Here, given the mask for one or more objects in a reference frame, the goal is to propagate these masks to subsequent frames. On this benchmark task, we've compared a few naive 2D and 3D baselines, but we hope that the community will come up with exciting new solutions for this task. Note that although we have built explicitly our benchmark on top of Epic Kitchens, our geometry estimation method can also be used on other egocentric datasets. And here are 2 reconstructions that we've obtained on the Ego40 dataset. Before concluding this talk, I'd like to encourage all Epic Kitchen users and all Epic Kitchen Challenge participants to try using the additional annotations provided by Epic Fields. And to do so, I've picked a couple of recent works that have used these 3D annotations on very similar ones for their task. So this will allow me to give you 2 more examples on top of the 3 benchmark tasks that I described in the paper where geometry is relevant. As a first example, I'd like to mention the work of Lorenzo Mulabadia and colleagues, where they automatically extract affordances from the Epic Kitchen dataset using a 3D map of the environment. This 3D map is not exactly the one released by Epic Fields, but it's similar in spirit. And this 3D information allows them to provide pixel-level precision for the affordance location. And they've released the Epic AF dataset, which adds multi-label and spatial affordance annotations to Epic Kitchens. As a second example, I'd like to mention the Out of Sight, Not Out of Mind paper from Chiara Pleseri and colleagues, where they used the 2D object mask annotations from Visor and the pipeline from Epic Fields to localize cameras in 3D. This allows them to lift those annotations in 3D and to track objects across the scene, also in 3D, even when they're out of sight. To sum up, we've released the Epic Field dataset, which enhances Epic Kitchens with 3D annotations, and a companion benchmark with 3 tasks. I really hope you'll find these annotations useful and you'll try them for some of your egocentric video understanding tasks. This is the end of the presentation. Let me just add that the people I mentioned here on the top slide are the ones who made all those contributions possible, and I'm very lucky to have worked with them. And now I'd like to take any question, if we still have time for that, of course.
So I just turned on the microphone, so you probably could not hear the applause, but people clap their hands. Are there any questions? Okay, I got a question. It's a bit technical, but I saw your results of reconstruction of some Ego4D scenes, and since part of the dataset is also paired with 3D scans of the environments, it's just I think it's a limited number of environments. Did you have a chance to check if your 3D reconstruction matches that kind of 3D scan ground truth? Maybe it's not a ground truth, but it should be accurate.
No, that's a great question. And this is one way we could have evaluated the reconstructions. But as I mentioned, we really worked on top of Epic Kitchens, and we just tried on a couple of samples of Epic on Ego4D just to show feasibility. But this is not where we did most of the study and most of the work. But it could be interesting to compare what is obtained with the reconstruction and what is predicted with these scans that are available with the dataset. I know that the Ego4D dataset has been also extended. So yeah, that's also an avenue to be considered, but not something we've done so far.
Okay. Any other question? Dima?
So yeah, inspired by all these things, how can we convince 3D people that pixel perfect 3D analysis isn't really needed? Because I don't think this is part of the problem, right? That they're really wanting nerf perfect pixel level stuff, which I think, is it really needed for video understanding, you think?
That's a very good but very tough question, right? It depends what you want to use your reconstruction for. Of course, you need the reconstruction to be precise enough if you want to start locating things in 3D and be able to track them, right? Because otherwise the reconstruction algorithms are not as resilient if you have some of these issues. But when it comes to this reconstruction, maybe something sparse would be enough for many of the tasks. And this is true that it does not directly translate into perfect new view synthesis as the NERF community or Gaussian splatting community is used to. But these tools are still useful, I think, for modeling the scene and starting querying the environment to understand what's going on. So there's a bridge to gap there for both communities to better understand what is needed in each side. But I think your question is really smart, and I don't have a better answer than that.
Other question? Okay, so let's thank Diane again, and
thank you very much.
So thank you so much, and then we go to the next session, which is the Epic Kitchens challenges session. I guess you're going to keep using this. Okay, that's great.
Okay, no worries.
The mic.
It's not working. It said stop working now.
The talk's going to share the slides.
our slides. Okay, awesome. So today, Jacob and I will be talking about how the last year was for the Epic Kitchen challenges. So to begin with, if people still don't know what Epic Kitchens is, so Epic Kitchens is an egocentric data set of 100 hours of egocentric videos, where we have 20K unique narrations and 90K action segments, along with 20 million frames. Then we have the Epic Trilogy. In Epic Trilogy, we have Visor, which was very well explained by Diane right now, so I'll skip over it. Then we have Epic Sounds, where what we have done is we have just given audio to the annotators and annotated what it sounds like. So we have audio annotations for the actions that are happening. Then we have Epic Fields, which was done here. So we have 2D, we have converted 2D video to the 3D scene, and we have accurate 3D mapping of where the kitchen is, how the things look like. And now a quick flashback of how the Epic Kitchens challenges have turned out in the past years. So the first round we had was in CVPR 2019 Long Beach. We see all the happy faces here of people who were winners in the challenges. Then in 2020, we unfortunately went virtual, but still we were able to have winners in the challenges there. And these are the people that we have. For 2021, we have multiple winners. We have winners in 5 challenges. And these are the people that were winner in 2021. Then in 2022, we came to New Orleans. We have multiple challenges. We have challenges from 6 winners here. And we have multiple people who we can see virtually as well as in person. And then in 2023, last year, we met in Vancouver. We have around 7 challenges where people were winners. And now we will talk about the challenges that we had this year. So we had 9 ongoing challenges, out of which 3 didn't receive any valid responses. The rest have valid responses. And then we have 1 new challenge, which Jacob will introduce to us now.
So yeah, the challenge this year, audio-based interaction detection. So for those who aren't familiar, if you're given an untrimmed audio in Epic Sounds, the goal of this challenge is to detect the action boundaries or the sound boundaries and classify all of the proposed regions as well. So if you're familiar with visual action detection, this is like the audio counterpart. So for those who aren't familiar or might not remember from last year, we had the Epic Sounds training splits, which matched the Epic Kitchens ones. And we also then went a bit further and divided the test set into 2 challenge-specific subsets. So last year, we had the recognition subset where we released the available timestamps for the actions, but not the labels. And then we also withheld sort of a half detection test split as well, which we didn't release any information on. So there's no timestamps. There's also no labels. You're just given the video IDs of what we'd like you to evaluate on. So why is audio-based interaction detection challenging? So in Epic Sounds, we have 78,366 categorized annotations from over 100 hours of audio, spanning 44 different classes with unique sound signatures. And then all of these classes are also variable length. They're potentially overlapping with an average length of 4.9 seconds. So we're expecting your methods to be able to distinguish between all these sounds, sort of distinguish between the overlaps and know what all of those sounds are. So it's quite a difficult challenge. So as this was the debut year for the audio-based challenge, we're just going to have a look at some of the numbers and what we got. So we had 27 submissions from 9 different users. And then from the baseline that we released to the top 1 method, we have an improvement of 7.47 MAP over the baseline this year. So if any of you are interested in this challenge, then you're welcome to participate next year and see if we can push these numbers even higher. So congratulations to the team who placed first for that as well. So going on now, we will present the awards and the certificates, and as well, we have a select few methods to present their work. So we'll start with the virtual rewards. So first of all, congratulations to the team at Deep Glint, who placed 2nd in the action recognition track, as well as the action detection track. Then we have the team from the Department of Electrical and Electronic Engineering at the Hong Kong Polytechnic University, who placed 1st in the multi-instance retrieval track. Congratulations to the Intelligence Perception and Image Understanding Lab at Gideon University for their 3rd place award in the multi-instance retrieval track as well.
And then congratulations to the School of Artificial Intelligence at Gideon University, who placed first in the semi-supervised video object segmentation track. And then congratulations again to Gideon University for their second placed award in the semi-supervised video object segmentation track. Then congratulations to the third place team in the semi-supervised video object segmentation track for the Intelligent Perception and Computing International Joint Research Center at Gideon University. For the first place award for the School of Artificial Intelligence at Gideon University for the audio-based interaction recognition track. And the third place award for the audio-based interaction recognition track from the Intelligent Perception and Image Understanding Lab at Gideon University. And congratulations to the third place award of the School of Artificial Intelligence at Gideon University for the audio-based interaction detection track. And now we'll go to the in-person certificates. So for this, we'd like to ask the teams to come up and collect their awards from Sidan. And then if they could wait at the side as well, and we'll take photos after all the teams have been called up. So to start with, congratulations to the team at the King Abdullah University of Science and Technology, or KAUST, for their first place awards in the action recognition track, the action detection track, and the audio-based detection track. And congratulations to the team at the University of Oxford and the University of Bristol and Czech Technical University in Prague for their second place award in the audio-based interaction recognition track, audio-based interaction detection track, and action detection track in third place as well. And then our final in-person award, we have the first place domain adaptation for action recognition track from Shanghai AI Laboratory, as well as second place multi-instance retrieval and third place action recognition. Okay, so now we have our invited speakers for the challenges as well. So this will be a 7-minute talk with a 3-minute Q&A at the end. And we'd first like to begin with the team from KAUST for their rank 1 action detection, sound detection, and action recognition method.
Can you please connect to your PC? Have you joined over Zoom?
Join over Zoom or?
So that you can share your screen there. Do you have the link?
No, I don't have the link. But I can.
So let's direct it through the speaker so when they come.
Okay, so what's the Zoom link?
Share.
Okay, sorry for that. So sorry for that. So another issue is that since we train the model, the verb, task, and non-task separately, we then need to construct the action labels. So we select the top 10 noun classes and top 10 verb classes for each time step, and then we calculate their product to view the action probability and classes. Actually, when we're evaluating the action labels on the noun and verb task, we observe a 3 to 5% performance drop. So this reflects that there is conflicts between the noun task and verb tasks. Maybe joint training will help it, but we didn't have enough time to explore. So in the end, we surpassed our last year's submission by a very large margin from 22.52 to 31.97. This builds a solid baseline for future works. And also, our strong results does not only come from the innovative detection methods, but also come from a very good detection code base we use. Actually, we use the OpenTAD. This is a recently released large-scale TAD code base and supports over 40 methods and 9 TAD datasets. So it's very easy to migrate to a new dataset and can achieve stronger performance. So therefore, we use this code base to build our method also on this newly released audio-based interaction detection dataset. And thanks to the organizer, they have already provided a very good feature, which is auditory slow fast. And we use this auditory slow fast with our code base and our method. We boost the baseline from 7.35% to 14.82%. So this will also set a solid baseline for future works. We also noticed that in this task, the audio feature is much more important than the visual features. Although we extract inter-video 2 features, which is very strong, but it performs much worse than a simple auditory slow fast. So apart from the pre-extracted features, we also want to introduce our CVPR work that is doing end-to-end learning. So all the TAD experiments, long-form video understanding experiments, they work on the pre-extract features. However, in this recent work, we managed to perform end-to-end training with 1 billion parameters over 1,000 frames. So we find that actually by doing end-to-end training, the performance can be greatly improved. So we can surpass the best features by a large margin, and on some data sets, we can even double the performance, the average ME performance. So that is very important, means end-to-end training. And also, even this backbone is already fine-tuned on the short video clips, let's say applications, we still can find that performance gains by doing end-to-end training on long-form video understanding. This also indicates that the upstream recognition task is not very consistent to the downstream detection task, and maybe end-to-end training on the downstream task can further help the performance. So our code base and technical report will be released in our code base. And if you have any questions, you can ask or communicate with me. Our poster is hosted in June 20th in the afternoon. So if you have time, please have a look. Thank you so much.
So we have a few minutes for questions. Are there any questions? Yes.
Congratulations on the award.
Thank
I
you.
was wondering if you tried the audio recognition task.
We don't have enough time. Sorry.
So
Yeah.
it's just time. It's not like you tried it and it didn't work.
Yeah.
Okay. And or the anticipation task, is that something you've looked into at all?
We didn't also have. Yeah, we didn't work on that. Sorry. Yeah. Yes, please. And that's a very good question. That actually Mamba was recently just introduced, and there is a paper called Video Mamba Suite. They explore the Mamba architecture in the long form video understanding, because Mamba suits the long form sequence modeling, and it basically proves that vanilla Mamba or Vision Mamba if you apply it on the feature temporal long on the pre-extracted feature, it has really similar performance to the standard self-attention or others. But if you share parameters in the SSM, they can have larger improvements. I think the Mamba, the strong performance of Mamba comes from the one, they have good architectures, and also they need less hyperparameters to tune, and also they don't very large data to fine tune to learn the inductive bias. I think from the perspective data efficiency, Mamba has more advantage. Yeah.
One last question.
Is that inflation for the hybrid network?
Yeah.
Was that control for the number of parameters? So what I mean is, in the equation you showed that this hybrid network is better in terms of performance. But is it better because of the architecture, or better because you just move parameters?
Yeah, that's a good question. Actually, we find that even actually, for example, basically Mamba has the half parameter of the hybrid causal block. But we also apply if you increase the hyperparameter of Mamba to the same amount, you can have worse performance. So each row is the best performance we tuned. Yeah.
Let's thank our speaker once again. Thank you for.
Thank you.
Okay, so now the team from Fudan University for their first round.
Let's give the first listens about the 14 challenges. Application is later.
This is the presenter view. Can you please use the slideshow?
Where's the
Let me see. Did it go? Here it is. Use slideshow. Is it okay now? Awesome. Sorry. Okay, so you can start whenever.
this one?
Hello. This is not. Sorry, we are not speaking it aloud. Yeah,
Yes.
they're trying to solve.
Okay.
Thank you.
Thanks for the introduction. My name is Lan from Fudan University, and today I'd like to introduce our solution to the application challenge. Okay, so this is a collaborative work with Yifei, Baoqi, Guochen, and other teachers from Shanghai Laboratory. Okay, so our general idea is to design a very powerful egocentric video language model, which we call EgoVideo, to solve a series of tasks. And this is achieved via progressive training. We will just introduce this progressive training strategy. So here, this is the first way to do video language pre-training as, sorry. Can I slide this? Okay. So the first stage, we do video language pre-training in general domain, which is also the intern video 2 model. And I'll dig a little bit detail into this model. So it contains 3 steps, and I just show step 1 and step 2 here because we didn't use the model for step 3. So in terms of step 1, it is about distillation training from image experts. As you can see, we train a video encoder and with mask modeling, and the feature representation we distilled is from an image expert, for example, intern VL. And also you can do the feature-wise L2 similarity here. So this is about distilling the rich knowledge from the image expert to serve as an initialization of the video encoder. So this is about step 1. And step 2, we do the multimodal contrastive learning. So we have a video encoder, then we have a BERT large model as a text encoder and an audio encoder. So we have these 3 modalities data, and we can do the contrastive loss like between video and text, and video and audio and text, something like this. So this is about multimodal contrastive learning. So in the first stage, the data we use is a combination of multiple action recognition datasets, including Connect 400 and 600, 700, and ActiveNet, etc. And then we only use the videos and discard their action labels, because what we do is distillation training. We don't use their action labels. Okay, so for the second step, we use a hybrid combination of image tags and video tags datasets, including Lion and WebVid and InternVid and so on. Okay, so this is about for training on a general domain. So the second stage, we do the post-training on egocentric domains, because we need to shift the domain from general to egocentric, so as we can tackle the egocentric videos in the applications, right? So here we choose a lot of egocentric datasets like Ego4D and a subset of egocentric videos from how to 100 million, because for instructional videos, some clips, they're also egocentric, but most of them are exocentric. And we choose some of them to merge into the entire egocentric video datasets, and also some videos that are generated by algorithms from recent works like Video Recap and Lavila. Okay, so we have this very large amount of egocentric tags and pairs, videos and text pairs, and we can fine-tune our text encoder and video encoder on this data set. So the experience here is more frames. For example, 16 frames are always better than 4 frames, but also it takes longer time to train a model. Okay, so also more egocentric data leads to better generalization performance. Okay, so in terms of stage 3, we fine-tune this the model we have from stage 2 on different tasks like action recognition and domain adaptation and multi-instance retrieval. For that domain adaptation, we only fine-tune the model on the source domains because we don't have access to the target domain, the label in target domain. So as you can see, for action recognition and domain adaptation, we just use the cross-entropy loss. And for multi-instance retrieval, it's very similar to the contrastive learning. So we just fine-tune like the stage 2. Okay. As you can see, our model achieves better performance than the previous model, Lavila and Avian, which are both developed by Yue Zhao from UT Austin, which were also very good works. And also for domain adaptation, I think because we collected a very large data from Ego4D and because this covers a wide range of activities. So I think it is
Suddenly worked. Sorry.
okay. Okay, so I think this model is better at domain adaptation here.
So I think we can now.
Okay, so I think this model now is better at domain adaptation because the data can cover more domains here. Okay, so for multi-instance retrieval, our model also achieved very good results. And also for zero shot and fine tune. Yeah, and here are two experiences. For the first one is video language pre-training on web scale image or video text pairs learns very general good features. And the second one is our post-training on a collection of egocentric videos also demonstrate very good transferability. Okay, so to conclude this work, our work use EgoVideo, a very strong video language model with progressive training strategy to solve a series of action understanding tasks on application. And it's a bit pity because we didn't try other tasks like Professor had mentioned. And we think we will try in the future. Okay, so the code is also available from here, which will update it soon. Okay. Thank you.
So any questions for it?
The presentation, thank you very much. So you don't do any adaptation of the target domains. So it's purely a generalization model.
Yeah, so our focus is about creating a very large scale egocentric data to try to cover the,
No longer need to do adaptation. We're going to be able to solve, because adaptation is about collecting unsupervised, like unlabeled data in the new domain you want to adapt to.
yeah, I think it depends. For example, if the source domain and target domain, they have very large gap, I think there's still a very large work to be done to design, very good model to solve this problem. But if you think, if the domain is not that, perhaps nowadays the vision foundation models, they can also cover this domain. So perhaps it is not very technical thing. I mean,
Training set this Ego how to subset that you train.
we've been trying to refining it nowadays, and to be honest, we annotated some of them because nowadays there are no publicly available Ego Axel classifier from the best of my knowledge. And we've been trying to solve this problem. It's even though it sounds really easy, but in practice, when you do this, you face a lot of problems. For example, how do you define ego? And there are a lot of ego-like videos in how to. It's photos that only contain hands, but it's not recorded by in first-person view. So we've been trying to, how to design this, and we're working to improve this data. Okay, thank you.
Thank you so much. Any other question? Okay, then we would like to thank our speaker. Thank you. Let me just read and read. Thank you so much.
It's now Oxford and Bristol for their second place ranking in sound recognition, sound detection.
You'd like to change your device from click here. Check. So yes, click here. And then select yes. So we see your presenter view on the room, so you make sure. Oh, HTML. It's not great. Do you have a photo? Awesome.
Hello, my name is Jason Hall, and I'd like to have a presentation of a presentation title is TIM, a time interval machine for audio-visual action recognition. My name is Jason Hall, and this is a joint work with Jacob, Vangelis, Andrew, and Dima. Oh, and this gives us sample. This shows a sample clip of the epic kitchens, and then, as you know, epic kitchens have the distinct annotations in the visual and audio with the both temporally and semantically. And but the question is like how to use these annotations. So the current approach in this action recognition is that we have this like a start time interval with start time and end time we're interested in, and we want to recognize the action. So the current recognition approach is that we have a visual, we crop the video and a corresponding audio, and we somehow use this, put this two modalities to the model and then recognize the action. But actually context helps. Like if you look at this example, this person is like wash potato and then they take the knife and they start cutting the potato. If you know what's happening after this, like wash tomato, and then like cutting tomato, it's really helpful to recognize the current action, which is wash tomato. And there are actually current approaches which uses the neighboring clips to recognize the current action. However, there's not always we have this like certain like start and end time of this neighboring clips to recognize the current action. What we usually have is the kind of untrimmed video, and we only have the certain like timestamp of the start and end time, and then we want to recognize the action. So current approaches don't use this like untrimmed video quite well to recognize, to use the context and then to recognize the action. So therefore, we're kind of interested in TIM, which is the acronym of time interval machine. So if we have this untrimmed video and then the corresponding audio, and then we want to say that like for the rest of the slides, we use the blue as a video and then red as audio. And if we have a start and end time you're interested in, and then we also have like a modality, so we can have a question that what's happening between the start and end time in the visual side, or what's happening between start and end time in the audio side. If we have this start and end time, we create this encoded query with a tagging with the modality, and then put this to our model called time interval machine, along with this untrimmed video with a video and audio. And this time interval machine is a transformer encoder, and then get the visual action or auditory action. The idea is quite simple. So it's like if we have an untrimmed video, we want to know what's happening between 3 seconds to 5 seconds in the visual modality. We take this at 3 and 5 number, and then create the encoded query, and then put this query to our model, and it gets the corresponding action. We can do this in the different modality. We can do this in the audio modality. Say we want to figure out what's happening between 0 to 5 seconds in the audio modality. We simply took this like two numbers, 0 and 5, and make a query, and then ask Tim what's happening between here, and then we take this, get this corresponding action. Can do this, and then also the cool thing about our model is that we can really simply deal with the overlapping action. So if we want to know what's happening in the audio between 11 to 14 seconds, also between 13 to 19 seconds, we simply just take this like two numbers and then ask Tim what's happening between them, and then we get corresponding action. So I'm going to present the full picture of this Tim. If we have an untrimmed video and the corresponding audio, we have this free visual encoder, a video encoder, and a corresponding audio encoder. And then we put this to the GV and GA, which is just a simple linear layer. And then we get this visual features and then audio features. We have to note that these visual features and audio features like cover a certain time interval. And then we have visual time query and audio time query. So we have a question of like what's happening between 0 to 4 seconds, or what's happening audio between 1 to 3 seconds. We simply put these numbers to the time MLP, in time interval MLP, and then get this like feature which encodes this 0 to 4 or this time interval. And then we put this query with a classification CLS token. And then we also, I just said it, but like there's a features also covers certain kind of timestamp. So we need to have a concept called feature time interval. So we put also these time interval to the time interval MLP, and then get the features, and then tag this to the corresponding video features and audio features. And of course, we also introduce this learnable modality token. So we put the learnable video token to the visual modality features, and then learnable audio token to the audio features. We put all together to the audio visual transformer. And then from the corresponding CLS token, we have the classification head, and then we get the corresponding action, both in visual side or audio side. And this also shows how this like time interval NLP, but it's really easy. It's like we have this feature time intervals and also the query time intervals, which is like two numbers, start and end time. You put this two number to this MLP, which is a 3-layer 3 linear layer and a ReLU in between. And then we have this corresponding feature time encoding and then query time encoding. And then we put this feature time encoding to tap this to the features. And then query time encoding is used as like a query or question to the model that what's happening between these time interval. So this is like a approach for recognition, but we have to adapt TIM for detection. So we introduced 2 different methods. One is regression head. So for regression head, we have this like a CS token, and then also the query time encoding, and then the finality token. Instead of using only the CS head, we also introduced a regression head, which is like regresses the action, the time interval when the action is happening. So if this is, we query as a 0 to 4 second, it regresses to the nearest time interval where action is happening. And also we construct this query pyramid, which is has like have a covers it from the short time to the long time. And we put this all to the TIM and then get the corresponding like actions and also this like intervals. But during training, we assume that the queries, which has a IOU with the ground truth is more than 0.6 second, we deem as a positive query, but the rest of them are like negative query. And we use only these green ones for our detection. And so these are results. We had a 4th place in the action recognition and then 3rd place in the action detection. We want to emphasize that like we use only the public data set, and then we also didn't use any like self-supervised training method. And also we got 2nd places in sound recognition, sound detection check. This is a regular paper. We released the code. And then if you want to take a look, please come to the Thursday PM session.
Thank you so much, Jason. Are there any questions for Jason? Okay, so then we'll continue with the session with our 4th and final virtual talk.
Okay, can you hear me now and see my slide?
So your slide is not full screen. If you can please go into the presentation mode.
So I can start now.
Yes, you can start.
Okay. Hello everyone, I'm Wang Xiaoqi, and we are very excited to be here to present our solution for the multi-instance retrieval challenge. Specifically, we propose a novel loss function called symmetric multi-instance loss, which offers a more precise learning objective for this challenge. First, we come to the previous training framework. Sorry, second. In this training framework, we have the video input and the corresponding narrations. So we also have the pairwise hard labels. After calculating the similarity matrix, and we need a loss to constrain the similarity matrix and the hard labels. So the most common loss here is the max margin loss, of which the learning objective is SP minus SN larger than gamma. The SP and SN are the similarity between the positive and negative pairs respectively, and the gamma is the margin. However, this challenge differs from the classical visual text retrieval tasks by providing a relevancy matrix that can act as a set of soft labels for video text pairs. So in 2022, the EgoVLP proposed a new training framework. Here we still have the video clips, but we no longer use the corresponding narrations. Instead, we find all the narrations at where the relevancy value is larger than 0.1. So we search all the relevancy metrics and get all the hard sample candidates of this corresponding video. And we random select one, for example, the open fridge, and add it to the soft label matrix as well as the similarity matrix. So the CP, or the relevancy value for positive pair here, could be any value between 0 to 1. So for example, it could be 0.7, 0.5, and so on. So with this training framework, we can easily transfer the max margin loss to adaptive max margin loss. So here the margin in the max margin loss is the gamma, and in the adaptive max margin loss is the Cij multiplied by gamma. So it can also regard it as Cp by gamma. The Cp is the relevancy value between the positive pairs. However, it will raise a problem. The problem is the soft label matrix will not look like this, but instead the actual soft labels will look like this. The CIK, or the relevancy values between the negative pairs, will not always equal to 0. And in the bottom of this slide shows the actual implementation of this loss function. So consider a special case where the relevancy value of negative pairs is even higher than the positive pairs. That's set it to see the negative pair is more positive than the positive pair. So in this special case, the AMM loss will optimize the model to the exact opposite direction. So how to solve this problem? We ask 3 questions here. The first one is the relevancy value for the negative pairs, the Cn, is not always 0. We have a very simple solution. We modify the margin from Cp by gamma to Cp minus Cn by gamma. But there will raise another problem. As aforementioned, the relevancy value for the negative pairs would be even higher than that for positive pairs. So the Cp minus Cn is less than 0. And in this situation, we switch the position of the positive and negative pairs. That is to say, the positive pair is now the negative pair, and the negative pair is now the positive pair. So you can see that our loss function become 2 parts. One part is for R is larger than 0, and the other part is for R is less than 0. And how about R equal to 0? We set a relaxation factor here. So since the Euclidean distance between the positive and negative pair is less than gamma when R equals to 0, we will not optimize it. Otherwise, it would become the dominant loss. So here gives the complete form of our symmetric multi-similarity loss here. And together with the flip and add trick, it's a very simple trick. We just flip the video frames during inference and add them together. And the ensemble strategy, we train 6 different models and calculate the mean value of the similarity matrix. And with all these solutions, we get the best performance. Compared to the previous SOTA in 2023, we improved the performance by 5.34 on average MAP and 3.49 on average NDCG. And compared to the AMM loss, our loss improves the VIT large model by 2.3% on average MAP and 2.8% on average NDCG. And our code is now available on GitHub, and we will release more fascinating things on this repository. Thank you for your attention.
Thank you so much for the talk. Thank you so much for the talk. Do we have any questions?
think so.
Okay. Okay, so thank you. So this concludes our Epic Kitchen Challenges session. Now we will meet at 1:40 after lunch for the EgoVis Awards. So let's see who won the awards and let's have fun then. See you later.
Yeah, I realized I only did the coach.
We'll wait a few minutes. We're definitely waiting for our photographer. So we're not starting before he is here. Right. Welcome back. Thanks to the speakers and the session chairs for an excellent morning session. We're starting the afternoon 2 sessions, which, as the program states, the first one will involve 3 things: the EgoVis Distinguished Paper Awards, which I'll tell you a little bit more about. I know many of you are here for that specifically. Then we have the combined keynote from Michael Frank and Bria, which will be introduced by Tushar. And then we have the area challenges and data sets before the next coffee break. Right. What is this new adventure? We thought about looking back a little bit. It's not a lot, but a little bit, at papers that have transformed the field in 2022, 2023. So these are peer-reviewed papers at conferences or journals that were accepted between January 2022 and December 2023. And we're looking for original and innovative contributions to this field, the field of egocentric vision. And particularly, we're interested in papers that offered contributions beyond just writing in the paper in the form of code, models, and data. And indeed, this had been a major factor in the impact these papers had had on the field. So this was an invitation for people to nominate their papers. Each paper was submitted along with a prologue that describes why by the authors. So it's a self-nominated prologue on why this paper should be deserving of the award. It also had the list of reviews that the paper had been accepted based on. We received, I think online we do say we did receive around 30 submissions that all were deserving and passed all the setup here. And papers have been selected based on either being chosen by more than 50% of the board that voted for the awards, the non-conflicted board, or at least three out of 7 people. So it's a combination of either. And the award will be given in alphabetical order. So there is no particular order of these awards. I'm giving them completely alphabetically. Each set of winners will be given a 2-minute speech. It was labeled as Oscars without the tears. So no tears will be allowed, but they're supposed to reflect on how the data was collected, how the impact was achieved. So we'll be going through the next 20 minutes will be the award deserving awardees as long as their 2-minute wisdom speeches. Okay, and this is my brilliant arts and crafts project with the certificates, which will help Antonino kindly agreed to take the photos. So this is the person you should be smiling for the photo of. And again, in no particular order, the first distinguished paper award in our first round of EgoVis awards goes to Assembly 101, a large-scale multi-view video dataset for understanding procedural activities.
Thank you very much for the word, Tima. So Assembly 101 was a collaboration between Meta and Angela Yao's team at National University of Singapore. And we both had different interests. So Meta's team wanted to have a new data set, egocentric data set, captured with Quest 2, and capturing hand-object interactions. And our motivation, we were working on procedural activity understanding. Our motivation was having a new data set that's not from the kitchen domain, and that also has egocentric recordings. So we started this project during COVID time. We recorded this data set, I think, through like 3 different time zones. I was back then in Germany, and Angela's team was in Singapore, and the other Meta team was in the US. It was, not very easy, but at the end we managed to finish the data collection, annotation, and everything. And Assembly 101, afterwards, like after the publication, got interest in many parts. Procedural activity recognition, it's been used. And they later also published a work on called Assembly Hands, where we try to provide ground truth for this kind of interactions. And recently, I also see more and more papers about mistake detection in procedural activities. This was also introduced in this paper. So for me personally, Assembly 101 is also very important because after this project, I got a job at this group at Meta, and we started a new team for action recognition. And right now I'm actually doing online action recognition, developing models for smart glasses for online action recognition. And my first data set, the first data set I used for this project was Assembly 101. Yeah, I think that's all. Thank you very much.
The second paper, again in no particular order, these are alphabetical, goes to ego body pose estimation via ego head pose estimation.
Okay, thank you for the amazing award. I'm very excited and honored to be here today. So our journey starts with the goal of estimating full body human motion in a more accessible setting using egocentric radios, which requires minimal sensors. And the most challenging part for this problem is a lack of large-scale paired data sets with both egocentric radio and full body motion. So capturing such a data set is not very practical since motion capture usually requires specific hardware. So in our project, the key is to use head pose as intermediate representation so that we don't rely on such paired data set with both egocentric radio and full body human motion. And another critical component is a conditional diffusion model. And I think the diffusion model really advanced a lot of research fields, including ours, which enables us to generate highly diverse and very dynamic human motions from head poses. And I think our paper opens some new exciting opportunities. For example, maybe we can integrate more video-derived data with EgoEgo to further improve the motion estimation performance. And the second, I'm excited to see whether we can use this approach to extract motion from egocentric radio and use the extracted motions to further improve the human behavior analysis to infer human actions and intentions. And finally, I'd like to thank my advisors for their support and positive feedback during the research project. And their encouragement gave me the confidence to address the challenging task because at the beginning, I really don't believe this will work. I also want to thank the authors of previous work and for fruitful discussions about the egocentric pose estimation topic. And these discussions really deepened my understanding of egocentric pose estimation. And thanks again for the award. And we are very excited to continue pushing the boundaries in egocentric vision. Thank you.
Great. The next is Ego 4D, around the world in 3,000 hours of egocentric video.
Hi, everyone. Thank you so much on behalf of all the 84 authors of this paper for this recognition, which is really awesome. So if you don't know about Ego 4D, in a few words about the motivation, the aim was to collect everyday unscripted activity in as many places as possible and as natural settings as possible. And at the end of the day, this meant about 3,600 plus hours of such content from almost 1,000 different individuals in 74 cities around the world. And the team behind this came from 14 different institutions, as I said, 84 authors, and it really brought together PhD students, faculty, researchers, engineers from Meta as well. And this was a process. So thinking of journey, it was about a 2-year effort that started brewing within 2019 towards the end of maybe summer, fall, and then launched this data set for the first time in 2021. So I was reflecting back on what were some of the challenges along the way to get to this output. One, we were dealing collectively with a very large group of scientific collaborators with lots of ideas, lots of energy, and also lots of logistics, which included engaging with these 900 plus camera wearers or participants. We had challenges and interest in ensuring privacy and ethics standards so that this would protect the subjects involved, but also ensure that for the research community, it's a kind of full-fledged resource that we can really rely on and continue to use. And then, heard it in Assembly 101 too, there was COVID along the way. So if you notice that 2-year span, now we had people in the wild doing unscripted activities also during COVID lockdowns and trying to capture that. So for me personally, this effort has really been a highlight in my career so far. Why? The willingness of these world experts in video to come together to do this long-term focused effort. And two, it's just been so thrilling to see the growth and participation on these challenges. Baseline's getting better and better. As you'll see later today, now the 4th instance of the challenge, and I think it's something like 85 teams who are participating now. And also to see the adoption by sister communities like robotics, language, bringing new ideas that didn't exist at the start of this effort, but now can be enabled in new ways. So finally, big thanks to everyone who created Ego4D, some of whom are here in the room. And thanks again for this recognition.
Great. We have 3 out of 3 female representatives. I like this. The trend is good. We're making some balance. Great. The 4th award goes to Egocentric Video Language Pre-Training.
So thank you very much. Since Kevin is absent from the CVPR conference due to his personal issue, so I want to say hello, I'm Stan. I'm not working in this area, and today he sent me the note to deliver the speech on behalf of him. So I'm very proud that EgoVLP has made it to the distinguished paper list at EgoVis along such amazing works. So EgoVLP is my first research project during my PhD. And when Professor Mike introduced the dataset Ego4D to me, I was super excited and dive into exploring the massive egocentric videos. I have spent a lot of time to explore the egocentric videos, and I'd like to talk about how it came to be. So at first, I found that they didn't really help with the third-person tasks such as MSRVTT, and this made me constantly think about what kind of task Ego4D could help with. But then I tried it with egocentric videos such as Epic Kitchens by chance, and it showed significant improvements. And this made me believe in the importance of egocentric video pre-training. And I'm very glad to see that EgoVLP is now receiving the community's attention, and its model and findings are making a difference to the egocentric community. And finally, I'd like to thank my collaborators, including Alex, Mattia, Michael, Bernard, Dima, Liu Wei, and Mike, and many others. Thank you very much.
Next is EgoHumans, an egocentric 3D multi-human benchmark.
Right. I'll prepare this. I have to hang on a lot of stuff. Some of them are in the room, Min, Lingni, Ayush, Chris, Richard. This was my first dataset project and also the hardest project I worked during my PhD. It took us 8 months to collect the data and about 1 month to get the methods to work. But it was a learning experience going all the way from cameras to having a model which works on your particular set of data. And there were questions which I would not even imagine you have to worry about when you're working in a dataset project. Like, how many memory cards are they prepared for tomorrow? what batteries, how many charges do we have? Trying to make sure that GoPros don't heat up in Seattle summer. That was a big issue we run into, but I think this was the biggest learning experience, and now it's a whole thing on its own. There are spin-off data sets, and the code is being used to support more data sets in the future, but really appreciate. Thank you so much for the offer.
Excellent. And the next distinguished paper award goes to EgoVLP v2, Egocentric Video Language Pre-Training with Fusion in the Backbone.
Thanks so much for giving the award to EgoVLP v2. This was my first internship during PhD. I was in Meta during the summer of 2022, and I started the work with the aim to build good summarization systems for long-form egocentric videos. But then we saw that for building summarization systems, as the summarization dataset at that time was very small scale, we needed very good pre-trained weights. And from there, I started to look into Ego4D, the previous papers like EgoVLP and Lavilla. And from there, we built the pre-training system. So the whole thing took almost 8 to 9 months to work to complete the pre-training, then to transfer the pre-trained weights to multiple tasks and benchmarks. But the overall experience, like it was a like multi-institute collaborative effort, and I learned a lot. And I think this was the first big scale project in my PhD. So I would like to thank all my collaborators. I think some of them is already here, EL and Peng Chuang, and my advisor for supporting.
Next, Epic Sounds, a large-scale data set of actions that sound.
Thank you very much for the award. So kind of before Epic Sounds, everyone kind of knew audio and visual have very strong correlations, but there's a bit of too strong of an assumption because people kind of assume this was perfectly aligned. But when we kind of thought about it, there was a few issues. We use different semantics to describe sound, and sometimes we use different timestamps to describe actions for the same thing in visuals. So this is kind of where Epic Sounds was born. And yeah, we went through a year's worth of work, annotating 100 hours worth of audio, equally as many hours typo correcting and listening to sounds that are really indistinguishable. You'd be surprised that an egg sounds like a ceramic bowl when you're just listening to it through headphones. And yeah, it was a really big effort from all of us. So thanks to our co-authors, Vangelis and Andrew, who aren't here as well. Thank you to Raja and his team for helping us collect all the annotations and sort of getting all those temporal timestamps for us to go through. And yeah, thank you to the audio community as well, the Egocentric community, for really responding well to the data set and sort of taking up through the challenges and giving us a lot of feedback and helping us to understand the data even more. Anything? Yeah. and yeah, thank you very much.
Next, HoloAssist, an egocentric human interaction dataset for interaction AI assistance in the real world.
So I'm actually covering in for Shin, who was the first author. She couldn't make it today. And I think Dane is on call here. But HoloAssist has been a labor of love for all of us involved. When we started like 2.5 years ago, there were very few truly multimodal data sets out there for long form video understanding. And, we were all working with the HoloLens and we realized that there was a lot of other inputs that we could use beyond vision and language to really inference on tasks related to long form videos. So we started from there, and then the second idea that we had was to actually have sort of this interactive agent that that can look at what we see and basically help us along the way for step-by-step guidance or sort of this open-ended questions of the task around the task. So you know, if you look at the data set, we have both action recognition, but also other kinds of novel metrics around mistake detection, intervention prediction, and so on, which actually try to model the user intent beyond just the task at hand. So there's already a lot of engagement from the community. Thank you. We love that excitement goes on. And a huge shout out to everybody involved in Microsoft Research, Neil Joshi and his team, and also in Microsoft Mixed Reality, Mark Boniface and all of us involved. Thank you.
Two more. Next, learning video representations from large language models.
Hi everyone. It's very happy to be here to win this award, and then thank the committee for selecting La Villa as one of the outstanding awards. This project was done during my internship at Meta, and then it was mentored by my two amazing mentors, Ishan and Rohit, who really helped me a lot during the project. Because I think I actually had a lot of like back and forth kind of things during the project development. So basically the project was trying to learn a very good video representation from large scale video. And then like before we mostly like have these kind of like single label video data set. And then we realized like it is very impossible to scale to like even large scale, because we know like these video or like action particularly, they have a very complex combination of these nouns, verbs, and then even more complex like kind of descriptions. And then we realized that natural language might be a way to go. And then it's very fortunate to have Ego4D dataset. We actually have very nice kind of natural description, like curated by the entire community, like 3,000 of videos with the kind of human annotated like natural language description. So it serves as our starting point. And then we also figure out that we can actually leverage the large language model to help us create even more captions. Which actually we find that it is very, it's becoming more and more popular in recent kind of computer vision community actually. So we have these caption model like actually moves beyond these kind of egocentric videos, but also like for these like more generic kind of video community. So it's very nice to see the impact of the La Villa. So we actually have like over 400 stars on GitHub. And then I heard that like the model itself is also like used in some internal kind of product things, but no more details. Yeah. So, and then after this project, I'm still working on like kind of building more scalable and then more foundational kind of video language models. And we also figure out some more efficient way to train La Villa. So if anyone is in the community, like academia, and don't have these kind of 4 or even more like GPU clusters, we also have a kind of lighter weight solution to train kind of a La Villa, or like even model like can compete with the La Villa using just 8 GPUs like in academia resources. So yeah, so like I think I say too much. Yeah, still I'm very happy, like because I'm too happy, so I maybe speak too much. Yeah, so thank you everyone. Yeah.
And the last selected award in no order goes to Sound Spaces 2, a simulation platform for visual acoustic learning.
Thank you for the award. Hello, everyone. My name is Chen. I recently obtained my PhD degree from UT Austin, working with Professor Kristen Grumman, and right now I'm a postdoc at Stanford, working with Feifei Li and Isang and Dali. So it's a great honor to receive this award for our work on Sound Spaces 2. And I want to briefly reflect on this journey and the impact this project has had. Sound Spaces 2 began as an ambitious idea to bridge the gap between audio and visual perception for egocentric vision in the embodied setting, where a robot can see and hear the world as humans do, enabling a more immersive and interactive AI experience. Capturing scalable and massive egocentric audio-visual streams can be challenging, and we decided to take a simulation-driven approach where we can simulate both video and audio given the mesh of the environment and configuration of the space in a scalable manner. We incorporate an audio propagation engine into Habitat, which is a visual simulation platform, and build a continuous, configurable, and generalizable audio-visual simulator that produces realistic audio-visual rendering on the fly. Developing Sound Spaces 2 was a challenge, but also rewarding, which required the collective effort from both researchers at UT Austin, but also researchers from Reality Labs at Meta. The impact of this work has been profound. It has been the most widely used audiovisual simulation platforms for egocentric audio rendering, transforming how researchers approach multimodal AI tasks. Seeing the community adopt and build upon our work has been incredibly fulfilling. Sound Spaces has enabled new research directions, facilitated advances in navigation models, and even crossed over to the audio community, impacting challenges, for example, at ICAST. I want to thank my collaborators and the supportive research community. This recognition has been a collective effort, and we are excited to see how Sound Spaces 2 will continue to inspire and drive future innovations. Thank you.
With that, I would like to particularly thank all the members of the EgoVis board who took a lot of time to review. I also would like to thank and congratulate all the people who submitted but were not selected in the top 10. They were an exceptional set of papers that we had to look into. Great progress. And I will end by thanking the Meta Area team for sponsoring the Monitor Award, which hopefully will allow the authors to enjoy a little bit more beyond my handcrafted art craft drawing certificates that you will receive. Thank you very much. And next, we're going into the third keynote, with Tushar.
Okay, that's good. Yes, let me introduce you. All right. It's my pleasure to introduce Michael Frank and Priya Long as our speakers for this session. Michael is a professor at Stanford University, where he heads the Stanford Language and Cognition Lab, which builds computational models to study children's language acquisition, part of which involves how this relates to their visual perception. And Priya is an incoming assistant professor at UC San Diego, leading the brand new visual learning lab. She led a lot of the work on the vision to language acquisition link while she was a postdoc at Michael's group. I interacted with Michael very briefly over email back in 2022. We were supposed to schedule a meeting to talk about some connections between my research and his own group's work, but I was 2 months from graduating, and understandably things just fell off the radar. So I'm very happy to hear about the research, pick that up, and see what our two fields can learn from each other. Take it away.
Thank you very much for the invitation and the kind introduction. We're very happy to be here today to connect with this community and to share some of our most recent findings. So my goal today is to do some scene setting and tell the story, and then turn things over to Bria to tell us about the recent work that we've been doing. So as an outsider to the computer vision field, the pace of progress in the past few years has just been incredibly exciting. And the same is true for natural language processing, where the rise of transformer language models has just fueled these incredible advances. My question is how these tools can tell us about the human mind and how they can provide insights into how children learn. Comparing AI to humans is exciting, but there's a fundamental problem, which is that AI uses vastly more data and often vastly different data. So starting from the perspective of the human mind, here's a picture of my 5-year-old son, Jonah. He's just learned the game Candyland, and he's playing with 2 of his buddies. What does he have in common with modern AI models? Critically, both he and state-of-the-art language models are zero-shot learners. They can learn new tasks like a quick overview of the rules. But there's a critical disanalogy between these systems. By our best estimates, Jonah at age 5 and other 5-year-olds, they've received between tens of millions and at most hundreds of millions of words of training input. In contrast, LLMs show zero-shot learning at hundreds of billions, trillions, or even tens of trillions of words of data. So there's this data gap of between 3 and 6 orders of magnitude that we need to explain between learners and models. And these same arguments, of course, are playing out in computer vision, where people have been asking whether we need better algorithms to reach human levels of performance, or whether human level data will be sufficient to get human level performance even with current approaches. So turning to the cognitive science literature, we can ask what explanations are on offer for the gap between human scale intelligence, roughly in the order of tens to hundreds of millions of words, and LLM scale intelligence at hundreds of billions. And although I'm framing this in terms of words here, I think we can think about this more generically in terms of data. And so these arguments really apply in the vision domain. We'll show you that in just a moment. One approach in cognitive science that's been very popular over the years has been nativism, in which the key argument is that humans come evolved or pre-trained with representations of the world, including of concepts like an agent or an object. And this pre-training via evolution leads to very rapid learning. So maybe they make better use of the data they have. A second possibility is what's referred to as constructivism. Here, the emphasis is on children's active and social learning. They get the world curricularized for them, both by the social actors around them and by the examples they themselves generate through their exploration and their movement in the world. A third possibility is simply that the kind of data that kids get is fundamentally different, and the grounded real-world data they receive is actually much richer than what you get when you boil that down into a set of decontextualized tokens. And of course, when you're looking at a graph like this, you might importantly ask how much of this difference in order of magnitude is simply due to evaluation or comparison issues. After all, multimodal transformer models also speak many languages and can recall many facts about the world. That's not so true of my 5-year-old. What I want to argue today is that there is a strategy that can help us address these kinds of questions. The strategy is that you take your algorithm of choice, you train it on children's training data, and you evaluate on children's learning outcomes. In other words, you try to create an apples-to-apples comparison between models and human learners in order to understand whether the efficiency of algorithms is sufficient to learn what children learn on the amount of data that children get. And then, of course, we can do the hard science of using LLMs or other models as cognitive models and comparing to other kinds of models. For example, those with greater pre-training of some sort, or greater ability to explore the world and learn actively or from social others. So with this kind of strategy in hand, we can then be a bit more specific about how we define what we mean by a data gap. Now, I've been giving you a sort of general idea with respect to zero-shot learning, which I think is a particularly exciting phenomenon, but we can also define data gaps for specific tasks, for example, visual categorization or few-shot learning or grammar learning in language and so forth. And the basic schema that we want to define is that we need some kind of human compatible metric. So our benchmark needs to be something where we can get a human top line. Then we want to assess what kind of data humans actually have access to and define some age level of performance, whether we want to match a 5-year-old, maybe that's a low bar, or whether we want to match an adult human. And of course, calibrate to the data quantity of that particular age. And then we can create scaling curves and define a data gap with respect to those scaling curves. So this is the kind of approach that we're seeking to follow in this kind of work. And in order to enable that, my lab aims to build open data resources that help us characterize children's and their performance, make those available to the community, both for developmental scientists to study learning and also for folks like you to use as benchmarks. Some of our resources concern children's language input. This is both multimodal video as well as corpus data. We also archive data about children's in-the-moment processing with eye tracking and their learning outcomes based on large samples of kids from around the world. So in the next couple of minutes, I want to tell you the story of our journey into looking at egocentric video as a particularly important kind of training data, which is, of course, why I'm here and hopefully why we can tell you a little bit about some of the work here. So the first data set that we created was called SACAM. This was an early data set that we gathered using our first attempt at an egocentric camera. It was a small, lightweight, matchbox-sized camera with an aftermarket fisheye lens. We gathered data from 3 children, about 470 hours, 2 hours a week, from 6 months to 30 months, gathered now quite a while ago, starting more than 10 years ago. And the quality here was relatively low, 640 by 480, and the audio especially is low quality. Now, this data collection, we've heard a couple of people say, well, this data took me 8 months, and I respect that, but this data collection was quite onerous. And for that reason, the only people who participated were the children of developmental psychologists. But we were very proud of this data set because we were able to share it openly through databerry.org, which is a video data sharing site specifically for developmental data. Developmental data are more sensitive. They're gathered in the homes of families, and the activities that are represented there include not just meal times and play times, but also diaper changes, breastfeeding, a variety of intimate activities. So we need more protections on these data, but we want to make them as open as possible to researchers. So if researchers at universities are interested in accessing these data, they can sign an institutional agreement that requires that they not re-identify or reshare the data. And if folks are working in non-institutional industry research labs and are interested in accessing the data, they can collaborate with folks in universities to gain access through an authorized investigator. So if you have trouble with access to this data set, please let me know, because it's our intent to make this open to the community. And you can see, many of you are specialists in egocentric video, so you know a little bit about this, but you can see that the child's perspective is quite different from the adult perspective, as noted by pioneers in this field like Linda Smith, Karen Adolph, Chen Yu, and a variety of others who have used this method and from whom we learned how to apply it. Our first steps here taken by Bria were into characterizing the social information that kids had access to. And our idea was to use off-the-shelf computer vision to get a sense in this larger corpus of videos what kids were seeing. So we used pose detection via OpenPose. Results were substantially worse than in non-egocentric video, in part because of the complex crops and angles that the models encountered, but still better than previous systems that we'd used. And in this data set, we found robustly something that other investigators had noted, namely that there were far more hands in the field of view of kids at all ages, and for all of the 3 of the kids, than faces, suggesting, again, following previous research, that hands are really a uniquely valuable learning signal. And you can get a very nice sense of this here in these frames, which have been blurred to show the general kind of human characteristics of the human field of view, which is fixated on a single point with high resolution. So you can really see how hands are demonstrating, pointing, showing, and so forth, and really could provide some interesting signals. We had less success with SACAM, however, when we looked at understanding category learning. The videos were really too low resolution for segmentation models, at least at the time. So we used MaskRCNN, and we really got very poor performance. Even after fine tuning, we only did well on a small number of object categories. The video angles often obscures what kids were interacting with. And as has been recognized by a variety of work in this domain, in the natural home setting, infants see some objects a tremendous amount, and then there's a long tail. And dealing with that long tail was very, very challenging given the nature of our data set. So we weren't able to pursue this direction with those data. However, the growth of contrastive learning, unsupervised learning methods in computer vision was really an important step forward for us. And so our collaborators, Cheng-Shui Shuang and Dan Yeamans, started to train a variety of different contrastive learning algorithms on SACAM data. Their interest in this study was in doing neural predictivity. So they were using both fMRI recordings and also macaque electrophysiology data to try to predict the kinds of representations that primates learn in their visual system based on these contrastive learning algorithms, a variety of different algorithms, including SimClear, local aggregation, and others. And Cheng-Shui found fairly good performance for these algorithms, both static image and video-based algorithms on SACAM. But they called this really a glass half full, glass half empty finding because the unsupervised approaches didn't actually beat either unsupervised approaches on ImageNet or supervised approaches. And so there was really more to do here. So there was a kind of memorable meeting where Dan came to me and said, you know, I know this was a lot of work for you to get this first data set, but could you get a lot more data? So Bria's going to tell you a bit about that multi-year project now.
Thanks for having us here today. So here in the second part of the talk, I'm going to tell you a bit about the BabyView camera and the data set and what we've been able to do with it so far. So we set out to create a better, higher resolution camera for use with kids. We collaborated with a product design firm in San Francisco called Daylight Design to construct this device, which is based on the ultra lightweight GoPro Hero Bones, which you can see attached here to a child safety helmet with both of my children nicely demonstrating for us. These are relatively easy to build and easy to deploy. There's a 3D printed mount and the components, it's around $400 each. And our team can build these in around 10 minutes. Importantly, with the GoPro Hero Bones, we can now capture both video data, but also accelerometer and gyroscope data to identify the child's self-motion. So now we build entire bouquets of BabyViews that we send out to families around the US, hopefully other places in the future. And we ask parents to record their children's everyday experiences in the home. And so our goal here is to record an entire child's year worth of data. That would be 4,000 hours of data. For context, SACAM was around 400 hours, so this would be tenfold in size. So of course, this is quite ambitious and we are still working on it, but I want to give you a sense of what these videos look like. And in fact, here we go. This is a video from my living room. This is my daughter doing a dinosaur puzzle in the living room. And you can notice right away that you can see her hands because it's a much different field of view. We've rotated the camera, so it has an effective 100-degree field of view in the vertical dimension. And now you can see not only who she's seeing, but also what she's doing with her own hands and what objects she's interacting with. So this is one small snippet of a video from the data set. Currently, we have 28 families. We're going to be having our first release on Databrary in November 2024. So right now there is a parental embargo on the data, so parents can excise portions of the data set that are sensitive afterwards. So it's not yet available, but will be in November. So we have 28 families that have contributed to this first release. You can see the cumulative hours of video on the y-axis with the age and months during recording on the x-axis. Different families are recording different amounts of data, but some of our star families have already recorded, upwards of 60 hours of data and are still recording to this day. So we are continuing data collection right now through next September and perhaps into the future pending funding. We've been recording not only in the home, but also in a different type of environment, that is a preschool environment, where we're starting to capture children's learning environments beyond these early years in the home with their caregivers. These are peer-to-peer interactions among 3, 4, and 5-year-olds in a preschool environment. This particular environment is a Montessori-like preschool where kids roam around relatively unstructured, and so we get a lot of variation and a lot of different kinds of activities happening. And while we're still analyzing these videos, we've already started to look at the language data in them. And we've seen quite a bit of variability just in what happens in this one preschool. So we've looked, for example, at the grammatical complexity of the sentences that adults and other children and the children wearing the camera are saying and during different activities, either indoors or outdoors. And we see quite a bit of variation in that grammatical complexity, as well as variation in the amount of speech that's happening, and presumably in their visual environments as well. So just in this first pass, we see quite a bit of variation in language across these different activity contexts. This higher resolution video captured in both the home and the preschool environment has some real advantages, as you might anticipate. So we turn to pose detections, going back to our original work, and we wanted to benchmark a suite of pose detection models to see if we could get some that might actually accurately detect the poses in these videos. So we have the COCO validation set, the different models off the shelf on the x-axis, and then we annotated around 300 frames ourselves of every pose key point in a number of frames. And while you can see that there's quite a gap in terms of how these models are doing on these egocentric developmental data points, as well as versus the COCO validation set, we do see that our largest models are doing pretty well. So these higher resolution videos and the bigger and better models are allowing us to have improved pose detection for all key points, not just faces and hands. So here is another video from the data set, again, in my living room, since we're still under the parental embargo. Here's my daughter getting a book to bring to story time, and you can see the pose detections overlaid on both her own hands, as well as myself and my son. These higher resolution videos also have advantages in the other domain we've examined, that is in object segmentations. So this we've evaluated less systematically, but just to show you a few example frames, this is the same MASCAR CNN model. This is not fine-tuned, just off the shelf. These are higher confidence segmentations. And you can see while there are quite a number of miscategorizations, those duplos are not scissors, it's still getting a pretty good sense of the boundaries of the different objects in the scene. So we're excited to see how these higher resolution videos are enabling us to use all sorts of different off-the-shelf models to extract descriptives from these data, which will be useful just for characterizing what's happening across development, across individuals, and across different contexts. Next, we turned to seeing what kinds of models we might be able to train on these data. What kinds of models can actually learn from children's egocentric visual experience? So we asked, how well do self-supervised vision models perform as they learn from increasing amounts of developmental egocentric video data? So this work is led by Stefan Stoyanov, who's here today. You can say hi if you'd like to ask him any questions. So what we're going to do is train on 1, 5, 10, 25, 50, and 100% of the data set. And we're going to be training actually on a combined data set of both SayCam and the BabyView home recordings. So we're trying to get as much data as we have on this first pass, and we're going to be collecting more data in the future. But this is to see when we have as much data as we do, what can these vision models actually learn? What we're going to be doing is training different versions of DynoV2, which is a self-supervised transformer. And one of them in particular, we're going to be using this model because we can evaluate it on a number of different downstream tasks. So we can evaluate it on both ImageNet classification using a linear probe, but also depth estimation, as well as semantic segmentation. So we're going to ask how well do different vision models trained on increasing amounts of the data set. These are going to be randomly sampled frames from the data set. How well can they perform on these downstream tasks? So next, I'm going to show you the results from these 3 different domains. So here on the y-axis, we're going to have the top 1 accuracy as well as the top 5 accuracy for ImageNet categorization. The red X is the random initialization of the model, and in blue, we're going to have increasing amounts of the egocentric video data. And so in general, what we see in both top 1 and top 5 accuracy is that as you have increasing amounts of data, of course, you're getting better at ImageNet recognition, but there's still quite a big gap to ImageNet pre-trained DynoV2. It would require quite a bit of data, unrealistic amounts of data to get up to that human performance. You might also note that little pink dot that is actually Ego4D pre-training. And even when we're increasing our data set size by quite a bit by training on Ego4D, we're still quite a bit far away from ceiling. So this suggests that learning from egocentric videos, when we're taking these random frames from the videos at least, is really challenging. We're still quite far away from achieving human level performance. We also examined depth estimation as well as semantic segmentation. Here, the relationship is a little bit less clear for scaling. As you add more data, you don't necessarily get that much better at either of those tasks. So we're still quite far away from being able to use this kind of data to train a model to human level accuracy. But you might remember from the first part of the talk, when Mike said that we want to be evaluating on children's learning outcomes. In fact, how should we be evaluating models in the first place? Should we even be evaluating them on ImageNet object category recognition if we're giving them videos from the first few years of a child's life? So in fact, we very much agree. And so that's why in the last project I'm going to tell you about today, I'm going to tell you about our work trying to evaluate models like children. In order to do this, you need to have large developmental data sets of learning outcomes, which is non-trivial at best. So I'm going to show you an example trial from our picture matching tasks, which I'm going to show you the data from today. Here are my kids, yet again, now a bit more grown up. She hears the word duck, chooses the correct image. Here's the word milkshake. It's going to ask me for some guidance. I'm not quite sure what that is. Still gets it right. You'll notice there's some distractors on here. Here the word is knee. She gets distracted by that other body part, but eventually gets it right. So here on all of these trials, we have distractors that vary in the similarity to the target word, the target visual concept. And so we can actually start to model not only the actual target choice, how well children are at knowing what a knee or a milkshake is, but when they choose distractors, what distractors they choose. So this was the task we use in a task we've called visual vocabulary. We have quite a few children here. We have about 1,600 kids. And now we're going to be able to use these data to calculate how model human dissimilarity changes relative to model training. So on the x-axis, we're going to be using checkpoints from OpenClip, which is a multimodal model. And we're going to be plotting model human dissimilarity on the y-axis. So closer to the bottom is going to be more similar to humans. And we're going to do this for different age groups of kids. So we have 3 to 10-year-olds, around 200 adults as well. And what we find is that really early on in training, you actually see that the model is more similar to the youngest kids. So it looks more like the 4 and the 7-year-olds than it does the adults, the 25-year-olds, that turquoise line. And as training goes along, you see that the model becomes more similar in its response patterns to adults. So there is at least some similarity between how the model is learning visual representations for these common visual concepts and how kids are learning representations, how they're getting refined over childhood. This is just one of many ways that I think we should be evaluating these multimodal models. And in fact, it's one task in a new project we've been calling DevBench, which is a multimodal developmental benchmark for language learning. So visual vocab was one task. Here are the others, which I won't go into in detail, but are now up in our paper and archive. So we have a pretty large age range. There's infants in this benchmark as well, all the way up through adults. There is eye tracking task. There is the task I just showed you. There are similarity judgments. And we think that this is really important for evaluating models like children so that we're not necessarily evaluating them like adults or against a gold standard that's not realistic for them to achieve based on children's training data. And so in general, we think that by examining children's data, training data, constructing models that are learning from this data, and then systematically evaluating them on children's learning outcomes is a really important way to try to understand the data gap between human learners and machines. And with that, I'd like to thank you for your time, highlight all the wonderful folks who've been involved in this work, and we'll take any questions now.
We do have time for a couple of questions, so Emma.
Great presentation. Thank you very much for coming and sharing with us. I'm curious about this reluctance in the child making the decision very quickly, because that's not what models do, right? Our models are very decisive. Do we know whether this is a crucial part of developmental learning? And if so, what insights can you offer to us on what you've learned from this type of information?
Sure. Yeah, thanks for that question. So in this particular video, I only showed you responses where the child was correct. Those were pretty easy trials. But you can look systematically at children's error patterns over development, which we have done and are incorporated into that dissimilarity metric. And children, they go from kind of choosing distractors randomly to choosing more related distractors over development. And so the behavioral paper that comes from that task, we see a really long developmental trajectory in this, like all the way through age 8 and 9. Children are really taking quite a long time to have very precise representations of visual concepts. But you can get graded probabilities from these models. You can see that they're more confused, between a knee and an elbow than between a knee and a milkshake. So I think that metric is actually doing a nice job of picking out model to human similarity.
The idea which we saw indeed everything that maybe having a better knowledge of what objective the children are trying to solve with the first bridges gap, because like I think the algorithms are important, but like we still don't know what objective they are trying to solve.
Thank you for that. So I think I take your question to be, how does this, what's the interaction between understanding kind of sample efficiency and algorithms versus objective? I think I'm being kind of classic sloppy cognitive scientist and lumping in algorithm and loss function in the same thing. But in fact, these are two different things. And I guess I would say that our collaborator, Dan Yeamans, has really actually hammered into me that he thinks our current generation of loss functions is insufficient for describing human learning or even maybe primate learning, that the kinds of predictions that organisms want to make about the world are very different than the kinds of predictions that, say, Dino or SimClear are making.
I had a question about, Priya, you had the slide about how the training of an open clip model resembles 7-year-olds as training progresses. Was it purely based on just accuracy on a benchmark, or do you think there's specific quirks about what a 7-year-old has learned versus what a 1-year-old has learned that is also captured?
So this is, I kind of went over this quite quickly, but this is not just accuracy, this is actually modeling the choice patterns. So the probability that a child is choosing the target and all the distractors relative to the model's probability of choosing those. So it isn't just pure accuracy. In fact, that isn't a great, you don't see really nice correlations across development when you just look at accuracy.
I see many relationships between what they are seeing during their everyday life and what we're testing. For example, investigating.
Yeah, that's a really nice question. The age ranges here are a bit different. So the video that we have from the home environments are younger kids, and then these are older kids who are doing the vocabulary tasks. But I think absolutely you're right that eventually we really want to know how to say frequency of haptic interaction or visual experience or auditory experience relate to the learning outcomes that children are seeing. It'd be nice to have this within child, but that's a slightly larger project.
Maybe I'll just add one thing to that answer, that kids are really, really good at out of distribution very early. So if you get a 1-year-old and they know the word spoon, they can identify any spoon or, butterfly, any butterfly. They're not limited to the only butterfly they've seen. And that's fundamentally different and really kind of part of this story that we're interested in investigating. Exactly. There's some works that do that, not from us, that are very nice, actually. Yeah. Maybe.
Let's do one last one.
Question more on the kinds of data collection. I'm curious if they're making the devices more comfortable, where does it like data much variation essentially? So they feel like it's what stops you from reaching the bunch of your.
Babies hate hats. I don't know if you've played with the baby recently, but they love to rip things off their head. Yeah. So we actually find that this helmet, although it looks big and clunky, is actually much comfier than the headband type mounts that we've used. You need something rigid enough to maintain the view angle, or else you end up with floor cam or ceiling cam. Right? Probably some people in this room have tried this sort of thing. So you need some kind of rigidity, and if you have rigidity, you have real tension on the head, and that's what the babies hate. So the soft helmet has been by far our winner in terms of uptake. But really, our recruitment here is in some sense limited by the fact that each family requires specific attention. So we check in with every family every week and see how things are working with them. Do they want to delete when their child was naked on the video and so forth. So that's the bottleneck for us, is simply the kind of we call it the care and feeding.
We're out of time. Do we have time for one more, Angelina? Oh, is it a quick one?
Yeah.
All right, let's do it.
Bingo. All right, back over here. Okay, thank you, everybody. Should be okay. I'm going to be as brief as possible. I think Faye has got a 1 minute mark for me in T-minus 7 minutes. So let's see if I don't get the hook to take me off stage. I'm just going to give a very, very high level intro because there's a lot of goodies coming from the team showing really technical results and various other sort of like interesting data sets that have been produced in the course of the last year or so of Project Aria. And I'm going to title it basically Bridging the Gap to Always On Contextual AI, which is really what the heart of Project Aria is all about. And to start with, I'll take us right to the top, which is to remind us of the paradigm that we're all in, which is the first wave of human-oriented or human-centric computing. And what we mean by that is this. Actually, not so long ago, Alan Turing and a lot of pioneers in computer science had no idea what a two-dimensional graphical user interface was. They didn't even have a mouse, let alone networked computing and printers and the internet and all that. They didn't have any mobile phones. There was no mobile computing. In fact, computation was something that humans did. And the dream was to essentially mimic, if not one day go beyond, what humans can do quite naturally. Now, between then and just a few short years later, Doug Engelbart came along and showed what was at that time called the mother of all demos. And so from the point in sort of like the 1940s, late 1940s to 1968, the explosion of the first great wave of human-oriented computing had begun. That meant that in the first demo for the first time, there was a windowing system with a graphical user interface that a user would use to control a computer that would allow them to essentially amplify their intelligence. And it included not just a mouse and a keyboard and a screen, but also networked computing and so on. And we forget about this because, you know, it seems so long ago, but actually, if you look at that date and this date and think that everything in between, everything that basically leads up from the very first kind of personal computer, which was called the Xerox Alto, that put that demo into sort of a real machine you could buy, all the way through to the smartphone that's in your pocket, actually only in 2005. That's it. That's the history of human-oriented computing. And yes, it introduced the paradigm we're used to, but surely there's a lot more to be done. And Turing, of course, you know, before there were these graphical user interfaces, was thinking about computation and the interaction paradigm very differently. They were also thinking simultaneously about artificial intelligence and robotics, and also not just machine intelligence, but animal intelligence. And they were thinking about all these things together, not as separate areas of study. And one particular point I think that stands out is Turing's quote from a conference he was giving, a seminar, where he says, what we really want is a machine that can learn from experience. You know, we don't want to have to sit down and program everything into it, sort of thing. And if you think about between then and now, with your phone in your pocket, especially if any of you have got ChatGPT in an app, you can certainly say that AI is here and it has learned on all of the human experience that has gone into essentially web-based data sets. Internet scale AI is here, and it's here in the form that you can chat with, far surpassing what originally would have been sort of the Turing test, chatting with a human and wondering, is it a human? Now, of course, you can fool it, especially if you're an expert, but, you know, plenty of studies show that ChatGPT-4 and things in its class are well past the threshold of being able to trick most humans who are not experts in the field for many minutes, if not indefinitely. Some people really think of this thing as, you know, conscious, aware of its surroundings. Of course, the thing is that something's missing. It can't possibly be aware of its surroundings unless you tell it about your surroundings. And even though we're at the cusp of multimodal AI today, where you might show a bit of a video clip, it has no concept of your lived experience unless you tell it about it. So, you know, the human experience goes way beyond text and even beyond you constantly telling it about your experience. What we really need to do is give AI your real life context. Now, that's starting to happen with a new wave of AI around essentially wearables plus AI. This is where something like Meta's smart glasses start to be able to provide, you know, in situ, available wherever you are, access to things beyond just what you're talking about in text, to, in this case, video clips, and do sort of, you know, visual QA on it. And that's good stuff. So this is the beginning of a paradigm of wearables and AI towards what we'll call contextual AI. Okay.
To get there, to go beyond where the current products are, we need a lot of egocentric vision research to take place. And that's why we're sitting here today in this particular workshop, because this is the beginning of this paradigm. And it's actually fun to have a look at the history of this. Of course, people might know about the HoloLens. We don't like to think about HoloLens as being historical. It's actually quite a modern device. Aria came after the first HoloLens. But way before both of these, there was Mike Land at Sussex and with his partners doing work on egocentric vision, in particular through the lens of cognitive science and understanding how humans see the world. And what you can see here is one of his own made devices that allowed him to sort of be able to get in the wild eye capture, which was very novel back then. And then one of the very first studies with a backpack and an eye track and an egocentric outward-facing camera to be able to get and start to understand where do humans look when doing tasks and how do their eyes move and potentially why. They were trying to uncover the very first sort of like science of in the wild egocentric research. Now, Aria is a step very much from that point in the direction of, but it must be at scale and it must be available to many, many more people. And that's essentially what we've been doing in Project Aria. So if you do go along to projectaria.com, you'll find yourself with lots of access to data sets and be able to click on buttons to be able to find if you can get one of these devices that are free for academia and industry partners, and essentially start to capture for the first time at scale in a device that doesn't weigh you down, that can last multiple hours, egocentric computer vision data sets that include not just the outward-facing camera and eye tracking, but also spatial microphone arrays and the ability to process that into a 3D space-time coordinate system that allows us to essentially anchor all the information that's coming from the wearer in a consistent frame of reference, which I think we'll see later on has a lot of advantages. So why are we doing all of this? Well, to get past that first great wave of human-oriented computing, the 2D screen, go way beyond it to what we call contextual AI. And essentially, that is the combination of context, both the physical and the digital, with that AI system. In fact, we'll say that we're not entirely sure that ChatGPT-4 isn't already sufficient, especially in an agentic framework. What we're absolutely sure of is that if you don't get the context from your wearable devices to it, then certainly it's not going to be that useful to you. And that brings us to the elephant in the room, which is that AI today is defined by essentially solving for the problem of data and compute. Data both for training time, sure, you've got lots of data, it could be much bigger than your individual data set, could be internet scale. And we need to get there from an egocentric data set perspective at much bigger scales than we currently are. And at the same time, that data is going to look very different from the data that's available to you at inference time because it has to come from an actual wearable device. So whilst you may have trained on massive scale simulated data sets, at some point you must cross the chasm into the real world wearable where you have things like motion blur, you have things like battery life that have to be traded off against the resolutions and the rates that you can run. And the same is true with compute. I might have tens of thousands of A100s that can go to work on those massive data sets. But at some point, the model inference is on devices that have 10 times less battery than your mobile phone does today, and will actually have considerable less compute than your mobile phone will tomorrow. There just isn't the area for thermal dissipation in wearables the size of glasses compared to a mobile phone. With that, Ming-Fei is saying, I've got to stop, so I shall. Welcome to the workshop for Aria in the Egocentric Vision workshop, and I'll hand over to Ed.
Thank you very much, Richard. Just while I get set up here with the laptop, just have a bit of a show of hands of who is working either with Project Aria devices or Project Aria data sets at the moment from the room. Or we
There's one right there.
everyone right there. Okay, we have consent for recording for everybody. Obviously, please do have a look at Project Aria. There. Unmuted as of now. Here we go. Hi there online. Okay, so as Richard introduced, Project Aria's goal is really to accelerate machine perception and AI research for future AR glasses, or really any type of AI wearable that needs to be able to understand your context from the real world. But rather than sort of talk through what the Project ARIA program is a little bit about now, I thought it'd be good to introduce one of our research partners who can talk about it from their perspective. So let's take a look.
I'm a PhD student in computer science at IIT Hyderabad, where I work on computer vision and machine learning. We are working on the driver interpretation project. For example, if you're driving a car wearing the IR glasses, let's say you want to take a right turn, but you didn't notice that there was a blocker there. The machine learning model can tell whether you're paying attention to the object that is in front of you. It's very important for the natural use case of accident prediction. Now, with the help of ILS, we can develop a video understanding model that can help us in avoiding accidents. The main advantage of ILS is the IS data. From IS data, you can map the scene where the driver is looking at, whether they are paying attention to the cars that are there in front of them or looking at the mirrors while they are taking a turn. Also, it gives you the point clouds. Point cloud can detect whether there is another car that is passing by, which may not be visible in the EgoVis. And also it gives you audio. So when the car is honking, from the audio signal, you get that information. So that's how all the sensors can work together. Data collections have become very easy. We can just record the video and upload it through the NPS service. We get the point clouds of the 3D information out of the box. And that has significantly improved the speed of our work. Every year, millions of people die out of accidents. If we can build an efficient model for this, we can save millions of lives.
Okay, so that's just one example of how one of our researchers that we're partnered with is using our Project ARIA to accelerate their research. But really, there are two parts to the Project ARIA program. One is the kit that we provide to external researchers like yourselves to be able to conduct independent research. And we have a number of tools that I'll talk through what that involves. And the second are these resources, these open science tools, models, data sets to be able to use and benefit from Project ARIA, regardless of whether you have access to the glasses or not. And just to take you through some of the updates that we've had over the last 6 months, I want to just talk a little bit about both of these sections in turn. So first of all, I mentioned about the Project ARIA research kit had a number of different tools to be able to use the glasses. We allow people to be able to record sequences using the glasses, to be able to process those sequences using what we refer to as machine perception services, like calculating a trajectory or understanding where eye gaze is. This is a service, a cloud-based service that we provide to be able to up-level people's research challenges and work on different types of goals. We have tools to be able to use these glasses for prototyping, so you can stream data and then process that data in real time, and then a number of different tools to be able to access and consume that data accordingly. So a little bit of a glimpse over some of the updates for these internal tools that we've improved over the last half. One of which is this new tool that they use for actually working with data from the device. This is called ARIA Studio. This allows you to log into your device, to be able to access the recordings from your glasses, to be able to select those recordings, pull them onto your computer, iterate and kickstart machine perception services so you can calculate things like trajectory really very simply. For the purpose of time, I'm going to move forward a little bit here. We have a new machine perception service for wrist and palm positioning within sequences. So you right-click a sequence, you kick off the wrist and palm machine perception service, and then you can then get that output delivered to your computer. And we have a new really exciting tool called Time Sync or Tick Sync. This essentially allows you to take multiple different glasses that are capturing simultaneously in the same space, and you can actually align those very accurately to within a couple of microseconds. So just to talk a little bit about how that works is essentially we have one set of glasses that acts as a hotspot or a server that then the other glasses can speak to. And it really is as simple as clicking from your computer to initiate a recording when you have multiple devices set up. And we really do all that hard work for you. So that's a little bit of a quick start overview over the new features that we've had with the research kit. Now moving on to the open science resources. A couple of days ago, we launched the Dataset Explorer. This is essentially a one-stop shop, enabling you to explore Project ARIA datasets. We've really been influenced heavily by what the team have been doing with the Ego4D program, who have a similar explorer. We're really building that out, allowing more people to be able to understand the contents of datasets,
visualize them prior to downloading, and then downloading them all via the browser. We also have improved our tools to be able to allow you to take the essentially the default format that we produce with Project Aria called VRS, which in fact is open sourced, and then convert that to any format that you want for any of your downstream tasks. And finally, we have things like EgoBlur as well, which really produces the best-in-class tool to be able to obfuscate data that you've captured using egocentric data, so that you can adhere to the various different restrictions and requirements around the world for capturing data responsibly. And finally, I do just want to give this little teaser about the support we have for Nerf Studio that now allows you to take data directly from Project Aria and kickstart Nerfs using that. And this really is just the beginning of our work towards enabling this type of reconstructions using Aria data. So final slide from me, I will just say, we really want to work with partners here in the audience today. We want you to enable you to capture data using Project Aria. The data is yours. We're interested in learning how people work with these devices, what people can learn, and we provide a number of sets of community guidelines to help capture that data responsibly. Now, with that, I'm now going to introduce Chris Shi to talk through some of the data sets and challenges over the last year. Over to you, Chris Shi. Let me help get set up with the HTML. There. Then share. Okay. First. Yep. Yep. All right. Difficulties.
Cool. Can we see?
Yeah.
And here? Okay, great. Hi, everyone. Sorry for technical difficulties. My name is Chris, and I'll be talking a little bit about one of the challenges we had from 2023 to 2024 called Aria Synthetic Environments Reconstruction Challenge. So just to motivate this challenge, we'll take a quick little look at some AR and VR applications shown here. So in order to enable such applications, including gaming, virtual telepresence, augmented spaces, etc., a fundamental piece of technology that's required is the ability to understand the geometry of indoor spaces. So to that end, we introduced the Aria Synthetic Environments dataset. Now, what is this dataset? This is a large synthetic dataset of 100,000 unique procedurally generated indoor spaces. To our knowledge, this is currently the largest dataset of this kind. So it sets a new precedent in terms of scale for indoor synthetic datasets. Furthermore, we've provided a bunch of annotations to enable research for egocentric machine perception tasks. And if you check out the QR code, more details can be found on the dataset website. So what is in this dataset? We'll just take a very bird's eye view here, quite literally. As mentioned, the dataset itself contains 100,000 unique multi-room scenes that have been procedurally generated. And so on the top right here, you can see 10 of these scenes from a bird's eye point of view. Each of these scenes have been populated with 3D CAD models coming from the Amazon Berkeley dataset, of which there's about 8,000 unique meshes. Now, for each of these unique scenes, we simulated an agent walking around these scenes and then simulated sensor data from an Aria rig. So what you're seeing in that middle there with that GIF is 8 scenes, 8 of these trajectories. You're seeing the rendered simulated RGB trajectory
of ADD scene. So you can kind of see the indoor structure, some of the objects, etc. We also provide semi-dense point clouds, which is a product of our ARIA machine perception services. Not shown here, but I'll show it in the next slide or next couple of slides. And importantly, we also provide ground truth annotations for scene reconstruction in what's called, or what we're calling, a structured scene language. And that, as you can see at the very bottom, shows the architectural ground truth layout for these scenes. So what is this structured scene language that I just mentioned? So this is kind of an interesting point here, which is that we're providing these ground truth annotations in a language that kind of looks like CAD. And this format contains all the geometric parameters that are necessary to fully recover the ground truth geometry. But it's very compact. It's only in the order of bytes. It's very, very simple. So this example here represents an entire scene of approximately 8 walls, a few doors, and a couple of windows. Most previous methods typically directly estimate these geometric parameters, and this format suggests that it's possible to use methods that directly produce text-based representations. So by releasing this ground truth format, we're kind of encouraging researchers to also investigate prediction of text-based representations for geometries. And to pair with the release of this dataset, we also released a challenge, the ASC Reconstruction Challenge. And this is characterized by the following statement, which is, given an ARIA trajectory, generate a structured language description of the main architectural layout elements of the entire scene, consisting of walls, doors, and windows. So your input can be, for example, an RGB trajectory that we've released, or on the bottom here, bottom left, semi-dense point clouds from ARIA's machine perception services. In this case, it's overlaid over the RGB images. And the goal is to produce a text-based representation of the scene as shown on the right here. And just note that the geometry and the text themselves are equivalent. We hosted this challenge on the eval.ai website, and the winner of this challenge will present their solution in just 10 minutes or so. Cool. So I'll just briefly digress a bit to discuss our own research into this problem, also using this data set. So we investigated a novel method called scene script. And this scene script is a relatively simple architecture. It's just a 3D CNN and a standard transformer. And given that ARIA trajectory, this time it's not a GIF, but you imagine you're walking through this scene, we use ARIA's machine perception services to obtain a semi-dense point cloud, as we saw in the past slide. And we run it through the scene script network. And this network auto-regressively predicts tokens that represent the structured scene language that you see here in the third column. And we found some encouraging results, not just on our own synthetic validation set, but also on real-world scenes, including offices and home environments. So on the bottom here, we're seeing some sim-to-real generalization of the predicted structure of architectural layout. And furthermore, we're able to easily extend this representation of the structured scene language to include 3D bounding boxes and also coarse 3D object reconstructions, as shown on the very, very bottom right here. You can see some couches and some chairs and tables reconstructed coarsely. And to find out more, please check out the website using the QR code. And just to leave you with something kind of fun, here is an example of that sim-to-real generalization I was mentioning. This model was trained purely in simulation. And this is running in real time on a real-world apartment. And so you can see the architectural layout, some coarse object reconstructions, bounding boxes of arbitrary objects, walls, doors, and windows, etc. And this is viewed through an app we built on the Quest 3 headset. Cool. So this is Scene Script and the ASC Reconstruction Challenge. And next, I'll pass it to Xiaoqing, who will discuss the ARIA Digital Twin Challenge.
Just while we're waiting, is there any questions for Chris on either the data set or the research, just while we're waiting for the Zoom to come online? We have some questions at the end. And Shivesh as well, we're really excited. We'll be able to come up to present his methods for winning both the scene script challenge that you're about to, or pardon me, the reconstruction challenge that you just heard from, as well as the object detection challenge.
All right, thanks, Chris. Yeah. Hey everyone, my name is Xiaoqing, and I'm going to talk about the ARIA digital twin object detection challenges today. So first of all, let me give you a recap of what we have released in the last year, the ADT dataset. So the ADT dataset is, probably the most comprehensive and high quality content of the real world this dataset we have ever released. So the motivation of this dataset is like, we just want to give you everything in 3D, the content of everything in 3D. That includes the object, includes the human, include the scene as well. So we want to see how many AR and AI applications that we can help with, and also inspire you to come up with new applications as well. Right? So let me show you an example from hundreds of sequences that we released in the last year. Right? So this sequence basically in the leftmost column that shows the raw sensor data of the AR glasses captured in the real space. And the rest of the columns are the ground truth associated with this raw sequence. In the third row, you basically see the 3D-oriented bounding box. That means not only the object shape, but also the pose of the object shape we all give to you. And next to it is the 2D box of every object, and also the pixel-accurate 2D segmentation of everything. In addition to that, you also see this hand, the human hand also has the segmentation. That is because we also track the human as well in the scene. We also provide you with the depth map because we reconstructed the surface of everything. And in addition to all of them, we also give you a synthetic data, which is one-to-one match the raw sensor data that is in the leftmost column you're seeing. All right. Then how did we make it? We basically reconstruct every object in real space, every object. So what do I mean by it is we basically push the geometry accuracy to the sub-millimeter accuracy, and we also reconstruct the complete set of the material of every object. And we also push the similarity between the real object and the synthetic rendering to the most. Here is an example that you see. One of the photo is a real captured photo, and the other one is simulated one. In addition to it, and we track everything as well. So that includes not only the static object, like the furniture that are not moving in the scene, but also the moving object that is interacting with the human. And we also track the human pose as well. Also associated with all of the machine perception capability given by the ARIA glasses, like the eye tracking, hand tracking, so everything. Then what we did is we basically modeled the entire scene as well. So the geometry of the walls and the ceilings, and we model every light source in the space to match the real world. And then we put them together. That gives you this beautiful rendering of the apartment. This is a rendering, not a real capture sequence that you can see. The photorealism is basically at every corner of this apartment. let me also give you an idea about what does the content look like for this data set. So we cover two spaces, one apartment and one office, and we released in total 300 sequences for you to use. In total, we have like 400 objects instances, and we have a couple of activities as well. So it's kind of themed. Over the past year, we observed like 700 users that has used our dataset, and this number is still growing up, which is very exciting. And thanks for using our dataset as well. Okay, then next, let me talk about what's new in the H2 and right now as well. So the first thing is like, as Ed just covered in his part, is like we have already onboarded our dataset in the dataset explorer. That means you don't need to go over this tutorial to download this dataset to get an idea now. You basically just go to this website and you can visualize these sequences just by one click. And so don't hesitate and check it out. And if you like it, download it. Right? The second thing, which is more exciting, is we are releasing all of the 3D models, 400 of them, at the same quality that you have seen in the previous slides to you for free. Yeah, and let me show you an example. So this is one of the small objects that we show in the apartment, and we release all of them. I think previously we had some license issue that we were solving. Right now we are conquering it. We're almost there. So just looking forward to it. All right. Let me talk about a bit more about challenges. So we hosted a challenge, which is one of the first wave our challenges in the last year. So our challenge is about 3D object detection challenge, just one of the use cases of our dataset. So in order to do this challenge, we basically apply the same technology into a new space, which is not apartment, not office, but a shopping, mini shopping mall. That means we have the same quality, no matter for tracking or reconstruction for this new space. This is a fly through of the new space. The challenges that we host in more details is a few shots, 3D object detection and tracking problem. That is we select additional 20 objects. Those are examples of these objects. They have some textureless object, has the texture object as well, symmetric objects, all kind of difficulties. And we ported 80 sequences in this space. And the participant had these sequences with 5 seconds of the ground truth at the beginning of each sequences. And the job is to predict the 3D pose of this object for the remaining of the sequences. So here I show you one example. The 3D bounding box appeared at the first 5 seconds and then disappeared. Then the participant is required to predict it for the remaining of them. All right. How do we evaluate it? We basically, because we reconstruct everything so that we use the surface distance instead of conventional like IOU 3D box metrics, so that it's more accurate and more fits into the AR applications. And then we calculate the average precision over all of the sequences. And the winners result is 12%, which is very exciting, but also indicates the challenges we have here, right? The new sensor modality from the Egocentric, and also the nature of the difficulty of the 3D object post-estimation. All right, so that's all from my side. I want to welcome our winner, Shavesh Khan, to onto the stage. Right, so he is a winner for our both challenges, and he will explain to you how he conquered these two challenges. Thank you.
Now, my solution is divided into two parts. One is wall detection, and the second stage is the windows and the door detection. So this is just an overview of how the wall detection works. This is describing this in more details now. So first of all, I take in the point cloud, then I take the ego trajectory, and I convert that into a top-down 2D heat map. So I'm not sure if this is like clearly visible on the right or not. Okay. Yeah, I'm not sure if it's clearly visible here, but like what you can see is like this is like a top-down heat map, where you see like the white lines are mostly the places which have a higher density, and the black ones are the places where we don't have a huge density of the point cloud points. So what you can see from here is basically the higher density points places would most likely be walls, because that's just how the walls are structured. We'll have like a much more higher density, more number of points in those directions, and that's what our object detector basically captures. So once I have this two top-down heat map, I basically train a simple object detection model, YOLO model, and what I'm able to get is the walls as objects. Now, this gives us the walls in like top-down 2D, but we want the 3D structure of the walls as well, like the height of the walls. So for that, again, I use a very simple technique. I take the point cloud, and instead of compressing this along the z-axis as we were doing previously, so previously it was like a top-down view. Now what I do is like I take the point cloud and I compress it along the x and the y-axis. So what that gives us is basically this histogram, and this histogram represents the number of points for every height level at like different height levels. So you assume that there will be two peaks. There will be one for the ground, because you have like more density of points along the ground, as well as you have another like a high peak at the ceiling level as well. So the difference between these peaks basically gives us the height for the walls. So this concludes the height and the like, 3D structure for the walls. Once we have that, then I go for the doors and the windows. So this is a two-stage architecture here. First of all, I take in all the camera images, RGB images, and I train a segmentation model on top of this. So this is basically to generate 2D segmentations of walls, doors, windows, and a background class. Once we have this segmentation done, I essentially do something like a raycasting, where I take in the camera parameters, the intrinsics and the extrinsics, and use that to essentially raycast the segmented points or segmented image onto the walls. So what you see here is basically like, this is like a 3D point cloud, which is extracted out of the segmented images. So like all the points which belong to like a door or a window, they will be projected onto the walls, and you will essentially get like a 3D point cloud, which can either contain points from the doors or the walls, sorry, the windows. Once we have this, what we have is basically like a 3D point cloud of all the windows and doors in the scene. But now what we can do is like we just take all of them and just cluster all of them together to get separate windows and door points, window and door objects, because at the end we want like a 3D bounding box from the point cloud. So that's what I did initially, but that did not really work out. Just because there was issues like the segmentation is not really perfect. There are like noise segmentation sometimes, and also there's issues like there are mirrors in the scene, and sometimes the reflection of doors or windows can be seen in those mirrors, and that's how you basically like just have like false positives, like false positive windows, false positive doors. So this was like not really working out. So that's when I think the context, I think which we already discussed today as well, the context is very important, and the segmentation model was like not even taking the context clearly, because it was doing a segmentation on separately on each of the images. So how can we solve this? So for this, basically, I generated another data set based on the segmentation model which I had. So once you have segmentation done and the recasting done, you have basically these door and the window 3D point cloud. Now I take this 3D point cloud and I take each of the walls separately to generate a 2D image for each of the walls. Once we have the 2D images for each of the walls, I train an object detector on top of it to get the final refined bounding boxes. So how this works is basically taking in for every image or every wall, you take in all the points which belong to that wall, train an object detector on top of that, and since we already have the ground truth bounding boxes for the windows and doors, we can just train a simple object detector again to get the final defined boxes, and these will not suffer from the problem of noise segmentation, and also like it will not have the problems of mirrors, because like it's able to figure out like what should be the shape of each of the windows or the doors. So this basically covers the solution for the first challenge. I'm skipping over a lot of implementation details in terms of time, but if you have any questions, you can take it later. Now coming to the digital twin competition. So the problem statement was basically to predict the bounding boxes for an object of interest. And like this is like for initial 5 seconds, we have like the bounding box, like 3 bounding boxes for the same object. We don't know what exactly that object is, but we can have like extract that information from the bounding boxes. And we have the camera poses of the video as well. So the solution is basically again a two-stage architecture. There's a separate thing running for the first 5 seconds when we have the actual bounding boxes, and then something runs for the next for the testing sequence. Coming for the first part, so basically what I do is I take all the RGB images initially for the first 5 seconds, and I take all the bounding box annotations, and these are 2D bounding box annotations, and I basically crop out all the objects of interest in there. So once you have the images for the object of interest, I pass it, I pass all of them through the image captioning model, which generates separate captions for the same object, and these can be sometimes inconsistent, because if you see this one, like it's very hard to tell whether it's like a mobile phone or it's like a video game, it can be multiple things. But what we're expecting is that like we'll have like some more consistent classes, and like we can basically get some consistency just using like a large language model. So basically what I do is I take all the captions which are generated, I basically prompt the large language model to extract a refined caption. And once you have this refined caption, I essentially use it for the post generation. So I take in the testing images, I use the refined caption, and I use it for a prompt-based image segmentation model. So that's basically just an extension of segmenting model with a language extension, which can take the language prompt, and I get the 2D bounding boxes for the object. Once you have the 2D bounding boxes, I basically take the depth from the annotated 3D position. So the assumption which I'm making here is basically the overall distance of the object from the camera does not change significantly. But in case it does, we can what we can do is like simply just train a depth prediction model and use it from there, and just project that along the direction of the object to get the 3D bounding boxes. And yeah, this again it was a very short description. Like what we can like improve upon this is basically by leveraging the entire training data set. So I was not using the entire training data set just because of computational resources. But if we can have like if we can have that, we can probably improve the model performance. Also, the ball detection in the first challenge, it can potentially be improved by let's also leveraging the RGB data set, and the depth prediction model. It will potentially help both the challenges as well. These are some of the challenges which I personally faced while working on the competition. So again, the lack of computational resources. So if we have that, then we can potentially have like improved participation as well. And also, I think we do not have access to the evaluation script for the first challenge. So if we have that, then we can potentially do like better local validation. So yeah, that's it from my side. And yeah, I have the code available for this on my GitHub repo. It's not available right now, but I'll make it available. And again, thank you for having me. And yeah, thank you everyone.
Thank you. Before we go, I just wanted Richard to give you a chance to present you with a gift in addition to the first prizes there. It's really a tremendous first step towards this, and we're really grateful for the time. Thank you. We're now going to just listen to a couple more presentations about new data set that we can expect, which hopefully will be of note to everybody in the crowd here. Starting off with a new data set called HOT3D.
Good afternoon, everyone. I'm Prithviraj from Meta Reality Labs. And today I want to talk about Hot 3D, a brand new benchmark for hand object tracking. So it's very exciting to see the large scale video recordings that are being created using all the different wearable headsets. However, looking at the sheer diversity of objects in these recordings, we are faced with a scaling problem.
Excuse me, just while I try to figure out while screen sharing is. Oh, it's on the- And also, I'll do it from my screen.
Okay, sorry about that. So I was talking about the sheer diversity of objects in these recordings, and it poses a scaling problem for us. Like, how do we go about indexing and parsing all the objects that are visible in these videos? And our eventual goal over here is to develop an always-on personalized contextual AI agent. So one solution is to only focus on objects with which we interact with our hands. For example, if you're looking at a view of a cluttered desk, we really only care about the objects which our hands are touching, such as the laptop, the mouse, or the phone. If you're walking down a grocery aisle, we only care about the objects which we pick up with our hands, maybe put it in our cart or put it back on the shelf. We really don't need to parse the rest of the objects in the scene. Hands are like a spotlight on the objects we care about. So development of an always-on personalized contextual AI agent likely requires a robust understanding of hand-object interactions. Unfortunately, the majority of the existing datasets focus either on hands or on objects independently. We strive to address this dearth of datasets by providing annotations for 3D hand and object poses involving daily use items captured via multi-view egocentric cameras. We introduced the Hot 3D dataset, which contains 1 million plus multi-view frames of highly accurate hand and object annotations. Recordings from the ARIA device will contain RGB and 2 monochrome egocentric views of the scene. The MPS pipeline also provides us with the slant trajectory of the headset, a semi-dense point cloud reconstruction of the scene, and also the eye gaze trajectory of the participant. To the best of our knowledge, this is the first time a dataset is bringing hands, objects, and eye gaze together into a single consolidated dataset. So to give you an idea of the scale of the dataset, as I already mentioned, we are providing 1 million plus annotated multi-view frame sets. It contains 3.7 million recorded images across all the camera screens spanning 830 minutes of recording. The dataset contains 19 participants interacting with 33 daily use objects with a cumulative object trajectory exceeding 13 kilometers. So how did we go about collecting this data set? We used a motion capture system called OptiTrack, where we place these 3 millimeter IR markers on the back of our hands and on the objects. We built a custom rig, you can see it on the left, to mount OptiTrack IR cameras to track these markers within a spatial area of 2.5 by 2.5 meters. And within this rig, we recreated 3 scenes from daily living. For example, a kitchen scene with a kitchen island and a shelf with produce items placed on it, a workroom scene with a computer table and chair and also a whiteboard to write on, and a
And then I need to unmute the video too, so they see me.
Yeah, if you want.
Please. Let me share this slides.
Yeah, and then here is the usual problem that this is what it's sharing.
It's sharing. Then
Yeah,
what
it's sharing
can I
this
do? But what is recording? Is it recording this view or this? Oh, this. So let me share. Let me actually.
Yeah, you should probably stop sharing and then select
display settings.
Because
But
if
then
you-
it's
if you
shared.
go up,
Yeah,
yeah, that's a problem.
that's a problem. Okay, so let me. Yeah, so we can share.
You should start sharing, and then well, you should stop sharing.
Well, I don't
then
think I
start
have
the
anything
presentation.
critical here.
Yeah, if you start the presentation now, then you should be able to select the screen you want to share.
Up here. And then I do share. And then I share this. Then the way will be good. And that's what will be recorded.
Yes.
It's already muted, so the answer will be good.
Yeah.
Yeah.
But we still can wait a couple of minutes.
Yeah.
Well, the second here, so that's gonna be. You don't see the pointer.
Yeah.
I see the pointer here, but then it's complicated. Yeah, okay.
Try to use the pointer function. So if you
Yes.
click there, I don't know if it's.
Yeah, there's a point. Yeah, that's better because the Zoom
Yeah.
participant can also see that. And
That's
I just want to say hello.
Hi.
And yeah, I'll be the chair of your session.
Oh, perfect. So it's good. Control me the time. I have not checked how much time, so just 5 minutes before or after you.
Okay, yes,
Right.
I can show. So it's 30 minutes, including questions.
Okay, so I'll try.
So when do you want me to let you know?
Maybe 7 minutes before, so I have 2 minutes to wrap up.
Okay,
And 5
okay.
minutes. Because I know. Hopefully
Yeah.
I will.
Okay, but I think. Okay, I'll show you the 5 minutes.
5 minutes.
But
perfect.
I'll show you 7 minutes.
7 minutes. Yeah, exactly. That's there is an understanding. Hey, Vita. Yeah. So this is there are some middle phase around a couple of weeks
I don't know whether if we want to make it worse. Yes, we do have. The story is point of view. Already. Egocentric. So I've just got to basically reorder. Of course, I think let's check. I'm actually some people. Yes. You did this news. Join with this line. Yeah. The logic is given. I don't know what you want. Yeah. What I want to show I will because it is fine. I have this.
For this announcement, so yeah, it's still it's 4 o'clock right now, but we'll wait for a few minutes more for everyone to make sure to be back to the room. So yeah, please wait for 3 or 4 minutes, and also please be seated for people who are standing there.
Actually, we use the arm. We use the arm. We trying to show this. I think it's like and when the camera goes, because you're trying to get the the object is central, but the area of the image, like the previous use, also have area show that bound which make
We'll begin 5 minutes or so. Yeah. Right, so yeah, let's resume our last sessions. So I'm Takumi Agi from AIST, and it's a great pleasure to introduce Professor Fernando de la Torre for the last keynote session. And he's an associate research professor at CMU Robotics Institute, and he's directing the Human Sensing Laboratory. And his research interests are in the field of computer vision and machine learning, and in the particular applications of human health, augmented reality, virtual reality, and method that focuses on the data, not the models. And yeah, today he will introduce talk about egocentric vision for human sensing. So yeah, Professor.
Yeah, thank you very much for the kind introduction, and thank you to the organizers for letting me speak in this very exciting workshop and also in front of this very distinguished audience. Today, the agenda for today, I briefly talk about some activities that we do in the Human Sensing Laboratory to try to understand human behavior from sensors. And then we are going to deep dive a little bit in how we can use egocentric vision for face and body avatars and other activities that we are going in the area of egocentric vision for human. Let me start a little bit about talking about the Human Sensing Laboratory. I started this 16 years ago to try to model subtle human behavior. And this was in part inspired by the work that John Gottman did. John Gottman is a psychologist from the University of Washington. And since the 80s, he has invited more than 3,000 couples to his lab. His lab is called the Love Lab. He invites the couples to the labs and asks them to start an ongoing topic of disagreement between the couple. One likes the dog, the other doesn't like the dog. And then after 45 minutes, seeing the interaction, he's able to predict with between 85 or 95% if this couple is going to get divorced in 15 years from now. You might wonder, how does John Gottman do? He looks through the video and he encodes every conceivable emotion that the couple shows in what is called a specific affect code. This specific affect coding has 5 positive emotion, joy, validation, humor, and 15 negative emotions like contempt, criticism, stonewall. He tries to encode all these emotions and then let's map into this label if the couple is going to get divorced in 15 years from now. But in order to do that, you need someone with the expertise of John Gottman, and you need the tedious manual labeling of doing all this encoding of emotion. So my big dream is always to develop machine learning algorithms to be able to predict all this subtle human behavior from sensors. Okay? And by the way, if you want your marriage to survive, 2 tips from John Gottman. First, show 5 times more positive emotion than negative one. Second, never show contempt to your partner. Along these lines, we did work like depression assessment. So if I'm depressed, I'm going to an interview with a clinician. The clinician ranks my depressed state after asking several questions. How are you feeling today? Do you have suicidal thoughts? And they come up with what is called the Hamilton score. But this depends on what you tell the clinician and the expertise of the clinician, not on how you behave. So our goal here was to provide some quantitative measures of behavior from audio, from depression, from audiovisual information. We record the interviews between clinician and patients. We record the face, we record the body, and we were able to predict with around 70% of accuracy if the patient was depressed or not, only from audiovisual information. Again, this is better than chance. There is a sigma there. And recently, another thing that we are very interested in this human sensing laboratory is try to monitor the well-being of individuals. My parents are in Spain, and I live far away in the US, so I would like to have systems that can monitor the well-being of them. But I've been working in computer vision systems for more than 20 years. I don't want to have cameras. So one of the things that we ask ourselves is, can we use the Wi-Fi signal? The Wi-Fi signal that is in this room to try to detect humans in the scene. And that's what we did. What you see here is how we are able to detect dense pose just from the reflections of the Wi-Fi signal. Now, this is a very contrived scenario. We have here 3 emitters and 3 receivers. This is from your router, the router that you have at home. And then we have people working around, and from the reflections of this Wi-Fi signal for the amplitude and phase, we were able to detect these dense poles. And we post this as a supervisor. Anyway, so in these 2 works, the key point was to be able to recover really subtle human behavior, like in the case of depression or marriage outcomes, or in the case of Wi-Fi, where the signal is almost noise, and that's what we have to recover. And that's the algorithms that we do. Now, this is an egocentric vision workshop. So right now, the challenge is, how are we going to use ego vision information for what is likely to be the 4th revolution in human computing? In my lifetime, I was lucky enough of see at least 3 revolutions in the area of human computer. In the 80s, the computers. In the 90s, the cloud computing and the interaction in the computers in the World Wide Web. 2007, we have the introduction of iPhones that allow interaction from everyone to everywhere. And now we are in the verge of the introduction of augmented reality and virtual reality with projects like ARIA or projects like Quest from Meta or Vision Pro from. So in many of these AR applications or VR applications, we are going to require subtle egocentric vision. We need to recover really subtle signals from humans. And I'm going to show you some examples. The first one is egocentric vision for face avatars. This work done at Meta while I was at Meta. And here, right now, I'm transmitting this talk via Zoom, but it's not the same. I cannot interact the same as the audience I have here that the audience I have at Zoom. And by the way, I say hi to everybody in Zoom, okay? But here I can see your face. I can see if you laugh at one of my jokes. I see if you have attention to some of my slides. It's not possible in Zoom. So the future of communications in the metaverse might be something like that, where what we are going to have is we are going to have an immersive headset that has 3 cameras, 2 pointing towards the eyes, 1 pointing towards the mouth. And from these 3 cameras, what we have to do is to extract the information and map it to an avatar that looks like you and behaves like you. And again, the trick is in this subtle human behavior that we have to extract. And this video probably you've seen before, but this is how it looks like. Here in the top corner, we have 2 people talking and they see the other person's face in the VR. It's much more immersive. And that's what. In order to that, in the Pittsburgh Reality Labs, the first thing that we did is we captured your face and your body with capture systems that have many cameras, more than 100 cameras. This is how our data capture looks like. We have kind of 50mm lenses, and we can capture 4-level details. That's that's a lot of cameras, very high resolution. And from that, what we did is first we built 3D models. AR and VR is all about 3D perception. So what we do is we have the multi-view settings. We do photometric stereo, detect some key points. Then we try to fit a common mesh. This mesh is going to be common across all the faces. We do some refinement. And at the end of the day, what we have is we have a mesh, 3D mesh, and we have a texture. And from that, we do what any machine learning person does nowadays, is we learn deep learning models with an autoencoder, in this case, a variational autoencoder. What we have is we have the mesh, we have the texture, and what we do is we find this variational autoencoder that has 2 parts. One, the state of this variational autoencoder encodes something about the expression, and the other latent space is encodes something about the viewpoint. Now, we have, this is a person-specific model. Basically, I collect data of you, and I have a person-specific model of you. This is a decoder that giving one latent space of expression of viewpoint I can synthesize. But the big question is, okay, so I have a generative model, a person-specific generative model that can reconstruct me, but the question is how I'm gonna solve the correspondence. In vision, you know that always the main problem is to solve correspondence. In this case of settings, for egocentric vision, also the problem is the correspondence. How do I find the correspondence between this facial expression and my avatar? Because if I know this mapping, then it's a regression problem, like many other things in computer vision. But I need to solve the correspondence, and because I have the headset, I don't know. So we do this in a self-supervised manner. And the idea is we are going to have many videos of someone that we have captured with this VR headset, and I know the decoder of this person. This is frozen. This has been learned offline. And then what I want to do is the following. I want to learn an encoder such that when I decode this, the expression and the pose of this avatar, and I render this in the viewpoint of the camera, I can reconstruct these views. That's what I want to do. Here, there is one other issue that we have, especially with egocentric vision, is we have here infrared cameras, and here my model has been collected with regular RGB camera. So there is a domain transfer that we have to learn. So basically, given a set of images that I collected and a person-specific model, I want to learn an encoder and a domain transfer such that these two things align. And this is what shows in this video that we show here, that we are able to, to align this 3D model that I have, person-specific model, with the video stream that I have from my VR headset. Now, this is the problem here is this is only for one subject. It's person-specific, so what we want to do is person-independent. We want to generalize to many users. And even for one user, you can see there is a lot of variability. People change. There is variability in the background. There is variability in the appearance. So the other thing that we did is unsupervised expression alignment across many subjects. So we have really accurate correspondence for one subject. And then now what we do is we learn across many different subjects. So how we do that? So for every subject that we have the correspondence with what I explained before between the VR images and my 3D avatar. And then what I'm going to do is I'm going to learn this from many independent subjects. Now, what I want to do is to have a backbone that is common across all the subjects. This backbone, what has to do is marginalize everything that is not related to expression. This backbone is going to marginalize background, is going to marginalize lighting, is going to marginalize appearance, because this is not relevant to the expression that I want to transfer. So that's what we do. And the other thing is here we have the mean of the 3D shape that also helps to do this normalization. The other trick that we did is we did 3D augmentation too, not only 2D with neural networks to do not suffer from overfitting is always critical to do augmentation. In this case, it works much better when we do 3D augmentation. And this video shows something very interesting. That is, when we learn across several subjects, we are able to align subtle, again, and always the trick is subtle facial expression across users. You just record different video sets, talk whatever you want, and then we align all the expression across users. And that's interesting. And some of the expressions are very subtle. Remember that the bar for communication is very, very high. We have to have communication systems that transfer every subtle expression, because in every subtle expression, we can have a meaningful social signal. So that's the key. And this is an example of an unseen subject and how we transfer, you can see in the mouth, how we transfer the expression from this person to the mesh. I can skip this, and this is Yasser, of course. And yeah, you probably have seen something like this before, but we can add texture to this one. Now, let me talk a little bit about bodies. We can apply similar technology to bodies. So we have egocentric video, and the problem is the same. from only one monocular egocentric view, we want to transfer the body motion to an avatar. Now, we have a problem. This is the problem. We have many problems. Otherwise, we would not be here. But one of the major problems that we are going to have, and this is common to any egocentric algorithm. First, we have a strong perspective distortions. So we have fisheye lenses, wide field of views that creates a lot of distortion. In this particular case, we have self-occlusions, especially in the lower body. There is, as we all know, ambiguity between 2D to 3D. It's a nonlinear mapping. Recover 3D is always ambiguous. But, and this is where the project area has made a good contribution also to the community. We don't have data with these people. That's one of the major issues that we have with egocentric views. And Ego 4D, 4.2 also, that we don't have enough training data. And in this particular case, because we don't have enough training data, what we did is we created a new synthetic data set of humans. And in this case, we just had 23 male, 24 females, around 400,000 frames, and we tried to cover variability around skin tone, clothing, and different type of actions. Surprisingly, these synthetic data work very well in realistic scenarios. And this is always the domain gap that we have between synthetic and real data. Is always hard to do, but solve. But in the case of humans, we have very realistic 3D models from graphic engines. And this make it work well. In terms of architecture, there was only a couple of ideas that I think are interesting. So we find a mapping from the image to a heat map. This is the heat map. And then we find a mapping from the heat maps to 3D. Why do we break this into these two stages? Well, for two reasons. The first one is we have a lot of data to predict heat maps, but we don't have much data between 2D and 3D. And the second thing is the data of 2D to 3D can be easily generated with synthetic data. And the other thing that is interesting, but this is pretty common nowadays, is that we do some multitask learning. So rather than predict from the heat maps the X, Y, Z position, we also predict the rotations and try to reconstruct the heat maps. So this backbone, is common to these three tasks and provides much more robustness to the method. And then these are some results in synthetic experiments. Not surprisingly, we do better than what was state of the art a couple of years ago. And then we just do an ablation study and just having these three different channels of multitask learning help quite a bit, from 122 millimeters to 50. So that just validates that multitask learning, it's a good idea, especially when you don't have much training data. We also test this in real data, which is mockup 2. And yeah, in this case, again, it performed around 20% better than state of the art for indoors and around 32% better in outdoors. Okay. And this is a little bit the video that shows how the system works. This is with real data. And in this case, we map this egocentric view to the 3D stick figures. This is by far is not, it's not good enough for any VR applications, and there are much better results nowadays. But yeah, back in time was the state of the art. Now, what other applications we are working in the area of egocentric vision for human interaction? One, and this is a collaboration also with Meta, with the team of Shugao. We are very interested in data-free online learning. What is the problem here? We have VR headsets and AR glasses too, that one of the key things are going to be, we are going to need to design new ways of interacting with the hands. We have amazing hand trackings that now can track the hands even when we have self-occlusions and we have the hands touching to each other. The problem is that many times when you ship these models to a user, the user wants to add new gestures. Imagine I want to add a new gesture, which is wait. I have a model that has been learned with around 20 gestures, and I need to add one. Here's the caveat. I cannot use my training data for two reasons. It's very big and there are privacy issues. So what I have to do is to adapt my model somehow to this new gesture without touching my initial training. How can I do this online learning without having what is called catastrophic forgetting? I don't want to forget the gestures or the gestures that I have learned. So that's another, that's another issue that we're trying to solve. And the previous paper is under review, and then this one also got under review. And here, what we want to do is with augmented reality glasses, one of big opportunity that we are going to have cameras looking at people. And one of the things that I want to know is, do I have an engaging conversation with this person? I would like to have my cameras, my glasses have cameras looking all of you and try to come up at the end of the day, which is the slide of the topic that you were more interested in, just by analyzing your behavior. And in this case, what we did is we invite a couple of people that they don't know each other and ask them to talk about topic. For instance, they start talking during 15 minutes, and at the end, they self-report what is the engagement that they have. And our question is, from all these self-reported engagements, can we predict these self-report engagements from behavioral information that I can observe from the AR glasses? And in this case, we use both. We use behavior, but we use also text with large language models. And spoiler alert, yes, we were able. We are able to predict engagement just by looking at this, at least the engagement that is, related to the self-report. This is how the system works. We do everything, track faces, bodies, and also a big component is the large language model surprise the text we are able to translate, have a lot of knowledge about it. And now, if I want to give a message here also to keep is many of the egocentric problems that we have for augmented reality and virtual reality, the main problem, the main bottleneck is not necessarily the algorithms as much as I like, is the data. If you think about when I talk about the project of Wi-Fi depression of face and body, 80% of the effort was on collecting the data. What's the problem? Collecting the data, doesn't bring you much glory. Nobody wants to collect data. It's not the fun part. If I tell you now, how many people wants to do data collection with me next year? Any volunteers? No. You think there's more fun things to do, but it's the most critical part. It's the most critical. So it's not only also about collecting data, it's about labeling. And when we're talking about labeling behavior, behavior is extremely hard to label. Things like depression, you give the videos of interaction between patient and clients to two different professionals, two different ratings. It's very hard to be consistent in behavior. Or in the example that I put, when you have the VR headset covering your face, try to infer what is your real 3D facial expression. Again, it's not a trivial thing. Yeah, so, and when we do collection, I mean, in this case, we are interested in research, but I spent 2.5 years in my life in production settings. And in production settings, data is much more critical. And so you have to make sure that my worst nightmare is that, hey, we ship a product and then it doesn't work for a subpopulation. I'm going to have real problems, Or when I have an algorithm and I say, how do I know where my algorithm fails? Things like that are critical and has to do also with the data and how we process data. So I just want to send the message, and I know some of the organizers here are doing a great effort towards this direction. So yeah, great. Yes, just the unpleasant reality for all of us that we want to do machine learning is remember that 80% of our time is really the data and 20% is the fun of the algorithm, but that's what it is. And just to conclude, and then we can leave it a little bit for questions, egocentric vision is critical for many human sensing applications in AR/VR. I just show some applications in avatars for VR, wearable glasses, gesture recognition and human understanding. For many of these applications, trying to extract what is the subtle signal is critical. And three important problems on this, egocentric vision is going to be data. So let's be ready for that. That's it. So I think I finished on time. Oh, sorry. And I forgot to say thank you to all my collaborators because I didn't do actually most of this work. So let me thank everybody. This, well, yeah, it's here. So I want to thank everybody. This work, some parts was done while I was in Reality Labs, and also some other part while I was at CMU, and many people contributed to this work. And yeah, now we can leave it.
Was a great talk. We'll have a few minutes to our questions. So yeah, please give any kind of questions.
Richard, I wouldn't expect less from you.
Yeah, so we're starting to get used to sort of like visual egocentric, at least in this group. What about sort of out there next generation sensors that we don't have yet? I'll give you an example. What about chemical sensing? From, you know, from a human? You know, they might be sweating a little bit, there might be chemicals in that sweat, might tell quite a lot about the prediction about what happens next. Have you had some thoughts about what the next generation sensing could be?
Yes, I mean, in terms of next generation sensing, definitely, for instance, for augmented reality glasses, my favorite application by far, and I'm sorry because I'm a video person, but it's the audio. You know, when you have a microphone array, and then you can, in noisy environment, you can focus in someone, amplify the voice of this person and the noise. You know? So in terms of something that can happen in the next 2-3 years, it's really definitely the audio. Then in terms of more long-term type of sensors, I mean, we have from haptic sensors, we have these other sensors, you know, there are many sensors that we can attach. Now, the question is, how do we develop? For this technology to really scale, we need to make sure that we have enough power consumption, you know, privacy issues that are going to come, especially from the video side, you know. So these are two things that really need to happen, you know, to make sure that this technology is going to be pushed forward. So another simple one will be kind of galvanic skin response. You can attach this very easily to the glasses. This measures the conductivity of the skin. With this, it can be a good predictor, for instance, of stress. You know, that is very useful. No, one of the things I always thought about how can I use these augmented reality glasses is, you know, is to know yourself. One of the things that the best thing that you can do in your life is to know yourself. Can these augmented reality glasses help you to know yourself? For instance, yeah, if you accumulate all the times that you interact with someone and you see their stress, or the times that you laugh in an interaction, and you know, you can collect a lot of data that can help you to know yourself. You know? So things like that. There. About the other, I did not think too much, but things like galvanic skin response can be done, you know, pretty reasonably nowadays.
Any questions? Yeah.
I'm wondering about the relation to the first thing that we showed with the rotation of faces, where show that both and the third study of the dialogue and our conversation with engagement. The third one, you have executed something and can you comment on the importance of that?
Yeah, for instance, in the first study, when we were doing depression detection, how do you detect if somebody is depressed? When somebody is depressed, they tend to have more gaze aversion. They don't look at the eyes that often. You know, to build trust with someone, and it depends cross-culture, you know, but in the US, let's say in Western civilization, to build trust with someone, you have to look at the eyes 80% of the time. These are the studies, no? Now, when you are depressed, you don't do that. You look much less. Now, when you are depressed, rather than having an honest smile, that you smile with the, you know, with the eyes, you damp the smile. You do like this, but it's not an honest smile. You damp the smile. So these things are super, super subtle. Okay? And then if you think you want to recover these things from face behavior, the head is moving all over the place. So you are recovering a very subtle signal, behavioral signal, when the head is all over the place. So you really need to decouple very well the rigid and non-rigid motion to be able to do these things. No? So this with respect to facial behavior. Now, in the interesting thing when we did this study of engagement is that the large language models actually understood a lot of nuances of language to be able to predict that. The results that we got are super interesting. I don't have a good explanation for that, you know. But but in the scale that we did experiments, which is of the order of 30, 40 people, that was super interesting that the nuisances of in a conversation, whether you are engaging or not with someone, part of the language was be able to be captured by this large language. So, and by the way, I love the Ray-Ban when I have the large language model and I can talk to it. That's a great feature.
And I think we can have one more question, so don't miss out this great opportunity. Then I wanted to ask about like trade-off between like sensor quality and like training model, because especially in production mode, I think it's rare to have ideal sensor, perfect sensor, and you have to balance between, for example, use 2D sensor to estimate 3D, and how to balance those, because if the sensor is quite like too cheap or like kind of less low quality, I think that the total effort will be too high. So any tips for?
My advice is if you don't want to get the price, don't talk to the product team. So they are going to give you a budget, which is like, what can I do with this? So they're going to tell you two things. First, to ship a product, we need to develop the hardware 2 years beforehand. So 2 years beforehand, you have to tell them what you need. And then they are going to give you, I don't know, a 10% of the CPU budget to run your app. And you are going to say, I mean, what I'm going to do here, no? So, but these are the constraints of real production scenarios. No, what I do believe is many of these things we can sense in low resolution, poor sensors, if we have a really good training data that has captured in very high quality sensors. So if we have a very strong prior that has captured with high quality sensors, then we can do inference in low quality sensors. But we need this high quality prior data.
The compatibility between that high quality and low quality sensor will be kind of important.
It's important, but once you capture high resolution, you can always render things in very poor resolution. So the question is to have a good prior in really high high quality, and then render or synthesize this in low quality, which is the thing that you are going to match later.
Yeah, thank you for the talk, and give some applause again.
The camera, so maybe people can also see them.
Okay, yeah, thanks everyone. And welcome to this last session where we'll talk about the Ego 4D and Ego EXO 4D challenges. So this year, like we continued to host our Ego 4D challenges. This was the 4th edition of the Ego 4D challenges. We had 14 tracks this time, and it included 2 new tracks. This year, we also introduced 2 new teaser challenges based on our new data set, Ego EXO 4D. And these teaser challenges covered body pose and hand pose. And for each of these challenges, we had cash prizes for top 3 winners. So for today's program, here is our high-level schedule. Like I'll first go over the overall synthesis for our Ego 4D challenge. what the trends look like, give a bit of overview of different methods. Then Chris and Gabriel will go over Ego XO4D challenge, learnings from that. We have two spotlight presentation, one from the Ego video team covering Ego 4D and some of the Ego XO4D challenge work, and then Hammer team, which will talk about the hand pose. And then finally, we'll have a small prize ceremony for all the winners from different challenges. So this is basically like in CVPR 2023, we had 14 tracks for these challenges. This year, we introduced two new challenges, Goal Step and Ego Schema, and removed one of the challenge, but all other challenges remain the same. Since we have so many challenges, I'll go over each of them quickly to give you a sense of the diversity of these challenges and what are different aspects of egocentric video understanding that these challenges cover. So first set of challenges are about episodic memory. These challenges include understanding what's happened in the past for a user. So we have visual query 2D and 3D, which we provide a crop of an object, which is referred to as visual query. And this object needs to be localized both in 2D and 3D in the given video. We also have a track for natural language queries, where given a video, we pose a query in natural language, and we need to respond to that query based on this video in natural language form. A related challenge is called moment queries, where again, the query is in a natural language form, but we have to localize these moments that are asked in the query temporally in the video. So we call these moment queries. We also have this general object detection challenge called Ego Tracks. This is designed for egocentric object understanding. Like these tracks are really long. An object can appear in like really very long videos, can appear, disappear, and reappear. So this is a pretty challenging task. Among the two new challenges, we have this goal step challenge, where again, we provide a language description, and then you have to localize in this untrimmed video, the start and end time for this particular procedural step. And finally, we also have Ego Schema as part of Ego 4D. This is a benchmark, which is about understanding very long form video. And so you're given a pretty long video clip, and you're also asked a question with multiple choice answers, and you have to provide answers for those. So this covers our episodic memory. We also have hands and objects, which is about understanding how hands and objects are interacting. We have some audiovisual kind of challenges, which is about understanding speakers, who is speaking, what are they saying, when can we actually transcribe those. We have social, where the objective is to understand when a person is looking at someone or talking to someone. And finally, we have this set of challenges about forecasting, which is about, given a video and a moment, just predict what is the next action that the user will perform in this challenge. And long term is same thing, but you have to predict a series of actions that the user will perform. So this is a list of all the challenges that we have. Now I'll go over some trends that we observed this year. So as I said, this is the 4th edition of our challenge, and we have seen the Ego 4D challenges growing very strongly over year. And we started with very small number of teams. Last year, we had a pretty strong participation, but we are happy that this year we have managed to increase the participation even further. This year, we observed 37% growth in the number of teams participating and 43% in the number of methods. And these are different because a same team can have different methods appearing in different challenges. So that's why we separate the teams and the methods. But overall, we see a pretty strong improvement or gain in continued interest in this challenge. In terms of per benchmark, episodic memory is the most popular, but forecasting, which has been historically one of the hardest challenge to participate, we observed significant growth in forecasting, which is really great. This is a pretty hard problem, but we are seeing strong interest in that. And AV and social retain consistent interest. Now we further break it down. We see that this goal step challenge, which we introduced new this year, had a really strong interest, like 24 teams participated in goal step challenge. So it's something that is gathering a lot of interest in the community regarding participation. But as I mentioned, LTA, which is one of the forecasting challenge, also garnered a lot of interest this year. And so we saw highest growth in terms of like the ratio, like looking at me, short-term anticipation and long-term anticipation. And as I mentioned, the new challenges gained a lot of interest. So one thing that we observed last year was it was getting very difficult to beat baselines and previous year winners, because these challenges have been running for a while and the methods are already at pretty good performance level. And so we continue to see this, like we saw a bit higher, like 71% of the methods outperformed previous year winners, but a significant amount of this was also because of new challenges which had like new baselines here. So if we only look at this number for challenges which have been running for a while, about 60% of the challenges people were able to like beat previous year winners. So we see a lot of participation, but it's not always the case that the baselines or the winning performance improves every year, just because the methods are already starting to get pretty good at it. And we had pretty good number of reports which were submitted after the challenge conclusion. So this has been always a highlight for me. Like Ego4D has strong interest from academic teams, and more than 80% of the participation even this year has come from academic teams, which is great. Like this is a pretty huge data set, but still it's great to see that academic teams are able to work and make use of this data set. Finally, in terms of the progress for each benchmark, this year we observed like goal step, which was a new challenge. But again, like within the first iteration, we saw 85% improvement in the baseline performance, which is really great. And STA is another very challenging task, but we saw a pretty significant jump this year, and similarly notable gains in moments and NLQ. So next, I'll go over 3 method highlights, which were sort of like standing out this year. First is I want to highlight this method called Ego Video, which essentially what it did is it trained like a new backbone starting from intern video 2, but collected like a large number of egocentric video text pairs to create this new backbone. And then they combine these backbones with well-established methods for other challenges, like individual challenges, to sort of like win in a very large number of like challenges this year. So they won in like they have rank 1 and 3 and rank 2 and 2 of the challenges based on this improved backbone that they have. We also have this method called Carlor for goal step, which interestingly, what it did is because goal steps within a video can be similar, like because the same step can appear several times. These are cyclical videos. And so instead of like treating them independently, what they did was they grouped them into similar goal steps and first try to predict all these different steps and then enforce some sort of like a soft prior on top of that to localize the exact goal step that you're looking. So it was an interesting approach, trying to really understand the problem structure and approach it in that way. Finally, we have the Ego Schema Challenge. It's a pretty popular benchmark right now, and big teams like from industries are also using this to benchmark their method. But we have the HCQA team, which got rank 1 in the schema challenge, and their approach was to do like clip level captioning. So they take like very short clips, 4-second clips, and generate clip level caption, and then create a summary from those captions, and then use some sort of chain of thought approach to answer the MCQ that we care about. So these were the highlights of the methods. And next, I'll hand it over to Chris to go over the EgoXO4D synthesis.
Okay, so let's talk about the EgoXO4D teaser challenge synthesis summary. Right, so the benchmark that we introduced is this ego pose benchmark. The input is going to be egocentric video, and then the output is supposed to be the 3D joint positions of the camera wear, and for both the body and hands for each time step. And the convention that we used for the skeleton is MS Coco, so 17 3D body joints and 21 3D joints for the hands. The data set that we collected for body pose and for hand pose, this is the largest manually annotated ground truth data set that exists. We currently have for hands 38,000 3D joints that are labeled, and then for the body, 376,000 3D joints that have been labeled manually. All right, so for the teaser challenge, we had a lot of participation. We had 12 unique teams. 8 were for the hand pose challenge and 4 were for the body pose challenge. And we had a very active leaderboard. And you can see that there are many, many submissions for both hand and body pose estimation. Okay, so let's talk about the Ego XO40 hand pose challenge next. Okay, so for hand pose, we're going to be given RGB egocentric video frame. And then we're going to estimate the 3D joint locations for the hands that are partially visible in the EgoView. And like I mentioned earlier, the hands are parameterized as 21 joints per hand. So here's an example of the egocentric video for the image, and then the 3D skeleton. So a little bit of motivation for this part of the data set. Many of the existing hand pose data sets are recorded in constrained environments, so usually in some kind of lab or capture system. So we wanted to break out of that and really get data from in the wild. And then in some of the data sets, it's also the case that the hand motions are quite simple. So they're just grasping or holding an object. So we wanted to go beyond that. Right. So here's some samples from our hand pose data set. We have multiple views. So we have one ego view, that's the one on the very left. And then we have 4 to 6 exo views, depending on the setup of the recording. And we recorded data over many diverse tasks and environments. So here's an example of bike repair and COVID test, cooking, and music. Okay, and let's see, I mentioned these numbers before already. So in total, we have over 4 million 3D hand key points that have been annotated. I'm not sharing the screen. Okay. So. Okay, sorry about that. Okay, so for this challenge, the metrics that we use are MPJPE and PA-MPJPE. So MPJPE is measuring the per joint estimation error of the location, and then the PA here stands for Procrustes aligned. So we're comparing everything minus the rotation and translational component of the hand. And the baseline method that we use is Potter. And we train this and evaluate it on the benchmark as our baseline method. Okay, on to the winners. So for first place, we have PCIe Ego Hand Pose. This had a performance of the PA-MPJPE as 8.49. And second place is Hand 3D for hand mesh recovery. This one had a score of 9.3. And then the third place team is the Ego Video team. And I think this Death Knight is the, okay, is the Ego Video team, 10.2. So overall, we're seeing a 23% reduction error observed by our primary metric. Okay, so some observations. So out of the different methods that were submitted, transformer-based methods were the strongest methods. We know that from other problems as well, that ensembling techniques tend to boost performance. We saw both parametric and non-parametric methods achieving strong performance. And then some of the challenging hard cases in the data set or things like occlusion and truncation when they're very extreme. And also the wrist location and hand orientation being ambiguous. Okay, next we'll move on to the body pose challenge.
Hello. Okay, so my name is Gabriel. I'm one of the organizers for the Ego Pose Challenge this year, and I'm going to summarize as just as Chris said. So the task at hand in our case was body pose estimation. So as he pretty much got the near rough idea, is you have this camera pose through time, and you have this egocentric view, for this case, a fisheye video of someone playing basketball. And what you're trying to get out of this is the 17 key points of the person within the video, or as we call it within this challenge, the camera wearer. So the challenge itself, while not overlapping with how Chris already pretty much described everything in the data set that we had, is this is a challenging task because, well, the camera wearer's body is rather rarely within frame, right? And participants had no access to any exocentric views or scene information, even though, well, of course, EgoExo was annotated through these exocentric views. The video on the left is an example of a method attempting to do this kind of reconstruction, and you can see how, compared to the ground truth, as this person's playing basketball and looking away, it's pretty hard, and it gets like drifted away through time. So our primary metrics are also MPJPE, which is pretty much the mean per joint positional error. So you get the Euclidean distance between the predicted point with a particular ID, and then you average it out over the entire body. So in our case, we also distinguished physical activities from procedural ones, since the skeletons or the generality of them are pretty much particular when comparing how you play football, for example, and when you're doing a COVID test or playing the violin. So even though those are not primary metrics, whenever I show you the leaderboard, you will also be able to distinguish how different methods did on a particular set of tasks. And in our case, well, you can see MPJPE is in centimeters, and you can see, well, exactly how does a 16-centimeter error looks when somebody's playing football. So our baseline for this challenge was only taking the camera poses through time. You get them through a linear embedding to a higher dimensional state. You put a proprioception transformer encoder, 3-layer, 8-headed one, and then you get a linear stabilizer to output a 51-dimension vector at the end, which you resize into a 17:3 answer, and then you just assign key points in a particular order and turn it that way. So our podium, on third place, we have our level-wise cross-attention BIT. So in a nutshell, they got 8 heads and a 3-layer coarse transformer in parallel with another 17 heads, 32-layer transformer, which they called fine, and they cross-attend a weighted block at the very end from each one's output. In our second place, which will be one of our spotlights later, it's called a conditional human motion diffusion model. So given an encoder-decoder style transformer with 6 layers and with 2 networks of size 550, they cross-attend with conditioning and the rotary positional embeddings. So something notable from this place is that the camera poses for these people were actually conditionals for the diffusion model, in which what they are iterating through are SMPL parameters. And you will see more about it later. The only input for this model was also the 30 Hertz slant pose. And their output is, well, the SMPL parameters I said once they went through the diffusion process. Very particular thing to notice here is that these participants didn't even train on our challenges train set, and they only transferred from a mass. Okay, very nice. And our podium winner is called multi-scale model fusion. So they implemented multiple transformer linear layers, robot layers, and MLP module, even after the stabilizer that I showed you in our baseline. And they played around with the amount of layers within several transformers, getting to 12 different models that run in parallel, and then they assemble the differences at the very end to get improved accuracy. Here are our challenges results. So as you can see, SGU has won with an MPJP of 1532. The second was from Berkeley, which got 17 times 19. STJU got 1809, and our baseline model started at 1851. The MPJ PVE, which is the velocity within different key points and frames, also got smaller as methods got higher in the podium, which is a nice touch. So our conclusion here, transformer-based methods were definitely the most popular type. Diffusion models are definitely not to be ruled out, and the general parameterization of inputs that you're going to learn about later proved a great transfer learning from a mass learned priors. Ensembling, fusing, and using different kind of models in parallel with multi-scale methods definitely boost performance. And in our case, we got a 17% reduction of the main MPJP metric.
So yeah, I think next we will do spotlight talks. We have two, one from the Ego video team, which won across several tracks, and the other is actually from the Handpose team. Apologies for the confusion there, but we'll have the Handpose team also present one of the spotlight talks. So can I invite the Ego video team member?
Hello, thanks for the introduction. My name is Xilan from Fudan University, and so today I'm going to introduce our team Ego Video solution on the first Ego 4D and Ego Exo 4D challenge. Okay, so I'm going to introduce Ego Video, a powerful visual foundation model for egocentric videos. And some of you may have heard it in the morning when in the application challenge. I'm going to introduce it again in a very brief manner. And then I will go through the Ego 4D challenge and Ego Exo 4D challenge. So I'm going to cover these tasks. So I won't dive into the details of each challenge, and I'm only going to give you a very general idea of this the solution. So if you want the details, you can refer to our code and report, which will be published soon. Okay. So first, give you a general idea of our strong foundation model, how it is trained and it is applied. The Ego Video model goes through a two-stage training. So the first stage is about video language pre-training in a general domain. As you know, the general video domain, it covers a lot of videos, far more than egocentric videos. So it can provide very good general feature representations. To be specific, the first step, we train a video encoder, which contains 1 billion parameters from a distillation training strategy from image experts such as InternVR or Eva Clips, something like this. Okay, so we use data sets including Connectix 400, 600, 700, and ActiniNet, and etc. And we drop the action labels in this stage because what we're doing is the feature distillation. We only do, you can think of it self-supervised training. Okay. So after this distillation training, we conduct a multimodal contrastive learning stage. So we have this pre-trained video encoder, and we add another text encoder, which is a BERT large model, and also video encoder. So we collect video, text, audio paired data sets, and we can do the alignment between video text, video audio, and maybe audio text. And also we do the pre-training simultaneously with image text data sets such as line. Okay. So after the video is trained on the general domain, we shift to the egocentric domain. So we do the video language post-training in egocentric domain. So in this stage, we collect a series of egocentric video datasets such as Ego4D and some of the how-to videos, which is sourced from YouTube. And instruction videos also contain some egocentric activities, but most of them are also still exocentric ones. And also a little bit videos from recent approaches that are generated automatically, such as video recap and La Villa. Okay, so here two keynotes are that more frames, for example, 16 frames are generally better than 8 frames or 4 frames. And also it costs more training stress, more training resources. And also more egocentric data leads to better performance generalization. Okay. So we use this video model to extract video features for like downstream tasks. And first, I'm going to introduce the NLQ and GoStat model, which is based on the ground NLQ, which was a very powerful model. So they're both the grounding tasks. So we solve the task in a very similar manner. We extract the video features and the text features, and we do multimodal, multi-skilled interaction like attention here and output the score. And you can see from the results that the NLQ is very challenging because many teams participated in this challenge. And so we ensemble more models like grounded VQA, which was also very good work. And also the conclusion is we have a much stronger feature and we can get really better results. So in terms of the moment query, we choose the baseline models, the action sensitive learning one. It is basically trained on localization loss, action sensitive, contrastive loss, and classification loss. And also we replace the basic 3D scene with our Ego video feature. And you can see the results that besides Ego video features, we have also implemented some features like intern video and some other features, and we try to merge them together and it leads to better results. And in terms of the long-term anticipation, we try to solve it with a large language model because large language models are better modeling the long-term relationship in the videos, like so from the Ego schema challenge, right? The basic idea is to let's continue from here. So the basic idea is to use the Ego video model to infer the current actions, and we feed them to the large language model to prompt it to, generate the next possible actions in a few steps. Okay, so you can see that the LLM can also affect the anticipation results, and as the Ego video is strong enough to predict the actions of the scene videos, so better predict actions leads to better results. Okay, so for the short-term anticipation, it is more close to a detection task. So we adopt like a 2D backbone together with a 3D backbone, and the 3D backbone here is our Ego video model. Fuse the features and optimize the classification and the bounding box loss. Okay, so the results can be seen that Ego video features indeed is better. In terms of the VQ 2D and 3D model, we adopt also a very strong baseline model, VQ lock, and do a very slight modifications over VQ lock. So we conduct a two-stage training strategy. The initial VQ lock only contains the stage 2 training, and we found that the full training, to unfreeze vision encoder in a first stage training leads to better results. Okay, so to tackle the 3D localization, we just use the model in 2D and to project it to 3D using the depths and the camera poses, which is also a similar idea from EgoLock. And as you can see, so unfreeze the vision backbone leads to better performance, and we can also achieve very good results by training free method to tackle VQ3D. Well, there might be a little problem with this slide. So the general idea for body and hand pose is that we do the multi-scale fusion, like we alter the depths of the transformer or the polling size for the polling attention transformer, so we can get multi-scale features, and we try to merge them together for better performance. Okay, so even the performance is not that high. Okay, so this is a big picture of our Ego video to solve a series of challenges in this task, and task-specific model ensemble may improve the performance for each challenge. And you can refer to our GitHub, which will be updated soon, and also the report. So one takeaway thing is that we've been doing some research on unpaired ego axle videos, because ego axle video is collected in a very time synchronous manner, because you need to record the videos with one ego camera and lots of axle cameras from static places, which is very hard to collect this data. So Ego Axle 4D is really a very good data. And we don't have that human resources and computation, so we can try to try to relieve this situation. We try to focus on unpaired Ego Axle videos to build pseudo pairs. For example, I build Ego 4D videos with Egocentric videos from how to 100 million, so we can do a lot of alignment stuff here. And also another work called Ego Axle Learn is also focused on asynchronized Ego and Axle videos, which is I'll give you a very general idea. So imagine you're a kid, so you watch your parents or the world to do things. So there's always an Axle view demonstrator here, and so you try to imitate the action from the demonstrator. So we have an Ego view follower. So this step you can achieve very unpaired data in a different environment and a different time. So like this, we are working on unpaired Ego Axle videos, and if you're interested, you can go and visit our poster session. It's listed here. Okay, so thank you.
I think we have time for 1 or 2 questions. If there are any questions for the speakers? So I had one question is, you mentioned like the impact of creating this egocentric video text pairs. Like, were there any studies which you did to actually measure that impact about just creating this egocentric only sort of data set for feature learning? Or what if you just do the combined data set? How much performance gaps do you see for some of these tasks?
Okay, we indeed did some it's a good question. We did some combination studies on the impact of different combinations of egocentric data sets, but we didn't write it in the report because we think that's going to be we need to refine some of them, so we will release them after our refinement. Okay. Thank you.
And the next spotlight speaker is Dana. She'll talk about the handle solution from the team.
So I'm here to presenting our work reconstructing hands in 3D with transformers, and we also submit use our method in the hand pose estimation challenge. And I'm presenting the work and also representing George, me, Ilya, Andrew, David, and Jitendra. So hands has been used in a lot of human daily activities. We use our hands in communication, in crafting, in gardening, playing music instruments, and also in cooking. And to understand hand activities well, we first need to understand human hands. And we have done previous work that to understand hands in 2D. So our previous work, we can find where the hand is, and also we can find the object the hand is interacting in the image. And later in our work, towards a richer 3D understanding of hands at scale, we upgrade this system to also predict the segment for the hand and the object in hand. And also we predict the hand grasp for the hand. And we also predict whether the in-hand object is a tool or not. And if the in-hand object is a tool, we also predict the second object, which is manipulated by the tool in hand. And if you're interested in this system, please check our method in the paper below. And so far, our previous work has been focusing on 2D, but hands is actually in 3D, hands moving in 3D. So in our paper, in our method hammer, we focus on understand 3D hand. And we try to reconstruct a hand mesh from a hand crop image. So in hammer, we have two ingredients that's quite important to make the method really work on even in the wild image. The first part is about the big model. So in hammer, we use the VIT edge backbone, which is much larger than the previous method Frank cap, which use ResNet 50. So the model size is increased significantly. The second part is about the data part. So in our training data, we combined 10 existing data sets. We combine all of them together as our training data. And this is 4 times larger than Frank mocap. And plus we use in the wild images from existing data. And we believe that it can also be improved to like incorporate more in the wild data in the training. Yeah, so previously we have seen results on third-person view, and this video shows our result on Ego EXO4D video, and it does quite well. Yeah, we have more examples on our webpage. So if you are interested, feel free to check more examples and check our paper. So when we evaluate our method hammer, actually we find existing 3D benchmark is quite saturated, which means that the performance of different methods, they're quite similar and cannot be distinguished. So to evaluate 3D hand reconstruction method, and especially their performance in the wild image and egocentric image, we collected this hint data set, which is short for hand interactions data set. And in hint, we use frames from New Days of Hands video data set and frames from Epic Kitchens, frames from Ego4D. We use frames from this video data set as our image samples, and then we do the 2D key points annotations for them. And since those frames they come from videos, they capture more natural hand and object interactions. And also in hint, we've focused on in the wild image, because you can see all the videos are not like captured in the lab setting. And also we have like images from Epic Kitchen and Ego4D. So we have a lot of egocentric view image. So yeah. And in terms of the results on hints, we see that compared with the previous state of the art, our method is around 3 times better on the metric of 0.05 PCA. Here it shows the result on nudist frames, and it has the same trend on the Epic Kitchen visor frames and Ego4D frames. And also in hints, we also annotate whether the key point is occluded or not, which means whether the hand key point is occluded by other objects, which happens a lot when hand is in interaction. So we also evaluate for visible joints and also for occluded joints. And you can see the results are around 3 times better on the 0.05 PCA metric. Yes, and here for the EgoEXO4D challenge, it annotates 3D key points using multiple views because it captures multiple views, it can get the 3D key points annotations. And also from EgoEXO4D, it provides a baseline method called Potter, which can predict 3D key points. And for the results, the hand post benchmark, the challenge, the primary metric is PA and PGPE, which is on the left side. And yeah, we first show the result of Potter. Yeah, this is the baseline for the hand pose estimation challenge. And then we provide our hammer results, which is just out of the box without any fine tuning. So you can see here in the primary metrics, the PA and PGPE, our hammer is already outperformed the baseline Potter. And later we try to make the method to perform better on the benchmark. So we do an example of hammer and Potter, which is we get the result from both methods, and then we do the alignment to get the result from the example of both methods. The last one is our challenge submission. So we also tried a little bit of fine-tuning hammer on the 3D key points annotations provided in EgoEX4D, and we see that when we combine, when we do an assemble of the results from the 3 models, which is hammer, Potter, and plus hammer fine-tuned, we get the best performance on the primary metric. So here are more results of our method on EgoEX4D images, and it does very well when the hands are interacting with objects and under heavy occlusions. And here are more examples, more extreme lightening, and also hand in gloves, and also hand of different color tones here. And our method is not perfect. It still have some failure cases. For example, sometimes the wrist orientation, as shown in the first row, is not correct. And also, when the hands are under heavy occlusion, as shown in the second and the third row, only a little bit of the hand are shown in the image. The method also cannot reconstruct the hand very well. And the last row shows that because our method depend on the hand bounding box as input. So if the ground truth bounding box annotation is not correct or off-centered, then our method will definitely not work here. Yeah, this is our method hammer, and thanks for your attention.
think we have time for one question.
What do you think is the more critical methods, including and stuff, gets the PA and PhD better, but without the alignment, it gets worse. Why? Because on the main metric, of course, every time you much better, but the absolute non-aligned metric, you got worse than better.
Yeah, I think the difference between those two metrics is pro-crustus alignment. So the primary metric is after alignment, and the other metric on the right side is not after alignment. So I think this is a common issue between for parametric method of parametric models which regress manual or simple compared with the other method that directly reconstruct 3 key points. So there is a hand-raised orientation prediction. So it's very hard. Yeah.
With a joint rotation, and then you again get better. That's why we align.
Yeah.
Addition. So great.
Okay, so for the final part, before we conclude this session, this is the prize ceremony that we always do for Ego4D and now for EgoXO4D. So we will be announcing winners by each challenge. And so whoever is present here from the team to represent, please come to the podium here to get your certificate, and also would love to click a picture. So yeah, we'll start with the Ego video team, which won the first place in the VQ2D challenge, and also the second place in VQ3D challenge. So yeah, so maybe you can go over there.
Yeah.
Okay, next we have the first place winner for VQ3D, the IVOL team. Do we have a representative from here?
Ego Chen.
We want to try to get that in.
Yeah, that would be nice.
Yeah.
Okay, for NLQ, the second place team is iLearn. Do we have a representative here from iLearn? No. So the first place is Ego Video.
Here they go again.
Lots of prizes and certificates.
Second place.
Yeah, second place for MQ again, Ego Video. So first place for MQ is long form video understanding team. Okay, so goal step, third place is iLearn. Second place is Ego Video. First place is Carlor team. Okay, for schema, third place is lifelong memory. NYU. Second place is PAN's Ego AI team. Do we have a representative here? Okay. First place, iLearn. We don't have a representative here. So looking at me, second place is USTB LAM team. First place is Lenovo Research. Okay. So STA, third place is SNU team.
Thank you. Yes. Congratulations.
Second place is Team Zario from Catania. And first place is Ego Video. LTA, we have the second place, HAI-PUI team. And first place is Ego Video. Okay, so moving on to Ego XO4D winners. Third place for body pose, we have the SJTU team.
They're not here.
Okay. Second place is the UCB Ego team. Do we have a representative here? First place is Ego Video. Third place for hand pose Ego Video. Second place is the Hammer team. And first place is Lenovo. We don't have them here. So yeah, before we conclude, we really want to thank Eval AI folks who always support us in the background. Like they just do so much of debugging with us every time we host new challenges. Like there's always like technical issues. So really thank. And then the CVDF Foundation for hosting Ego4D. So yeah, any feedback, challenges, definitely email us, and thanks everyone for being here and participating in our challenge and workshop.